The first question that must be answered for those starting with Arduino is to know precisely what it is. The answer is that Arduino is an open source electronics platform. When we talk about a platform, we're not just referring to the physical electronic board, but also the software. Both are easy to use. Speaking a bit more about the boards, they allow us to interact with our environment by being able to read input information, which could be, for example, a sensor detecting how much light is present in a certain space, as shown in the image. Another example could be detecting when a user presses a button. And we could also receive input information from the internet, being able to read messages from Twitter, for instance. Now, just as we can read information from the outside thanks to the board, we can also react in some way to the input information, such as activating a motor, turning on an LED, displaying a message on a screen, or posting something on the internet, like a Facebook message. We can do this by sending a set of instructions to the microcontroller on the Arduino board, which, by the way, a microcontroller is a very small computer on an integrated circuit. In the Arduino board shown in the image, it is the component enclosed in red and contains a processing unit, memory, and programmable input-output peripherals. You might be wondering at this moment, why Arduino and not other technologies? One of the main reasons is that, aside from being extremely easy to use, acquiring an Arduino board is very simple, as you can find them in any electronics store or online, and their price is extremely affordable, often available for less than $5. Another reason is that the IDE, which is where Arduino programs are created, is cross-platform. This means that it can run on a Mac, on a machine with Linux installed, and on Windows as well. This IDE is very easy to use for beginners, while also being flexible enough for advanced users to take advantage of it. Due to that feature, we find another one. Since it is an open source platform and extensible software, external programmers from the Arduino team can create tools and libraries that extend the functionality of applications or simplify complex processes by simply adding a library. Finally, since the platform is an open source project and extensible hardware, it allows all diagrams to be downloaded to create new boards, whether they are clones of the main one or have added functionalities by the user. To learn more about Arduino, we can visit its official website. We can do this by opening a browser and searching for the keyword Arduino. Here we have the first result, which is arduino.cc. Let's open this link, and here we have the main page of Arduino. What we will examine in this video are the types of Arduino boards, and we'll look at the features of the board we will be using in the course, which is the Arduino Uno. To find the types of Arduino boards, we will go to this link that says Resources, and we will click on the link that says Products. This opens the Arduino products page, and basically if we scroll down, we can see different categories of boards aimed at different audiences. First, we have the entry-level or beginner boards for those who are starting in the world of Arduino. We have some very well-known boards in the maker world, such as the Arduino Uno, the Arduino Leonardo, and other smaller boards like the Arduino Micro and Arduino Nano. Further down, we find some more advanced features of Arduino boards integrated into this category. First, a very well-known one is the Arduino Mega 2560. We also have other boards that, for example, integrate internet connectivity and other more advanced and specific features for certain audiences. Further down, we have those boards focused on the Internet of Things, which is a very well-known and widely used concept today. So we have some other boards focused on that sector, designed to optimize performance for specific characteristics to address these types of problems. We also have another section labeled Education, which basically includes some training kits. We have the section for wearables, which are devices that we can place, for example, in a piece of clothing. Lastly, we have the boards that have been removed from the market, as they have been replaced by others with greater functionalities or different improvements. The board that interests us is in this section labeled Entry Level. It is called Arduino Uno. Let's click on it. Here we enter the main page for this product, which is basically Arduino Uno Rep 3, meaning it is the third revision. We can make a purchase, if we wish, from this portal. In my case, I'm not going to buy boards at this moment, but I am interested in scrolling down to where we have a brief description of what this board is or what it was created for. And here, the description tells us that it is the best board to start with in electronics and coding, and that if it is your first experience with the Arduino platform, this board is the most robust one with which you can start experimenting. In the end, it indicates that this board is the most widely used and the best documented board in the entire Arduino family. So this is the board we have here. We can see that the background color of this board is green. However, we can also purchase, for example, a clone board that may have a different color. We mentioned in the slides that the microprocessor is a small computer, and the microprocessor in this case is this rectangle we see here, this integrated circuit. Let's review some photographs to see how this board looks. At the bottom, we have an overview of this board. If we do not want to see many specific technical details, we can read this brief description. We have the technical features section. Here, it indicates that the microcontroller is an 8 mega 328p. The operating voltage is 5 volts. And for example, regarding the input and output pins, we have 14 pins, 6 of which provide a feature called PWM. And we also have 6 analog pins, which we will analyze later. We have, for example, 32 kilobytes of flash memory, 2 kilobytes of SRAM, 1 kilobyte of EEPROM, and an integrated LED on pin number 13. We also see characteristics such as length, width, and weight. I also mentioned that this board is open source. Therefore, if we go to the documentation section, we can download the schematics for this board. If you'd like to view them quickly, you can click here on PDF schematics. Here we have the schematic for this board, so you can create your own clone if you have experience in board creation. Alternatively, you can make some modifications using one of the editable files available on the Arduino website. In the documentation, we have the files in a format for the Eagle program, allowing us to make various modifications. This is a general overview of the Arduino Uno board. We've quickly taken a general look at the Arduino Uno hardware. Now let's see how to carry out the installation of the Arduino IDE. To do this, we need to click on this link on the Arduino page that says Software. Here we will see two options, one that says Online Tools and another that says Downloads. We are interested in the second option, Downloads. Therefore, let's click on that option. Here on the software page, we see that the first result is a web editor for Arduino, where we can basically create sketches and more from a web browser. In our case, we are interested in the second option that appears further down, which is the Arduino IDE. Currently, it is at version 1.8.9. It may be that when you watch this video, a more updated version is available. You have different options for installation. For example, for Windows, you can download an installer, download a zip file, or you can even download the Arduino IDE version from the official Windows 10 store. We also have the option to download it for Mac OS or Linux. In my case, since I'm on a Windows machine, I can run the installer. Therefore, I will click on the first option. We go down to the bottom of this new page, and in case you want to contribute to the project, you can select an option here to contribute and download. Or if you just want to download the IDE, you can click on the option that says Just Download. I click on this option, which starts the download of the installer. We see that the installer is 106 megabytes, so let's wait a few seconds. After waiting a few seconds, we see that the installer has been downloaded successfully, so let's execute it. We see this license agreement. Let's indicate that we agree with it. We leave all the components selected, especially the one that says the USB driver. Next, we click the button that says Next. Here you can change the installation path. In my case, I will leave the default path and click the button that says Install. We will wait a few seconds while the installation takes place. At some point, this window may appear asking if we want to install this device software. We need to make sure to install it to avoid any conflicts. So, we click the button that says Install. Then, a new window appears to install the Arduino USB driver. Again, we click the Install button. Once we've done this, the installation is complete. We can click the button that says Close. Now, we will have the shortcut on our machines, which, if double-clicked, opens this new window, allowing us to create a program to upload to the Arduino board. With this, we are ready to continue. The next thing we'll do is connect our Arduino to the PC. To do this, we will locate the port we have here in the Arduino and connect this cable that you probably acquired when you purchased your Arduino. If you haven't acquired one, you need to get one, as it will allow communication between our Arduino and our computer. On the other side, this cable has a connection for a USB port, like the one found on common USB flash drives. At the other end, we have this special type of plug, which connects to this port on the Arduino. Now, we will carry out the connection, and if these lights turn on, it means that our Arduino is powered up and there is some communication between the Arduino and the PC. Let's see now if the PC actually recognized our Arduino, or if we need to take additional steps. How can we know if our computer has successfully recognized the Arduino board we have connected? To do this, we previously installed the Arduino software, and we have a shortcut here that will launch this application. We double-click on the shortcut, which opens the Arduino IDE. Don't worry about all these buttons right now. We'll look at them a bit later. What I want you to focus on are the options that say Tools, specifically the option that says Board. Here we can select which board we are working with. We will indicate that we are working with board 1, which is the board we have connected. Secondly, we also have something called a port under the Tools menu. A port is the communication port between our computer and an external device. It could be a printer, an Arduino board, or another hardware component. In this case, an active communication port appears, meaning we have some device connected to COM1, which is a serial port. However, you should take into account that this may or may not be an Arduino device. That is, this could be a printer or another device, so you shouldn't assume that we have a busy serial port here. We will select this port, and next, we have a tool that will allow us to obtain information about the board. We click, and we see that we have a native serial port, but we cannot obtain information from this device. What this basically means is that this port does not have our Arduino connected. It has some other device connected to the port. This has happened to me since the device I installed is a generic Arduino, not an original Arduino. Therefore, this may happen to you if you purchased your Arduino board from a local electronics store. To conduct a more accurate check, we can open the Explorer and search for the word hardware, which will essentially yield this search result, the device manager. Okay, we have it open, and what I want you to review is this area labeled ports.com and LPT. Let's expand this node, and we see that there is indeed a communication port labeled with 1, but our communication port connected to the Arduino is not appearing. This is happening because, as I mentioned earlier, my board is a generic board. The most common solution to resolve the issue of our PC not recognizing the board is to install a driver. A driver is that software piece that will allow us to recognize our hardware, which in this case is the Arduino board. For this, I will leave you this folder in a compressed format in the Downloads area, so you can download it and access it. Inside we have the installer. Let's execute it. Basically, what we need to do here is carry out the installation by clicking this button that says Install. This will install the driver called USB Serial CH340. So, let's install it. We wait a few seconds. Perfect. The driver has been successfully installed. We click Accept, close the installer, close the folder, and see what has happened. In the Device Manager, in the Ports section, we can now see a new port that did not appear before, recognized as USB serial CH340 connected to port COM6. Yours may be connected to a different serial port, so don't worry if it shows COM5, COM4, or another different number. With this verified, we can close the manager. Let's restart the Arduino IDE to apply the changes. We open it again, go to Tools, and see that in the Ports section, we now have the serial port .com6 available. Let's select it, click on Tools, and then click again on Get Board Info. Okay, notice that this time we did not get that strange message stating that it couldn't read the device information. Instead, it now indicates that we have an unknown board. This happens again because I have a generic board. If you have an original board, you will likely see specific information about the Arduino board here. Here we have something called the bit, and it indicates that we can upload any sketch to obtain this SN. With this, we can see that we have a successful connection to our Arduino board. Now, let's see how we can upload our first sketch to the board. Another way to identify if we need to install the driver that starts with CH is by observing a clear difference between an original Arduino board and a clone type board. Specifically, we can notice a difference in the type of chip used before the USB port. The difference lies in the shape of the chips. Therefore, if we find a square chip, it means we can connect our Arduino to the PC and it will be recognized seamlessly. However, if we have a rectangular chip that upon closer inspection displays CH followed by a number, then it will be necessary to install the driver I showed you in the previous module. What we will proceed to do now is upload our first sketch. This is to verify that the Arduino board is functioning correctly. Let's remove this dialog box from the previous exercise, and what we will proceed to do is go to File, where we have a section called Examples, which basically contains a series of examples for different scenarios. We are interested in this subsection called Basics, which contains the simplest examples of Arduino, and in particular, we are interested in this example called Blink. We click on it, and a new Arduino window opens. Don't worry about all the code that appears here. The only thing we will do is ensure that we have the board selected according to the one we are using, and also that we have the port selected successfully. Once we have this, we can upload this program through the button that says Upload. We click on it, the program begins to compile, which means it checks if it is a correct program. And we see that it indicates the program has been successfully uploaded to our Arduino. Let's see how it looks. Okay, if you look at our Arduino board, we have a built-in LED that corresponds to pin number 13 on the board. That is, the pin is connected to this LED to carry out simple tests like the one we're doing. Basically, what this pin is doing is blinking according to the specifications in this program called Blink. What it does is turn on this LED, wait 1 second, then turn off the LED, wait another second, and repeat this process. With this, we have verified that our program has been successfully uploaded. Let's proceed then with the course. Now, let's get to know a tool that I highly recommend for those starting in the world of Arduino. This tool is called Tinkercad. I'm going to tell you why it is an excellent tool. Firstly, it is a free tool. Secondly, it allows you to simulate your Arduino-based circuits. Thirdly, it is possible to share the various designs created with this simulator with other people. In fact, throughout the course, I will share projects created with this tool so that you can execute them from your own Tinkercad account. So what we will do to register for this tool is open a browser and type the word Tinkercad. Okay, we have this first link, which is the one we are interested in. Let's click on the link and we get to this nice website that we see here. If you do not have an account created on this site, let's click where it says Join Now, and you have different options here. In our case, we're interested in creating a personal account, so we click on Create a Personal Account, And here are different options to log into this Tinkercad account. In my case, I will log in with an email. We need to create an account. I will indicate that my country of origin is Mexico. You can place the country you are in. We will enter a valid birthday and click Next. Subsequently, we need to enter the email. I will type in my email address and set a password. Here we have a series of restrictions that we need to meet for our password to be valid, and this also ensures that it is a secure password. I will write, for example, this one that I wrote. We click on this box to accept the terms of service, and we create the account. If we reach this page, the account has been created. We click on the button that says Done, close the pop-up that appears, and we are interested in this section that says Circuits. We click on this option and notice that we can create a new circuit. Let's click the button. We have this nice graphical interface that will allow us to create different designs. We will take a quick tour of this tool. First, on the right side, we have this sidebar, where we have a set of electronic components that we can integrate into our project. There are several basic components, but they will really allow us to create quite complex projects. We have some components that you may have seen before, and we also have an Arduino Uno here. Notice how we can drag the component and drop it onto this interface that we see in the center. This way, we already have an Arduino type component as part of our electronic project. We can drag other elements if we want to, as many as we need. Okay, at the top, we have a drop-down where we can specify if we want basic components or some type of more advanced components. For example, if we click on All, we have a much larger list of components that we can integrate into our project. We can search for the component we are interested in, and we also have a button here that will allow us to list the different elements in a list. This way, we won't see a simplified list as we did here, but rather the description of each component. In the upper left part, we have different options for working with these components. For example, if we select a component and click on this first button, notice that it allows us to flip the component at will. We can also delete this component with the button here. The next button allows us to undo the change we made. So if we click the undo button, notice that the piece reappears here. We also have the button to redo an action. On the right side, we have a button that allows us to place annotations on a specific component or circuit. For example, I can place a note here. This is a note. Notice that this gives us a visual description of something we want to express, remembering that we can share this circuit with others. Therefore, writing notes is a good way to communicate what we want to achieve as part of this circuit. Here we have a final button that says Show Hide, which will allow us to view or hide the different notes that are part of the design. We also have a button that says Code, which basically allows us to code our Arduino, meaning we can input specific code for it to perform certain actions. Here, as part of this dropdown, we can choose how we want to represent this code in blocks, and text, or pure text. In our case, we will use the pure text option. We have some other options, such as starting a simulation, exporting this design, or sharing this circuit with others. This is a very general tour of this tool. It is actually a pretty good tool for those starting in the world of Arduino. And as I mentioned earlier, we will be using it in the first modules of our course. Hello, how are you, friends? I am Hector Perez from Interesting Projects. In this lesson, we will continue with our Arduino course. This time, we will talk about what to do once you have installed your Arduino IDE. If you're new, you have likely opened your recently installed IDE and found a window like the one we see here. What is the next step we should take? More importantly, why do these two things appear here? What do we have here? Well, let's look at it part by part. First, what would happen if we removed all this code we have here? We need to check that. How can we check it? In our Arduino IDE, we have a button with a check mark that says Verify next to it. This verify action will attempt to compile your program. Compiling the program refers to converting the code we will write on this screen into code that Arduino can understand. This process is called compilation. So this button will allow you to verify that you can carry out this translation successfully. If there is any type of error, we will be able to see it in this black area below. So let's try to compile this blank space we have here. We haven't written anything yet, but let's see what happens. Just to clarify, we click on Verify. If a window appears asking you to save this sketch, you can skip it. We click Cancel. Notice that a message appears saying Compiling Program. We see that immediately an error pops up. The error we get is a strange one that says an exit status of 1 was returned and that there is an error compiling for the Arduino board. Although the message doesn't provide much information about what is happening with this program, the truth is that we need to write a couple of functions for it to work correctly. We will see later in the course what a function is. But basically, these are pieces of code that are necessary in any Arduino program for a successful compilation. These two pieces of code are essential for you to learn if you want to take Arduino seriously. The syntax we need to write in our Arduino program is as follows. Void. Notice how void is written. We leave a space, and the next word we need to write is setup. For those who do not know English, setup translates to configure or configuration. So we will place a pair of parentheses, one to open and one to close, and then we will place a brace to open and a brace to close. This is mandatory in every Arduino program you write. Right now, we will see what this code we have written does. Let's try to compile this program, and we still get this error message, because there is a second functionality we need to write for any Arduino sketch to work. This second functionality will be written after this closing brace, and will be in the following form, void loop, where loop means cycle. So every time you write one of these functionalities, remember to include these parentheses and the corresponding opening and closing braces. Let's see if this compiles successfully. This time, we see a message below that says compiled. This means that our code has compiled successfully and is now ready to be uploaded to an Arduino board. You may have some questions regarding what we have written. What is this that we've written? But before that, let's look at a couple of things regarding the syntax of your program. What would happen if I removed these spaces we have here? Do you think our program would still work? Well, let's check it. Let's click on Verify. Okay, it says compiled. This means that it works correctly. For readability reasons, it's always recommended to leave some spaces so we can understand where each instruction starts and ends. You might also wonder what happens if I leave a set of spaces here. Will this compile? Let's check. We see it says compiled successfully. This means that these spaces really do not affect the syntax of our sketch. Let's remove these spaces. And another question you might ask is, what if I put this together? Will our program work this way? Let's check. In this case, we have a problem because if you notice, this is interpreted as if it were a single word. The compiler doesn't really know what we are writing here because it reads instruction by instruction, and at every space, it essentially breaks our code for interpretation. So here, it cuts this void, then sees a space and thinks, oh, I have a different token that I will interpret differently. In the next line, that's why it takes this loop as a different token or a different word and can compile successfully. However, here, since it's reading the entire word as one, it doesn't really know where this void starts and where it ends. Therefore, we need to always leave at least one line or more to separate instructions. Similarly, if at any point you forget, for example, to close this instruction, that is to include the closing parentheses, notice what happens. Let's validate the program. And it tells us that there is basically a problem in our setup function. So you must always ensure to place the opening and closing parentheses, as well as the opening and closing braces. Having understood a couple of concepts about the syntax of our Arduino sketch, let's now take a look at what we have written. What we have here is called a function. Later in the course, we will see exactly what a function is and how to create custom functions to achieve the functionality of our different sketches. For now, don't worry too much about this. Just remember that when we see a pair of parentheses and some opening and closing braces, it's a function. So here in the sketch, we have one function and two functions. These functions must be written exactly as we see here. There's no other way. If we change a lowercase s to an uppercase s, notice that we also have a problem because the compiler is actually looking for a function called setup with a lowercase letter. So remember, it is mandatory that you learn this. These two functions must be included in any Arduino sketch you write. Let's analyze each one of them. The first function, called setup, will be executed only once at the beginning of the execution of your Arduino sketch. Meanwhile, the second function, called loop, will be executed indefinitely. This means that the setup function should be used to initialize variables, initialize different components, initialize inputs and outputs, among other tasks we can perform in this function. Whereas in the loop function, we will be writing code to, for example, check if we can read a pin from our Arduino or perform comparisons to take one action or another depending on certain results. To see this practically, I will open a page called Autodesk Tinkercad to create a new circuit and show you how this works. This is an Arduino simulator, and it will allow us to simulate our components and Arduino code. In this demonstration, we will simply drag an Arduino Uno to our screen or interface here. Here we have it. If we go to the section that says code, we can write Arduino code. By default, this block section appears, but we are interested in learning the text version. Okay, here we have the text version. Don't worry too much about the pre-written code here. What we want to see now is how the setup function and the loop function work. To carry out this demonstration, I will activate something called debugging. Debugging is basically a tool that helps us see how our application is running in real time. We can place something called a breakpoint to indicate where the execution should stop in our sketch. That's what we will do here. We will activate debugging by clicking on this icon that looks like a bug called the debugger. So let's click. Here we see a message explaining how the debugger works. And basically what we will do is place a breakpoint in this section where these numbers are, indicating where we want our program to stop. We will set a breakpoint on line 3 to see how many times the setup method runs, and we will also place a breakpoint on line 8 to see how many times the loop function executes. After we do this, we will start a simulation of the program. Okay, notice that this symbol appears on our Arduino, indicating that we are connected, and the execution of our application or our Arduino sketch has started. Immediately it is stopped at this line marked with the number 3, and we can see this because we have a light blue background here. This means that we are currently debugging this program at this specific line. So we see that we have reached this setup function once. Let's click on the continue button represented by this symbol here, which says resume execution to see what the next breakpoint is that we will reach. We click now, OK, and notice that we are reaching the breakpoint placed at line number 8. Let's see what happens if I click again on this button we have here. According to the instructions we have, it takes a little while, okay? Notice that we have returned and we are back at the start of the loop function. So we stop once again at line 8. Let's click here again, and once again we reach line 8. This means that this loop function is actually a cycle that will keep executing over and over. Whereas, if you noticed, we never reach line 3 again. Therefore, this setup function only runs once, while this loop function runs infinitely. Learning how the setup and loop functions work is the first step for anyone who wants to delve into the world of Arduino. Now, let's talk about the topic of comments. What is a comment? Essentially, a comment is a section in our code that the compiler will ignore. We have two different types of comments. We will analyze each of them. Here we have a Tinkercad sketch open. We see that we have the setup and loop methods, as we have seen before. The first type of comment is indicated by a double slash like this. As you can see, these lines here have taken on a different color, and I can start writing any text here, which the compiler will ignore. If I were to remove these lines and try to start the simulation, notice that it indicates an error, as this word is not recognized as part of the code we are creating. So if we want to ignore certain words or text, we can use the double slash to ignore that text. For example, if we place this pair of slashes at the beginning of void setup, notice how these words change color. This means that the compiler will ignore these lines we see here. So if we try to start the simulation, we already have a problem, as it seems that we only wrote this pair of braces we have here. You might wonder, what happens if I have a larger comment? Well, in this case, we have a second type of comment. This type of comment starts with a single slash followed by an asterisk. To end this type of comment, you must write it in reverse. That is, write an asterisk followed by a slash. Everything within this section we see here will automatically be ignored by our compiler. This is a multi-line comment, while this is a single-line comment. What is the purpose of a comment? A comment can be used to specify a certain type of data or information that we want to convey to someone reading our code. For example, you can specify in the comment when you wrote this sketch how many revisions it has gone through, or describe its purpose and composition, among other comments. You can also add these comments throughout your sketch. For example, I can place a comment here, start setup, and then, for example, within the loop, start load. So we have a reference for ourselves or for someone external reading your sketch about what certain functionality is doing. Hello, how are you, friends? I am Hector Perez from Proyectos Interesantes. Welcome once again to a new lesson in this Arduino course, From Zero to Maker. In this session, we will discuss a topic that is very important to learn when starting with Arduino or any programming language. The topic is variables, which is essential as it allows us to manage different variables to store information throughout our Arduino sketch. We will approach this practically, as we did in the previous video. First, we need to define what a variable is. Well, a variable is a place to store information in the microcontroller. Something very similar happens with us. For example, if I tell you that I found a 20 pesos coin on my desk yesterday and I ask you about the value of that coin, you'll likely answer 20 pesos. Or if I say that the year 2005 is the birth year of Arduino, and I immediately ask you, what year was Arduino born? You will probably answer me that it was in the year 2005. Why does this happen? Well, because your mind has created a space to store these values instantly. It's the same thing we can do with Arduino. We can specify or indicate that memory spaces be created or reserved to store information that we will need throughout our Arduino programs. Surely, even if you haven't noticed it before, you have worked with or seen the use of variables in action. For example, let me give you a practical example. Here we have a screenshot of a project that is essentially a game using Arduino. If you look closely, we have here a runner that jumps over various obstacles. In the upper right corner, we see a number that says 95. This value increases as you progress through the level we have here. How is the management of this number carried out? Well, through a variable. Let's look at another practical example. Here we have a project we created earlier where we displayed the distance from our HC-SR04 sensor to an object. It is important to note that this sensor does not give you the distance as we see it here. It does not give you 42 centimeters to an object, but rather a different type of information. However, by performing a calculation, we obtain this distance. This distance is stored in a variable so that we can display it on our LCD display. Well, we already know what a variable is. Now, there's another point we need to address before we start writing code. What are data types? We have several data types, and each data type allows us to store a different kind of data. For example, if you want to work with integers, you can do so with a specific data type. If you want to work with strings, you can do that too. If you want to work with decimal numbers, you can also do that, as well as with Boolean values. We have other data types, but the most important ones are separated in a table on the interesting project site. Here we have this site. In this tab, we have a table with the most commonly used data types. In one column, we have a description of what each data type is for. For example, if we want to use integers, we need to use a data type called int. if we need larger integers, because if we look at this first row, it says that the range we can store with this data type is from minus 32,768 to 32,767. In the event we want to store a value that exceeds this range, we could use a long data type, which allows for a greater quantity of numbers. We also have, as I mentioned earlier, decimal numbers. In this case, we could use either the float data type or the double data type. Here we can see the amount of numbers they can store. We can also see that we have strings, single characters, and Boolean values or Boolean data types, which store either a true or false value. Okay, it is very important that you keep in mind these data types that we see here and learn how to write each one of them, as we will use them in each of our Arduino sketches. Now that we know what a variable is, what a data type is, and what the most important data types are, let's move on to our code or our Arduino sketch. I will use tinkercad.com again. I recommend that you create a free account, as you can simulate different circuits on this website, and it is completely free. Well, let's create our first variable. Well, how are we going to do this? By following a simple formula that I'll write here. The first formula we will follow is this. We will specify a data type plus the variable name plus a semicolon. The semicolon is very important, and it is something that many beginners in programming forget. I recommend that you always keep it in mind. So, following this formula you see here, we will first write the data type. What data type do we want to use? For example, suppose we want to store an integer number only. We do not want decimal points. In this case, data type that corresponds to the description of integer numbers is int. So we return to the program and write int space, the variable name. This variable name can be whatever you want. However, there are a series of rules that you must follow when naming variables. For example, naming a variable 1 is fine. It is incorrect to name a variable that starts with a number, like 8 variable. This is incorrect. You cannot have variables that start with a number. You also cannot have variables that contain special characters. You cannot declare a variable this way, as the use of symbols is not permitted. What is allowed is writing a variable that starts with a letter and contains numbers. For example, variable 1 and variable 2. This is correct. Now let's rename our variable to data1. Remember to write the semicolon that I mentioned earlier. Okay, at this point we have created our variable. Now what? How can we assign a value to our variable? Well, that is the second point. Once we have declared our variable, we can use it as part of our sketch. We can then write data1, type the equal sign, and specify the value we want to store in our variable, for example, the number 8. After performing this assignment, we must also write a semicolon. At this point, we should have the value of 8 stored in our variable data1. Let's run a test. To conduct the test, I will assign another value to data1. For example, the value 5, and I'll write the semicolon. I will do this because in debug mode, this simulator does not let me see the values unless we write something like this line we see here. Now, let's proceed to place a breakpoint on this line number 7. Let's start debugging as we saw in the last lesson by clicking on this bug icon. Click on Start Simulation. Okay, we reached this line before assigning the number 8 to data1, as the assignment will be reflected once we pass this line. If we look closely and position ourselves over data1, we see that it has a completely different value from what we want to assign, which is 22,016. This is happening because the variable has not been initialized with a value yet. So at this moment, the variable can hold any value we can imagine. Once we reach this line, we will assign the value 8 to data1. Let's click on this second icon to move to the next line. After passing line 7, notice that if we position ourselves again over data1, it now successfully holds the value of 8. If we clicked on this icon again, we would move to the next line. Unfortunately, at this point, we can no longer see the variable values, but at this moment, data1 already contains the information of the number 5. What happened here? Notice that we can no longer retrieve the value of 8. Once you assign a value to a variable, the previous value disappears and is no longer stored. Therefore, you must be careful with the assignments you make to your different variables. Okay, I'll stop the simulation and we'll look at a second way to create a variable. At this moment, as you have observed, we have created our variable, and on another line, we assigned the value 8 to this variable. We can simplify this and shorten these two statements into a single step. How do we do this? We will do this by following another formula. Data type plus variable name equals initial value, semicolon. Okay, here we will follow the same steps as before, but before placing the semicolon, we will directly assign an initial value of your choice. For example, we will write int.o2 equal to 5. As you can see, we have simplified these two steps into a single line, int.o2 equal to 5. This will create the variable and assign it an initial value at once. In case you want to create multiple variables at once, there is also a simple way to do that. For example, let's say you want to create the variables .03, .04, and .05 of the integer data type. Well, we will do it in a more simplified way. We will write int.03, .04, and .05, followed by a semicolon. Here, these three variables of the integer data type will be created. It is very important to note that if you want to create multiple variables at once, they must be of the same data type. You may be wondering at this point, what happens if I want to use a variable without declaring it in this way, or in this way, or in this first way? For example, what if I want to make a direct assignment to a variable that does not exist? For instance, .08 equal to 8. As you can see, .08 has not been created in this way. Let's see what happens if we start the simulation. Okay, we see that immediately we get an error message indicating that .08 was not declared in this scope. Therefore, if you do not declare a variable, you will not be able to use it in your Arduino program. As part of the recommendations for creating variables, you should ensure that your variables make sense. What would happen if, for example, you had a sketch from one of your classmates or a friend who wrote a variable called variable1? You really wouldn't know what this variable refers to. Is it storing a value from a sensor? Is it referring to a pin on Arduino? Or does it refer to some mathematical calculation you're performing? We truly do not know what this means. However, if we specify a variable like this, int pin sensor humidity, we know that this variable refers to a pin on our Arduino related to a humidity sensor. This, if you notice, makes much more sense than the variable we have above. Well, let's explore other data types. Let's delete this code we've written to avoid any issues and return to the data types page. Let's try different data types. Let's see what would happen if we exceeded the range we see here. What would happen if we wrote a value less than 32,768 or a value greater than 32,767? Well, let's see it in action. Let's declare a variable called big number that is equal to, we'll copy the number 32767, remove this comma to avoid problems, and write the semicolon. We will proceed to assign another number for debugging purposes. For example, big number equal to 0. We set the breakpoint, start the simulation, position ourselves over big number, and notice that we have this number correctly. However, let's increase this value by, for example, 3 numbers to 32770. Let's restart the simulation. We position ourselves again over big number, and notice that we do not have the number we specified during the initialization of this variable. We have a negative 32,766. Where did that number come from? Well, in reality, this variable can hold any value we imagine, since we are exceeding the range accepted by this int data type. Therefore, you must be careful to ensure that a number stored is within the range of the specified data type. In this case, if we want to store a larger number, we would need to use a different data type. If we look at the description, we have larger integers, so we would use the long data type. We write that the data type is long. Start the simulation again. And if we position ourselves over the large number this time, we see that we have the correct value in our large number variable. Let's stop the simulation and return to data types in Arduino. Another question I get a lot is, what would happen if we wanted to write a decimal number as part of this long large number assignment? Well, let's try it. Let's indicate that, for example, the initial assignment of large number is equal to 78.2. We start the simulation and we see that there is no problem. However, if we position ourselves over the large number, we notice that the value is 78, so the decimal point has been removed. So while you can assign a decimal number to your integer type variables, the fact is that the decimal point will be cut off, meaning it will not have any decimal points as part of the values of these variables. If you want to use a decimal point, you would need to use a float or double data type. Let's write the word float to assign the data type. Start the simulation once more, and as we can see this time, as part of the large number, we now have a decimal point included in this variable. We stop the simulation, and let's see what other data types we have. We have a string data type. Here we can copy this variable, or the variable creation we have as an example to test it. Okay. As we can see, we declare a data type called char. The char data type collects a single character. However, when specified this way, it creates an array of characters. In other words, we are storing multiple characters at once. As you know, a word is made up of characters. So what we see here is called an array. This is a point we will discuss later. But basically, an array is a way we can store many values in a single variable, as if we were declaring multiple variables at once, but within one variable. In this case, we are creating this string, which is a set of characters with the word Arduino. If we start the simulation right now and position ourselves over str4, we can see that we indeed have the word Arduino. We could easily display this word on an LCD display. Let's look at another data type, the char data type. We will copy the example we have here. We will paste it at the bottom. As you can see, a string, which is a set of characters, can store a collection of characters. However, a variable declared this way, which does not have the brackets we see here, indicates that it can only store a single character. Therefore, you should be cautious if you want to store an A, an 8, or a U, since you will not be able to store a string like Arduino. In fact, if we test this and position ourselves over my char, notice that we're storing in this variable only the last character we assigned, which is the uppercase O. This is the difference between declaring a string this way and a character as we see here. We have other data types such as the Boolean data type, which basically allows us to have either true or false. Let's copy this variable and paste it as part of the sketch. We'll run the application to see how this looks. We hover over running and see that we have a value of false here. These Boolean variables will be very useful when we get to this section on conditionals. In these Boolean variables, we cannot store, for example, the number 6. If we start the simulation, we see that there is no problem. But when we hover over running, we can see that we do not have the number 6 assigned to this variable. Instead, we have a value of true. So we can only store either true or false. In fact, for this data type, we could store the number 0 for a false value, or the number 1 for a true value. But if you prefer to use the words directly, you can write the value false or the value true for true. Okay, now that we've covered this point, let's talk about variable scope. Here in our example, we have declared all the variables within this method called setup. What would happen if, for example, we wanted to use this variable called large number within this method loop? Let's try it. Large number equals 8.7, for instance. Let's start the simulation to see what happens. And notice that we get an error message saying that large number has not been declared within this scope. This basically refers to the fact that we're trying to use this variable large number outside the place where it was declared. Or in other words, we're going out of the variable scope. The scope of the variable, and a simple way to recognize it, is defined by these braces we see here. This is the scope of the variable big number. As we can see, this method loop is outside the scope of the variable. Speaking of this variable scope, look at what happens if I try to declare this same variable again. That is a float variable named big number. We start the simulation and we already have a problem indicating that big number has already been declared. However, if we cut this piece of code and move it to the loop method and start the simulation, we see there's no issue, since this variable named big number is being declared within the loop method, which is a different scope for the variable. Therefore, we cannot declare the same variable twice within the same variable scope. As a part of this topic regarding variable scopes, if we had a control structure as part of our method, this control structure will be discussed later, so don't worry too much. If I declared a different variable here, for example, a bool running equal to true, the scope of this running variable would be what we see here, the one within the braces, as I mentioned earlier. However, an external variable with a broader scope, like big number, can be used within this subscope we see here. So here we could do something like big number equal to 2.3. Since this big number is still within the scope of its variable. So this is a point to keep in mind for future lessons. Past this point about variable scopes, what would happen if you actually needed to use this variable big number within the loop method while maintaining the same value for this variable? That is, this variable declared here could have a value, for example, 2. This value 2 will be different from this big number variable, as they will be two completely different variables storing entirely different information. However, if you want a single variable to store all the values in your sketch, you can do that as well. These variables are called global variables, which, as the name suggests, work throughout the entire Arduino sketch. To accomplish such a declaration, we need to declare the variable outside of the methods we see here. So let's cut this variable. The declaration remains the same, including the data type, the variable name, and the assignment if desired. With this, you will have a global variable that will work throughout your sketch. For example, we can remove this declaration of the large number variable and keep the same assignment. Let's see if this works correctly. Okay, as we can see, we have no issues since large number has been declared as a global variable. Therefore, we can use it both within the setup method and the loop method. Lastly, to conclude, let's talk about constants. What is a constant? It is a special type of variable that allows us to have a fixed value that will never change throughout the sketch. This can be useful, for example, if you need to declare a value that will be part of a formula, such as the value of pi, or any type of data that you know will never change, like the pin to which a sensor is connected on the Arduino. We know that a connection on our electronic board will never change. Thus, we can declare a constant or a variable as a constant. To carry out this declaration, we simply need to write the word const before the variable declaration, specify the data type such as float, and the variable name, for example, pi value, which equals 3.1416, followed by the corresponding semicolon. If we start the simulation, we see that there are no issues. However, if we want to change the value of this constant, for example, setting pi to 8.8, and we try to start the simulation, we find that there's an issue indicating that this variable pi is read only, and we are attempting an assignment. Therefore, we cannot modify variables that have been declared as constants. In this lesson, we will see what a method is and how it is declared. Methods are a very important concept for you to understand in Arduino-based sketch or any sketch you encounter in any project. To carry out this lesson, we will start with a project located at this URL, which I will provide as part of the attached files for this class. Once you paste this URL into your browser, it will display a page like the one we see here. What you will do with your account is click on the button that says Copy and Modify. This will open the designer we see here with the components already pre-assembled. Don't worry about assembling these components right now. What we will focus on is this section that says Code. Here, I have previously created some Arduino code, which you don't need to worry too much about in this area and at the bottom. We will mainly concentrate on the setup and loop methods. But before that, let's analyze certain information that I have written earlier. This is the lesson on methods, and look at what it says, available functionalities. I created this to give you a better idea of what you can do with this sketch. So before we analyze what I have written, what is a method? A method is a functionality that we can execute which someone has previously written, whether it be ourselves, another person, or someone from the Arduino team. These functionalities refer to what the device you are giving certain instructions to can do. For example, in this case, the instructions will be directed to the Arduino to perform a specific task. In this specific sketch, we have 6 different actions. The first is called initialize, and the second is called write. But note that here, I have also written that this functionality can write either a string or an integer. Where will it be written? On this display that we see here, this screen here. We also have another functionality to position where we will write this text string. We can specify an X point and a Y point. This is different from what we had before, where we specified either a string or an integer. In this case, for positioning, we need to provide an X point and a Y point. We can also clear information from the screen and wait for a certain time before carrying out another action. Here, we can pass an integer that will represent the number of seconds we will wait. Finally, we have a functionality called play, which will basically allow us to sound this buzzer or emit a beep. Once we understand what our Arduino program can do, we will need to indicate how these actions will be executed. These tasks are pre-programmed, but it is our responsibility to write how they will be executed, how many tasks will run simultaneously, how they will execute one after the other, etc. The first functionality we need to write is the initialization functionality, as this will allow us to pre-configure our entire environment here. Now, let's see how to use this initialization functionality. We will go to our setup method, which we have already discussed before, and we will start by writing the name exactly as it appears here, initialize. You could copy and paste this code, but I recommend that you write the functionality to gain experience with your sketch. So let's write initialize. What you have here must be written exactly as it is. You cannot have an uppercase R, a space, or any strange character within this name, as this is how the functionality name has been defined, and it cannot be changed for any reason. We write the final R. Once we have written the functionality that we're going to execute, we need to write a pair of parentheses. Whenever it is a functionality, we will write a pair of parentheses and a semicolon at the end. As you may remember, with variables, we wrote the semicolon. But in the case of functionalities, we need to include one opening and one closing parenthesis. As in our descriptive document, we see that we only need to write initialize. We already have the functionality ready to carry out the pre-configuration or the initial setup of our circuit. Let's go back to see what other tasks we can perform. Okay, we have a task here where we can instruct our Arduino program to write a message. Okay, let's invoke this functionality. So, let's write write. Remember the parentheses and the semicolon. If we try to initialize our simulation, notice that we already have a problem. And basically, the issue is telling us that the candidate or the function is expecting an argument. This is because there are functionalities that need information to work. In this case, initialize does not require any type of information, as the necessary code to initialize our components is executed internally within this functionality. However, in this write method, information is needed because thinking logically, when we want to write a text message on the screen, we need to know what we are going to write. We cannot just send a write message and have random text appear. Well, this could actually be done, but the reality is that when we want to display something on the LCD screen, it is something we need to show. If we go back to the documentation of this sketch, we see that it states this write functionality receives a string or an integer. Therefore, let's return to the definition of the write execution, and we will send a string. How can we do this? A string is represented between a pair of quotes. So, between these types of quotes, we will write a message, for example, Ector. Well, let's start the simulation again and notice that it seems to have turned on the screen, but nothing is displayed. Don't worry about this. All you need to do to solve this problem is to move this knob to the right. Okay, now we have the name displayed in a very simple way. What we have done is called invoking a function. What we see here in the functionality is known as a function or method. So we are first invoking a function called initialize, and then a function called write, which receives a string parameter with the value vector. Let's stop the simulation and see what more we can do. We return to the top and notice that we can also position our cursor so that it starts writing at a certain point on our LCD screen. This LCD screen, which we will see later in the course, has 16 positions in length and 2 positions in width. That is to say, we have 16 columns and 2 rows. Therefore, we could specify, according to this documentation, an X point to move to a certain position in the columns and a point to move to the row positions. Let's try that too. After writing the first string, we'll write position, which is the name. This is the name of our functionality, position. And note that we need to pass a parameter or a value for the X coordinate and also a value for the Y coordinate. So let's write position. Remember to add the parentheses and the semicolon, and inside we'll specify a parameter for a position in X. These parameters must be integer values. Now we will indicate that we want to move to column position number 5, and we will specify that we wish to go to row number 1. Remember, this refers to the X coordinate and the Y coordinate. Once we have positioned ourselves, we'll write another message. For example, we will change this first string to hello, and the second string will say something like maker. Let's try this. We start the simulation once more. Note that we already have the first string displayed here, positioned at location 5,1. Observe that it counts as 0, 1, 2, 3, 4, 5. Since the numbering of these columns and rows starts with the number 0, not with 1, as we are used to. This may sound a bit strange, but that's how it's handled here. So we count 0, 1, 2, 3, 4, and 5. This is why the letter M, or the word maker, is located in column number 5 and row number 1. Okay, let's stop the simulation and return to the instructions we can execute as part of this sketch. Note that we can also clear our screen. As we can see, this functionality does not receive any parameters or any type of information, so we will invoke it after this write functionality or after the invocation of write. So we invoke the clear function without any information. Placing a semicolon in the parentheses, we start the simulation and notice that only the word hello briefly flashed on the screen, but this was very quick. This happened because we invoked the clear functionality, but we didn't give enough time for the 2 messages we see here to display. Let's stop the simulation once again, go to the top, and notice that we also have a functionality to wait for a certain time. How long are we going to wait? Well, we can pass an argument, which is an integer representing the number of seconds we can wait before carrying out another action. So returning to our setup method, before clearing our screen, we'll write wait. Remember to include the parentheses and semicolon, and inside, we will specify how many seconds we want to wait before executing this functionality to clear our screen. We will specify that we want to wait, for example, 3 seconds. Let's start the simulation once again. Okay, the messages appear, and notice that after waiting for 3 seconds, this screen is completely cleared. Finally, let's check that we have one last method called touch, which will allow us to activate the buzzer we see here. Let's test this functionality so that after clearing, it alerts us that this screen has been cleared. Let's then invoke this functionality or this touch function. Let's start the simulation. Okay. And you could hear a sound, which is the sound of the buzzer we have here. This is how these methods we predefined as part of this sketch work. The important thing about this lesson is that you get used to how different functions are defined in order to invoke various methods. These methods are ones that I have written or prescribed for you to practice. However, Arduino sketches will consist of entirely different methods that will accept all kinds of parameters. So, I recommend that you continue practicing by creating different definitions to write various words. Essentially, practice with all these methods I have provided for you, so you get more and more accustomed to the correct syntax for invoking methods. Now that we know what a method is and how to invoke one, suppose someone asks you to create a sketch to implement the following functionality. First, to display a message on the screen. Second, to keep that message on the screen for 3 seconds before clearing it. Lastly, to play a sound notification to inform the user that the LCD screen has been cleared. Okay, to carry out this task requested of us, we will remove all the previous definitions, leaving only this functionality to initialize our circuit. Remember that the first task is to write a message on the LCD screen. Therefore, we will call the write method and pass it a parameter, such as Ector. The second point requested was to wait 3 seconds before clearing the screen. Thus, we will invoke our wait method and specify to wait for 3 seconds. We will clear the screen's content once the 3 seconds have passed. And finally, we will play our sound notification. If we wanted to display a second name on the screen, we would need to invoke the write method and pass it a second name. We wait the 3 seconds, clear the screen, and play the sound notification. This is a repetitive action that we would have to do over and over whenever we want to display a message on our screen. This is the case because someone specifically requested it to be done this way. What is the problem with what we're doing? Well, the problem is that we could write a third name, wait 3 seconds, and directly play the sound notification. Here, the error we have is that we forgot to call this delete method, which would cause here we have an error. We're missing an R. If at some point you see that the screen lights up, but nothing appears, remember to adjust this switch we have here, or this potentiometer, and the name will appear. However, if you noticed, this name appears, but it has not been deleted. Let's stop the simulation, and perhaps you could say that the easiest thing might be to copy and paste this code we see here. You might be right, but look at the amount of code we have just to display 3 messages on the screen. To reduce this amount of code, the ideal approach is to create a new functionality or a new method to encapsulate what we're doing repetitively so we don't have to write it over and over again. Let's then create a new method that will be part of this sketch. To write a new method or functionality, make sure to be outside of this pair of braces we see here, outside of any pair of braces. In this case, we are outside this pair of braces and the pair above it, as we have here. So we position ourselves, for example, below the setup or underneath the loop. And we're going to use a formula, return type plus method name plus parameters. Let's then start writing or defining a new functionality for the sketch. The first thing we need to define is the return type. In this case, don't worry too much about the return types as we will cover this in a later lesson. In this case, we will use a void return type, which means empty. That is, we are not going to return any type of data. The next piece of information we need is the name of the method. This name can be any name you choose, with one observation. If you have noticed, the method names we had above always represented an action. Writing is an action. Waiting is an action. Deleting is an action. Touching is an action. Therefore, I recommend that your methods always be specified as if they were actions. What are we going to include in this method? In this specific exercise, we will include the parts that do not change, meaning the invocation of the wait method, the invocation of the delete method, and the invocation of the touch method as well. What would be a good name for our method? I think the name clear LCD would be sufficient for this method, so I will name this method clear LCD. Now we have the name. We still need to specify the parameters for this method. The parameters, as we will see later, are the information with which our method will work. In our case, since we do not need any type of information, we will include only a pair of parentheses, one opening and one closing. Immediately after the parentheses or the closing parentheses, we will add an opening brace and a closing brace. This way, a method is defined. By the way, this is one of the simplest methods since we are not passing parameters and not returning any type of data. Within these braces that we see here is where we will write the series of actions we wish to execute when this clear LCD method is invoked. So let's go back to the top and proceed to cut the lines for waiting, deleting, and touching to paste them into the clear LCD method. This will ensure that every time this clear LCD method is invoked, these three actions will be executed without any mistakes. This means we can go back to the top, remove these three lines that we had after writing this name, and also remove this pair of lines after writing the last name. Instead, after calling the write method, we can invoke this new functionality that we defined. In this case, you're going to invoke clear LCD. Remember to place the parentheses and the semicolon. How do we know that we don't need any parameters? Well, because in the definition of our method, we are not receiving any type of information. So, after this write method, we will also invoke clear LCD, and after writing the last name, we will invoke clear LCD again. Let's check that everything is working fine by clicking on Start Simulation. Okay, we have the name Hector, then Ricardo, and lastly, notice that the screen has been successfully cleared after printing the last name. In my case, I haven't heard the horn since my computer speakers are off, but you have probably heard it already. Let's stop the simulation and review the step-by-step execution of this program. We will place a breakpoint on line 46. Let's enable debugging, which remember is by clicking on this bug icon we see here. We start the simulation, place a breakpoint on line 47, and click on Continue. The name is written, and we will perform a step-by-step debug to enter the invocation of this clear LCD method. Let's click where it says Step into the next function. Notice that when we invoke this clear LCD method, we go directly to the definition of the method that we have written. Let's click once more. Note that we wait 3 seconds, clear the screen, and press the horn. This is done every time we invoke the clear LCD method. This is how we can define our own methods or functions to reuse code that will be executed repeatedly. We already know what a method is, how to declare one, and now in this lesson, we will discuss the parameters of a method. As you can see in our sketch that we have created so far, we already have the functionality ready to clear an LCD. I want you to notice that as part of this setup method, we have a repetitive pattern. We can see that we invoke the write method followed by the clear LCD method. This repeats 3 times, and it would continue to repeat since this is the functionality that a fictitious person has requested. How can we solve the issue of not repeating this code over and over again? Well, by creating a new method to write a person's name that immediately clears the LCD screen. So let's write a new method as part of our sketch. We will indicate that we do not want to return anything. I repeat, we will cover data return in a subsequent lesson. Let's name our method, for example, greet. We will place parentheses and immediately add the opening and closing braces. Now, let's proceed to copy a couple of lines from our setup method, paste these lines, but notice that we encounter a problem. The issue is that this call to the write method is passing a specific name as a parameter. At the top, we see that we invoke the execution with a different name in this line, and with another different name in this other line. This is a piece of data that changes every time we call the execution of the write method. How can we resolve this issue so that we can pass any name? Well, we will solve it with something called parameters of a method. A parameter, as I mentioned earlier, is a set of information that our method can work with internally. In this case, the parameter will be a string which we will be able to replace at runtime so that it displays a different name on our LCD screen. This definition of parameters is specified within the parentheses that we see here. How do we define these parameters? First, we need to indicate the data type we want to work with, and second, the name of the parameter. In our case, to know what data type we need to specify, we will look at the definition of the method invocation for writing, and we see that it takes a string parameter. String in English is string, and we have a data type. Remember, we have seen this before, which is called string. So for this method's parameter, we will write the data type, which is string. We place a space, and the second name will be the name of the parameter that you want to use. This name can be whatever you want, as long as it is descriptive. I will then set the parameter name as name. This parameter will then hold the information that the method will work with internally, so we can remove this predefined string and replace it with name. Therefore, this parameter can have any name, Hector, Ricardo, or any other name you can think of, as long as it is a string data type. We return to the top, and instead of invoking this pair of methods, we will directly invoke the Saludor method, passing the name, which in this case is Hector first. We also remove this second line, invoke the Saludor method passing the parameter Ricardo, remove this pair of lines as well, and call the Saludor method with the name Anna. Okay, let's test our program execution. We see that we have Hector, the name Ricardo, and the name Anna executed successfully. This is how we can modify our methods to handle information internally. Now, as part of the parameters of a method can have any number of parameters you need. For example, suppose someone requires you to select the line where the name will be displayed. As we have seen so far, the name always appears in the first row or at index 0, but I suppose we need to allow the user the choice to write in line 0 or line 1. Well, to carry out this action, we could modify our greet method and add a second parameter to specify this information. How can we add a second parameter? This is done by placing a comma after each of the parameters, specifying again the data type in the parameter name. What data type do we need? Well, the possible values are 0 and 1, therefore the data type is an integer. We then indicate that the data type is an integer, and the parameter name can be whatever you want. In our case, a descriptive name would be line. Now that we have specified the second parameter, we need to modify the functionality within this method to position the line where we need to write the name. As you may recall, we have a method as part of that functionality called position, which takes an x parameter representing columns and a y parameter representing rows. Let's invoke it then. Before writing the name, we write position, the parentheses, and the semicolon. As part of the parameters for this method, we will pass the x value, which will be 0 since we always want to write our name in the first column. The parameter line corresponds to the parameter called line. With this, before writing the name, we will position our cursor in column number 0 and in the line we desire. Now that we have this, if we try to start the simulation, note that we have 3 problems here. As you can see, it indicates that there are too few arguments for the greet function, which requires a string parameter and an int parameter. In other words, we need to specify on which line we will place the message from the greet method. So let's indicate that first of all, we want the first name on line number 0, secondly on line number 1, and lastly again on line 0. With this change we made, let's start the simulation once more. I will restart the simulation. Okay, we have the name Hector. The name Ricardo has appeared on line number 1, and the name Anna again on the first line. This is how we can specify different parameters for our defined methods, allowing us to be increasingly flexible with our various methods to meet our needs. Now, let's talk about the return of data from a method. Imagine someone has asked you to create a function to sum 2 integers. You might think it's something very simple. Well, let's do it. We will define a new functionality called sum, which receives 2 integers. For example, number 1 and number 2. We could simply execute the write method, which, as you might recall from above, can receive a string or an integer. Now let's go to the bottom and print the sum of number 1 plus number 2 on our display. This operator we see here performs the addition of number 1 and number 2, and thanks to the invocation of the write method, the sum will be printed. Let's then return to the top, comment out the greet method, and instead invoke this new method we just wrote, passing, for example, number 8 and number 56, to see if everything works well. We start the simulation of our application and see that we have the number 64 as a result, which means it is working satisfactorily. Now, imagine that the same person who asked you to create this program now wants to retrieve the sum of these two values to later perform a third calculation, such as division by 2. Well, this gets a bit more complicated, as there is no way to retrieve the sum method's result since we need to perform the third operation within the setup method. How can we solve this issue? This is where the return of data from a method comes into play. How can we enable the return of a value as part of a method? Well, it has to do with the data type to be returned, which is the first specification that is part of one of the methods. In this case, we are stating that we do not need to return any data. However, here we can change the data type that we can return to any valid data type. Many of these data types we have already seen in previous lessons. In this case, the sum of two integers will be a third integer. Therefore, we can change this void to indicate that we want to return an int data type. We need to stop the simulation and change the void to int. By doing this, we are automatically indicating that the sum method must return an integer data type. This is not optional. If you specify that you need to return a data type, you're automatically indicating to your method that it must return an integer. How do we indicate the value we're going to return? Well, it's done with a special word called return, which means to return. Here we could write any number. For example, 32. This would work very well since we're returning an integer. However, even though we could return any integer, we are interested in returning the sum of number 1 plus number 2. Therefore, we could take this sum and pass it to the return statement. So instead of returning a fixed number, we can directly return the sum of number 1 plus number 2, removing the method call to write. And this sum method would focus solely on performing the addition of number 1 plus number 2 integers. Now that we know how to return a value, let's see how to retrieve it. In this part where we invoke the sum method, we can create a variable, for example, int sum, which is equal to the invocation of the sum method. What this will do is execute this method, which is the addition. Since the addition returns the sum of number 1 plus number 2, we will automatically have the resulting number of the operation in the variable sum. Therefore, we could directly write on the LCD display sum between 2, for example. If we start the simulation now, you'll see that we already have the number 32 displayed, which is the sum of 56 plus 8 divided by 2. Here we performed a very simple operation, but in reality, you could have a series of operations within a functionality and return only the result of executing these complex operations. Remember that you can return any type of data and always retrieve it by declaring a new variable. If you're a bit curious, you might be wondering how the write method can accept both a string and an integer, meaning two completely different data types. The answer to this is called method overloading. Method overloading is a technique that allows us to change the data type of a function that has the same name, enabling two different calls to the same function. If we examine the functionality of the write method located below, notice that we have two methods with the exact same name, that is, write. The only thing that changes here in the signature, which includes the entire method definition, is the data type being received as part of the parameters for this functionality. As part of the method overloading rule, the method must have a different signature to allow for two instances of the same method name definition. For example, if I change this data type from int numero to string numero, notice that even though the parameter has a different name, if I start the simulation, I have a problem indicating that we are trying to redefine the void write method with a string parameter. Note that we do not have the parameter name here, only the signature void write and a string data type. So this is one of the first rules. You must have a different data type for each parameter definition. You might think that by changing the return type so that our first method returns nothing, and the second method returns an int data type, this issue would be resolved. Let's change the definition back to string. Notice that this doesn't work, as what we focus on for carrying out method overloading is this definition we have here. The name of the function and the data type of the parameters we have as part of the method definition. Let's revert this to how it was. One of the advantages of method overloading is that we can specify different methods with a varying number of parameters that are part of these methods. For example, remember that earlier we had a method called greet? We can redefine a new method called greet, but that only receives the name of the person. Let's copy these lines. Remove this line for positioning. This method, which only receives a name, will imply that it does not need to position the name in any row. So it will proceed to write the name in the first row of our LCD display. We could have a third method, for example, that receives a name, a line number, and also the amount of time before performing the clearing of the display. So let's go back and copy these three methods or the invocation of these methods. Where would this time parameter go? Well, as you can see, we are invoking the clear LCD method. This clear LCD method by default specifies that we will wait 3 seconds before clearing the information on the screen. We can also solve this issue of being able to change the value of this number of seconds at runtime, and therefore, we could write new functionality for clearing the LCD display, but receiving the number of seconds we will wait. We copy these three lines we have here, and instead of this number 3 we see here, we will pass the number of seconds. In this way, we could invoke a function that waits for a default of 3 seconds, or a function where you specify the number of seconds to wait. Now that we have this new functionality, we can return to our greet method and specify that the amount of time it will wait before clearing the LCD is indicated by a parameter called time. With this, we can invoke the greet method, specifying the name, the line, and the amount of time. Let's test this new functionality. We return to our setup method, remove this pair of lines, and instead invoke the greet method, passing one name. We invoke the greet method, passing a second name, but also passing the line where we want to print this name. And we will invoke our third function, which receives as the last parameter the amount of time before clearing the display. This specification is an integer. For example, we will indicate that we want to wait for 10 seconds. Let's try our simulation. We have the first name, we have the second name, and we have the third name, which, as you notice, lasts 10 seconds before clearing the information on the display. Okay, there's the beep. As you have seen, it took longer than usual, since we specified that we wanted the duration to be 10 seconds. This is how we can overload our different methods to add functionality while ensuring that the methods we previously created remain fully functional. Let's talk about how we can connect different components to our Arduino. Specifically, let's discuss the inputs and outputs of Arduino. We can categorize them into two types, digital and analog. Let's start by discussing the digital inputs and outputs. If we review the documentation specifically for the Arduino Uno, we can read that we have 14 digital input-output pins, of which 6 are PWM output pins. We will discuss this definition of PWM later. You can find these pins in the section shown in the image on the right side of our Arduino. The numbering starts at 0, so even though the numbering goes up to 13, we actually have 14 digital input-output pins. Although it does not appear in the specifications table for the Arduino Uno, the pins marked with the label Analog In also have the same general purpose functionality as the pins on the right. This means we not only have 14 digital input-output pins, but we can also add the ones on the left to form a total of 20 pins of this type. Now, what does it mean for a pin to be digital? In summary, a digital signal can only have one value at a time, either a 0 or a 1. Translated to our Arduino, a 0 or a 1 corresponds to having 0 volts or 5 volts on one of the pins. This value is not exact. It can vary between 0 to 3 volts to represent a value of 0 and a range of 3.5 to 5 volts to represent a value of 1, approximately. In Arduino language, we have some keywords we can use to represent these values. The keyword LOW represents a value of 0, while the keyword high represents a value of 1. Remember this well, as we will use these words many times in our Arduino sketches. Let's analyze where these outputs are located and how we can interact with them. Imagine we have the following circuit. Don't pay too much attention to the components or how they are connected. Focus mainly on where the small bulb, or in the electronic world, the LED is connected. Note that it has a connection to one of the digital pins we mentioned earlier. Do you remember I mentioned that one of these pins can have a value of 0 or 1? Or in other words, a high or low value. Well, this is what happens if you apply a high value to the digital output. What happens here is that you would energize digital output number 8 with 5 volts, creating a potential difference. That is to say, at the output of pin number 8, we would have 5 volts, while at the pin marked with GND, where the circuit returns, we would have 0 volts. This causes the flow of current from one side to the other, which would turn the LED on. On the other hand, if we set the digital output of pin number 8 to low or 0, there would be no potential difference, so the LED would remain off. Let's move on to a demonstration of the concept of digital outputs. Okay, here we have a demonstration of digital outputs. We see that we have a simple circuit here, which is quite similar to what we saw in the slides. We have a wire that connects an LED. The LED is this small bulb we see here. We have a resistor. We'll talk more about the LED and resistor later. For now, focus only on this LED we see here. We mentioned that this LED is connected to pin number 8, and from the programming side, we will indicate what value this pin will have, whether it will be low or high. Let's go ahead and open the source code of our sketch, and we see that by default, pin digital 8 has a low value. Don't worry about the instructions we see here for now, we will review them later. Just focus on the fact that this is the pin number we are managing or controlling, and this is the value of that pin. In this case, we have a low value. If we start the simulation of our Arduino sketch, we see that the LED remains off as we have a low value on the digital output. However, if we change this value to high, notice what happens. We start the simulation, and this time we see the LED turning on successfully. This is how we can indicate what value a digital output will have. Also, remember that we said the high value represents a value of 1. Therefore, if we set the value to 1 directly, we can see that the LED also lights up. If we change the value to 0, which is equivalent to a low value, we see that the LED does not turn on anymore. This is how we can control a digital output. Let's now talk about digital inputs. Unlike digital outputs, which allow us to modify the value of a pin to affect an external component, a digital input lets us receive a value to work with in our Arduino sketch. The simplest example is using a push button. As I mentioned earlier, don't pay too much attention to the wires in our circuit. Little by little, you'll understand what each of them does. What I want you to see is that we have a button connected to pin number 4 and an LED. The idea of this circuit is to detect when the button is pressed and accordingly turn the LED on or off. The wiring configuration of our circuit will determine how we read the signal from the button. Let's see why. Broadly speaking, this is how our circuit functions when the button is not pressed. As you can see, I placed an arrow to indicate that while the button is not pressed, the current flows from pin number 4 to a pin marked with 5 volts. Since 5 volt represents a high value, as we discussed earlier, when the button is not pressed, our Arduino will read a high. I hope this doesn't confuse you, and if it does, don't worry, as we will cover this topic in more detail in a later lesson. On the other hand, when we press the button, the path closes, allowing the current to flow from pin number 4 to the pin marked with GND. As you may recall, GND is equivalent to 0 volts, so we can say that when the button is pressed, we will read a low value, which in our example will turn the LED off. As I mentioned earlier, this works this way due to how we wire the circuit. We could also set it up to function the other way around, meaning that when the button is pressed, a high value is read, and when released, a low value. Now, let's see a demonstration of digital inputs. We already have our example open here. As we can observe in our example, we have a LED and a push button. The idea of this circuit is that when we press this button, we can read the value of this push button on our Arduino. So based on this, we can turn this LED on or off. Let's start the simulation. As you can see immediately, the LED turns on. Why is this happening? This is happening because we are not pressing the push button we see here. Since we're not pressing this button, the circuit is not closing. We will discuss the push button component further later, but for now, you need to understand that as long as this button is not pressed, no energy will flow from the bottom part to the top part. Since no energy is passing through, this wiring is directing itself to where there is a connection, meaning it follows this route and reaches the pin marked with 5 volts. This is why, while we do not press this button, the LED remains on. This also relates to the programming. Basically, I'm saying in the code that as long as a high value, which is equal to 5 volt, is detected, this LED should turn on. If we press this push button, notice how our LED turns off, since completing the circuit causes the current to flow through this green wire, connecting to the top part, and continuing through the black wire to the pin marked with GND. Why is this happening? Basically, because current always chooses the easiest path. And in this case, since there is a resistor at the bottom, we will also discuss the concept of resistors later. The easiest path, without obstacles, is the one marked here. Then we press it, and the LED turns off. If we release it, the LED turns on. We've already talked about digital inputs and outputs. Now let's discuss PWM outputs and analog inputs. If we look at the documentation for the Arduino Uno, we won't actually find any direct reference to analog outputs on the Arduino. The truth is that Arduino does not have this type of output. However, we do have a type of pin that will allow us to simulate the behavior of an analog output. Let's review the table again. We see that there is a row that mentions 6 digital input and output pins, but they have special initials, PWM. What does PWM mean? Well, as a recap, an analog signal can have values between 0 and 5 volts, which means that if we had this type of signal, we could assign a value of 2.5 volts to one of the pins, for example. But we don't have them. We only have digital outputs, which, as we have already seen, can only be either 0 or 5 volts, in other words, low or high. Fortunately, we have PWM signals. What does this mean? Suppose we have an LED connected to one of the pins on the Arduino, and this graph shows with green lines a span of 1 second that marks the amount of time the LED has been on. This is what we would see when we assign a low or 0 value to the digital output. We don't see any activity, or in other words, the LED would be off the entire time. Now, suppose we assign a high or 1 value to the digital output for the LED. In this case, the LED would be on the entire time, in our example, for 5 consecutive seconds. Imagine if we could turn the LED on not for a full second, but only for a percentage of the time within that second. Since it is such a quick flash, in reality, this would not last a second, but rather a fraction of a second, giving us the impression that the LED is not fully lit, meaning it would appear dimmer to our eyes. Now imagine that we can turn on the LED for half a second of the total second, which means a workload of 50%. Would we have a dim glow? Well, this capability to operate a part of the duty cycle is called PWM, or pulse width modulation. This is what will allow us to simulate an analog output. To see it better, here we have a slow motion video of an LED with different percentages in the duty cycle. We can initially see clearly how the LED blinks. This happens because it is operating at a percentage of the duty cycle. However, gradually, we see that we stop noticing the blinking as the LED completes the duty cycle up to 100%. Now, let's analyze the topic of analog inputs. We do have this type of input on the Arduino boards. On the Arduino Uno, we specifically have 6 pins. Now, what is an analog input? These pins can receive a value between 0 and 5 volts. This means that we can manage ranges of values, not just zeros and ones, or low and high values, as we did with digital inputs and outputs. One of the components that allows us to handle these types of values is the potentiometer. We will look deeper into this component later, but you have likely worked with some type of knob that lets you vary a value. For example, volume knobs on speakers or knobs to adjust the flame on a stove, etc. The microcontroller on the board has a circuit inside called the analog to digital converter, or ADC, which reads the change in voltage and converts it into a number between 0 and 1023. This means that we can interpret this value and perform the necessary mapping to our Arduino components. For example, if we had 0 volts at the pin input, our board would read a value of 0. If we had a value of 2.5 volts at the pin input, our board would read an approximate value of 512. Finally, if we had a value of 5 volts at the pin input, the board would read a value of 1023, and so on. Let's look at a practical example of PWM outputs and analog inputs. Okay, we are now on our example webpage. As you can see, we have a circuit with an Arduino Uno, as shown here. First, let's identify which are the PWM outputs. We will recognize these outputs as part of our Arduino. Since they have this symbol we see here, we notice that pin number 11, pin number 10, pin number 9, as well as pin 6, pin 5, and pin 3 have this type of symbol, which means they are PWM digital pins. This indicates that we will be able to connect different components to simulate analog values. In this case, we have connected an LED, and the purpose of this example is to allow us to regulate the brightness of this LED according to our needs. This represents an example of a PWM output. On the other hand, in this section below, we see that we have this component, which is a potentiometer, essentially a knob that will allow us to slide it to assign a certain value. The idea is to combine both an analog input and a PWM output, which is from this LED. In this case, this knob will handle analog values, since, as you can see, we're connected to the pin labeled A5, indicating that it's an analog input pin. Let's see how this works when we start the simulation. Okay, notice how we have this LED turned on. Let's move the knob to the left. We have turned off the LED. As we move this knob to the right, notice how the brightness of our LED changes or increases since we are modifying the value of this potentiometer. If we position it all the way to the right, we see that the LED is at its maximum brightness. If we position it, for example, in the center, we have half brightness, and so on. So, to recap, we have here a PWM output that will allow us to simulate the variation in the percentage of voltage that reaches this LED. And we also have an analog reading from this potentiometer. If you want to test this circuit, remember that you will find a link to this project in the attached files for this class. In this lesson, we will learn in a simplified way what a class is, and we will do it in the simplest manner possible. We have previously seen that there are different data types, such as int, float, string, etc., and that we can use them individually to store information. Now, suppose each data type is an individual product, one you buy at any supermarket. For example, an int type could be a chicken leg, a float could be a pizza, and a string type could be an apple. Each product represents something individually. If we wanted to create a supermarket in the area, we would need to take several of these products and put them inside our store. With this, our supermarket would be, in the programming world, a new data type composed of several base types. But a store with products would be useless without daily activities. For example, we know that a store has activities like opening and closing the store, charging customers, and restocking a product when it is running low, etc. These activities, as we have already seen in a previous lesson, are called methods. So we can conclude that a class is a collection of data and methods to achieve a goal. In the world of Arduino, a class looks as follows. In blue, we can see the name of the class, which in our example would be something like store. In red are the data, which as you can see are actually variables, each with a defined data type. Finally, in yellow, we have a method. We could use this class in any new sketch we create, but for now, don't worry too much about the creation of classes. What I want to convey is that there are classes which are a special type of data that will allow us to access additional functionality beyond what is pre-established in Arduino. For example, serial is a class commonly used in the Arduino environment, and this class has a series of functions that will allow us to work through serial communication between the Arduino board and our computer. These are some of the methods available in the serial class, which we will explore in more detail in the next video. Now, let's see a practical demonstration of this class called serial. Well, let's watch a practical demonstration of this class named serial. Serial, as I mentioned earlier, is a class, and previously we talked about data types in Arduino. If we go to the Arduino code, you will remember that we can define different data types. For example, an integer data type, and assign a name to this variable, such as number 1. In this case, as I explained in the slides, there may be instances where you encounter data types that are different from those we have previously seen. In this case, the serial type is a very specific data type that will allow us to perform certain functionalities with our Arduino. This serial class is a special data type that contains pre-built functionality for us to access, and the specific class will enable communication between the Arduino board and our computer or other devices. This truly offers us a great advantage, since we can monitor, in a sense, what calculations our Arduino is executing, what information it has within this microcontroller, allowing us to see in real time what is happening inside it and whether it is functioning correctly or not. The way we will access this information stored in our Arduino is through the console or serial monitor. In the case of Tinkercad, we have this serial monitor at the bottom labeled Serial Monitor. If we expand it, we see that a new window appears, allowing us to receive information from the Arduino in this box, as well as send information in this field. In the Arduino IDE, we have our IDE, and on the right side, there's a magnifying glass icon that when hovered over, indicates Serial Monitor. If we click it, remember that the Arduino needs to be connected to our computer for it to function properly. Otherwise, you'll encounter an error. By pressing this button, we open the serial monitor. This section we see here is where we will receive information from the Arduino, and in this text box, we will be able to send information to the Arduino. This console here acts as the link between the PC and the Arduino. To establish this communication, we also need to understand a concept called data rate or baud rate. This data rate is specified in bits per second of transmission, also known as baud. If we look at the bottom, we see a series of drop-down options. The one we are interested in is the one that says 9600 baud. This value of 9600 is the default or standard transmission rate between our computer and the Arduino. If we expand it, we see many additional values that we can configure, but for our demonstrations, we will use this value of 9600 baud. Let's close this monitor, minimize our Arduino, and return to Tinkercad. Okay, to access this serial monitor, we will use the class we discussed earlier, which is the serial class. We have all the necessary documentation as part of the Arduino reference. Here we have the serial class, and we can see its description. At the bottom, there is a section called Functions, which lists the available functions that we can use as part of this class. At the moment, we are primarily interested in two. This functionality called begin and the print method. Let's look at the first method. This method is called begin, and what it allows us to do is essentially open the communication between the PC and our Arduino. Therefore, it is a very important method if we want to use the console to transmit and receive information from the board. Here we have the basic syntax for this method. Notice that we first need to call the name of the class, followed by a dot, and then the name of the method we are invoking, which in this case is begin, with the transmission speed between our PC and the Arduino in parentheses. Remember that this default value is 9,600. Let's see this in practice. Let's return to Tinkercad, and here in the setup method, we will call the serial class, followed by a dot, and the invocation of the method called begin. Remember to place the parentheses and the semicolon. Inside the parentheses, remember to enter the transmission speed, which will be equal to 9,600. If we start the simulation at this moment, we see that there are no issues as the code is correct. Now, let's see how we can print information as part of the monitor. Let's go back to the Arduino reference and specifically look at how we can use this print method. Essentially, this print method describes how we can print information to the serial port as human-readable text. Here we have some print examples. For instance, if we print the number 78, it will output the same number. And this works basically with any text shown here. This method goes a bit further, as it also allows us to perform conversions between different bases. For example, if we write the number 78 and add a second parameter with these characters we see here, it will return this number in its binary base, which is the representation we see here. As part of the documentation, we have the different available bases and what happens if you write a number along with a second parameter. At this moment, we are only interested in writing information as text strings. Therefore, we will guide ourselves by this first section we have here, and we'll see how to print a text string as part of the serial monitor. Let's return to Tinkercad, go back to the setup method, and imagine that we want to print a string. We will invoke the serial class and call the method named print. I will print, for example, the name Hector. Remember to add the parentheses and the semicolon. If we start the simulation now, we can see that indeed in the serial monitor, we have the name Hector. Let's click on this button that says clear to erase the information from the serial monitor. Let's stop the simulation, and suppose we want to write hello Hector on two separate lines. We will proceed to copy this first line and paste it below. Okay, then we change this first string to hello, and we'll keep Hector on the second line. We start the simulation to see what gets printed, and notice that we have the entire string printed all together. As part of this chain, we can also add spaces. For example, we could add hello space Hector. We will clear the monitor's content, restart the simulation, and here we have the output hello space Hector. If we want to print this string on a second line at some point, we would need to use a different method called println, which we have here. This method essentially adds a carriage return or a new line at the end of the string from the moment println is executed. Therefore, if we return to the Tinkercad program, instead of using print, we write println. Let's start the simulation. Notice that this time it is printing hello, followed by a line break, and on the second line, the name Hector. Remember, this text is printed only once, since, as you may recall, the setup method runs only once. If we copy or cut these lines and paste them into our loop method, let's see what happens. We see that this set of words is printed repeatedly as part of our loop method. So, this serial class is a powerful class that allows us to obtain information from our Arduino in real time, and we will use it frequently in our projects to ensure the calculations are executed correctly on our Arduino. One of the great advantages is that we will no longer need to connect an LCD display to show information. Instead, with our serial class, we can quickly and easily print different information. Now, let's talk about the component called LED, which actually stands for light emitting diode. In simple terms, it is a semiconductor device that emits light when an electric current passes through it. This is what an LED typically looks like. We see that it has only two leads, and usually one is larger than the other. The larger lead, which corresponds to the positive side, is called the anode, while the shorter lead, which corresponds to the negative side, is called the cathode. In electronics, each component has a symbol which allows us to represent the component in an electronic diagram. In the case of the LED, the figure we see on the screen is the symbol of a diode. This symbol not only serves to provide a visually appealing representation of the component in a diagram, but it also indicates a couple of interesting things. First, the arrows marked in the red circle indicate that this is an LED, as there is also a component called a diode that does not emit light. We will discuss it later. The second thing we can see in the symbol is an arrow. In a diode, whether normal or an LED, the current can only flow in one direction, from the anode to the cathode, which makes it crucial to connect the diode in the correct orientation. Here we see an example of the component called LED. Okay, we are back in Tinkercad to see a real demonstration of how a component called LED works. We're going to create a couple of quite simple circuits that will help us understand how an LED component works. First, let's look for a 1.5 volt battery in our list of components, and we'll also search for another component found in the list of all, which is this component called a light bulb, which is just a regular light bulb. Okay, we now have our light bulb, and notice that on the terminals of the bulb, we have terminal 1 and terminal 2, while on the battery we have a negative and a positive. We will proceed to connect these leads together. We will press on this lead marked negative, and we will position it on terminal 1. We will do the same with the positive lead, dragging it to terminal 2. What do you think will happen if we start the simulation right now? Let's find out. We start the simulation, and the bulb lights up. Let's stop the simulation and change the wires. We will remove these wires because we're going to cross them, meaning we will connect this negative wire or negative lead to terminal 2 of the bulb, and we'll connect the positive side of our battery to terminal 1. What do you think will happen now? Let's find out. We start the simulation and we see that our bulb lights up in the same way. We'll do the same exercise, but now with a component called LED, which we saw in the slides. So let's filter the basic components. We will look for a 1.5 volt battery again, and we will proceed to find a component called LED, and we will drag it into our diagram. The color doesn't really matter. What we care about is that it is an LED component. We will do the same exercise, meaning we will first connect the negative leads to the lead marked cathode, and we will connect the positive side to the anode. And let's see what happens. Okay, you can see that our LED is already lighting up a bit. Let's stop the simulation and proceed to swap these wires. We'll remove this wire and this wire, connecting the negative pole to the part called anode and the positive side to the part called cathode. What do you think will happen? Let's start the simulation. Notice that this time, our LED did not light up. Why isn't it lighting up? It's due to how a diode works. Here I have opened a program called FreeSync, which allows us to visualize schematics and create different electronic diagrams. Don't worry too much about this right now. What I've mainly done is place an electronic diagram showing how the two connections we made earlier with our LED appear. First, we have the connection we made initially, meaning when we connected the negative pole of the battery to the cathode, and also the positive pole of the battery to the anode. This is how the diagram looks. What we see here is the representation of the battery, and this part represents the diode. The top part of the battery represents the positive pole, and the bottom part represents the negative pole. What's happening in our circuit is that energy flows out from the positive side. Notice how our diode has this arrow shape indicating that energy will flow from top to bottom. This is why the energy flows correctly and lights up the LED. On the other hand, the second diagram we see here represents the second connection we made. In this case, energy will try to pass through, but when it encounters this wall, so to speak, or meets resistance against the operation of the diode, energy no longer flows. Therefore, this LED does not energize and does not light up. That's why it is crucial to connect your LEDs correctly. Now that we know about the component called LED, you may be surprised to learn that our Arduino board has a built-in LED by default. I will drag an Arduino component into our diagram that we see here. I will look for our Arduino Uno component, drag it, and notice that as part of the components of our Arduino, we have this little light with an L, which stands for LED. If we look for a picture of an Arduino, we see that we have exactly the same visualization. We have two lights, one called TX and another called RX. And at the top, we have the LED that is directly connected to pin number 13. Let's explore some additional methods that will allow us to conduct different tests with the internal LED of our Arduino. This will function the same way as if you connect your Arduino and write the same code that I will write in your Arduino IDE. The first method we will look at is one that will allow us to specify whether one of the digital pins of our Arduino will be configured as an input or an output pin. We already saw this in some previous slides. We need to control and specify how the pin will behave. Let's go to the code of our Arduino. We will select that we want a text code. We will remove this pre-created code that we see here. Inside the setup method, we will learn about a new method called pin mode. Note that we have the word pin in lowercase, and this second word, mode, starts with an uppercase letter. We place the parentheses and the semicolon, and with this method, we will be able to specify whether one of the digital pins will be an input or an output. This method receives two parameters. First, the first parameter is the pin we are going to configure. In this case, remember that this LED we have here is directly connected to pin number 13. So let's pass the number 13 as the first parameter, which corresponds to digital pin number 13. We insert a comma to specify the second parameter. We have two values that we can assign here that are of interest to us. The first one is called input. By writing this configuration, we indicate that this pin will be set up as a digital input pin. If we want to specify that this pin will be an output pin, we need to write output. Note that this word, or these words that we have seen, must be in uppercase. If we write them in lowercase, it will not work. In our practical example, since we want to change the voltage configuration of this pin to indicate whether an LED is on or off, we will set the pin mode of pin number 13 as output. Once we have specified whether the pin will be a digital input or output, we can begin working with this pin according to its configuration as either output or input. In our case, since it is configured as an output, we can modify whether there will be a voltage present at the output or on the Arduino pin. How can we specify this value? Well, you should know the method called digital write. We will also write this within the setup method. So let's write digital write. Notice how this method is written. Digital is in lowercase and write begins with an uppercase letter. This name is quite descriptive as it indicates that we will be able to write to a digital pin and set it to either a low value or a high value, which are the two possible states of a digital signal. To carry out this action, we need to specify two parameters. First, we need to determine which pin we wish to modify. In our example, since we want to affect pin number 13, we will write the value 13. Next, we will specify the value of that pin, whether it will have voltage or not. There are two possible values, low to indicate that it will have 0 volts, or high to indicate that it will be energized and have 5 volts at the output. Let's add the missing parenthesis and semicolon, and in our sketch, we have indicated that our pin will indeed be energized by default. Let's start the simulation to see what happens. Notice that our Arduino has successfully lit this LED. To show you that I'm not lying, let's change this value to low. Remember to write it in uppercase. Let's start the simulation. And notice that this time our LED did not light up. In this current example, if we want to modify the output of our pin, we need to stop the execution of our simulation and change this value. This seems rather dull. Something more interesting would be if we could turn the LED on and off by default. How can we achieve this action? Well, we'll cut this instruction where we indicate the state of our LED and move it to the loop method. Remember that this loop will be executing many times in 1 second. So we will indicate that we want to turn off the LED, but before turning it off, we need to turn it on. Therefore, I'm going to copy this line, paste it in a new line, and indicate that I want to turn on the LED first. Theoretically, this will turn on our LED and then turn it off indefinitely. Let's see if this works correctly. Let's start the simulation. Even though we have this pair of instructions that seem correct, our LED appears to be on all the time. Well, this is happening because remember that the execution of the loop method occurs many times in 1 second. To solve this issue, let's get to know a new method called delay. Delay in Spanish means something like wait, and it basically allows us to wait a certain amount of time between one instruction and the next. So we will indicate that once we have turned on the LED, we want to wait a certain amount of time. Let's see how to write this instruction. We'll write it like this. The word is delay, as we see here. This instruction or functionality expects a parameter, which is the waiting time in milliseconds. 1 second has 1,000 milliseconds, so calculate how many seconds you want to wait. In our example, we will wait only 3 seconds, so we will write the number 3,000. With this new instruction, we will indicate that our LED should turn on for 3 seconds and then turn off. However, if we do this, notice that once we return to the beginning of the loop cycle, the LED will turn on again. Therefore, we need to specify that we also want a delay after the LED turns off. Let's write another delay instruction after this line, and we will specify that we want to wait for 3 seconds as well. With this change we made, let's see what happens in our circuit. Let's start the simulation. Notice that our LED turns on for 3 seconds, then turns off for 3 seconds, and after 3 seconds, the LED turns on again. This runs repeatedly and indefinitely, as specified in our loop method. We have seen a series of instructions that will allow us to energize or not energize a pin on our digital Arduino. A more interesting aspect would be to integrate an LED component into our project so that we can see our LED turning on and off here. Let's see how to do this. We'll go to the Components section and drag our LED component. Okay, remember that this integrated LED is directly connected to pin number 13. Therefore, we will also connect this LED we have here to pin number 13, so we won't have to change the code, although you are free to do so if you wish. Let's take the cathode, which as a reminder is the negative part, and connect it to a special pin called GND. GND means ground, so the negative part is correctly connected to this pin. You may notice that your board has more than one GND pin available. It'd be perfectly fine to connect the LED cathode to any of these connections we see here. On the other hand, we will connect the anode to pin number 13. Okay, we can see that it is connected successfully. Let's see what happens when we start the simulation. Okay, and notice that our LED has turned on successfully, but there is a warning here. Let's stop the simulation and give a bit more time to this delay so we can read what's happening as part of our circuit. Let's set it to, for example, 15 seconds. Let's start the simulation. Let's read the message. The message states that the current through the LED is 52.3 milliamperes, while the maximum recommended value is 20 milliamp, and this could reduce the lifespan of the LED. What does this error message indicate? Well, it basically means that too much current is reaching our LED and it could potentially get damaged. What can we do to solve this issue? Well, we will explore this in the next video. To correct our project, we first need to understand what Ohm's law is, which is a basic principle of electrical circuits. With it, we can determine the relationship between potential difference or voltage, current, and resistance in an electrical circuit. However, to fully understand this law, we need to know what each of these concepts means. This image represents the three concepts of voltage, resistance, and current quite well. By the end of this lesson, you will see how you can understand the image perfectly. Let's first talk about voltage. Voltage is the amount of potential energy between 2 points in a circuit. Okay, that's a nice definition, but what does it really mean? To better understand this concept, take a close look at this image. You can notice that there is a height difference between the highest point of the waterfall and where the water falls. In this waterfall, and in any other, water flows from the highest point to the lowest point, thanks to gravity. This principle applies not only to massive waterfalls, but to practically any flow of water we know of. We can use this analogy to explain voltage. In an electrical circuit, electricity travels from a point of high electrical potential to a point of lower electrical potential. In the example of the illustration, current flows from the output of a battery marked with 5 volts to the point marked with 0 volts, as it is between these 2 points that the potential difference or voltage exists. This would allow us to turn on a small light bulb located between both points. Now, suppose the battery is completely out of energy. In this case, since both sides of the battery would have 0 volts, there would be no potential difference, and therefore the bulb would not light up. Let's now talk about current. Look at this image of this river. Now, let's see this image that shows a smaller flow of water. Which one do you think carries more water? That's right, the first photograph. You might ask me, what does this have to do with electric current? Well, in electronics, there's a very similar phenomenon. Instead of water flowing, electrons flow. Instead of water flows, there are cables or materials of different dimensions that allow these electrons to pass through. How is this flow of electrons produced? We know that an atom is made up of protons, neutrons, and electrons. Electrons are particles with a negative charge which are attracted to the positive charges of other atoms. In other words, at certain moments, they jump from one atom to another due to this attraction. These jumps are what create electric current. Current can then be defined as the amount of electrons passing a specific point in 1 second. Imagine for a moment if we could count each electron passing through a circuit at a point. The truth is, there would be an enormous number of them. That's why a unit called ampere was invented. To give you an idea, 1 ampere is equivalent to 6.5 trillion electrons. By connecting the concept of voltage with current, we can arrive at the definition that voltage is the force that moves a set of electrons. Therefore, the higher the voltage, the more current we will have in our circuit, or in other words, the more electrons we will move. Finally, let's talk about electrical resistance. This term refers to the opposition that electrons face when moving through a conductor. There are materials that will offer less resistance to their passage through a circuit, such as gold or almost any metallic material. On the contrary, there are materials that will offer greater resistance, such as plastics. In our electrical circuits, the way to create resistance in a circuit will be through electrical resistors. You may wonder, why would we want to create resistance in a circuit? Well, it's how we can control voltage and current in our projects. The unit of measurement for electrical resistance is called ohm, represented by the symbol we see on the screen. On the other hand, These are the symbols we can find to represent an electrical resistor in an electronic circuit. We see that below the symbol, there is a specified value followed by the ohm symbol. This means that in this specific case, the resistance has a value of 330 ohms. How can we know that the resistance has that value? There is a color code that will allow us to identify the value of the resistor. Usually these resistors will have 4 color bands. We can compare the colors of the bands with this color chart we see on the screen. This is a standardized chart, so any chart of this type will serve the same purpose. Let's do an example with the resistor in the image. Let's find the value of the first band, which is the number 6. Now, let's find the value of the second band, which is a red color with the value 2. As for the third band, which is a multiplier band, we have a green color. This means we will take the number 6 and the number 2, which is 62, and multiply it by 100,000. This gives us a value of 6,200,000 ohms. Typically, the resistors we use will have values well below this calculation we have made. Having analyzed each of the terms, this image should now even seem amusing, and you can surely interpret it without any difficulty. Returning to the original image, how will all this we've seen be helpful? Well, now that we understand the concepts that make up Ohm's law, we can see how to calculate different values, so that, for example, our LED connected in the previous activity does not risk burning out. Let's analyze our circuit. What values do we have at the moment? Well, remember that each output of our Arduino has a voltage output of 5 volts, so we have the voltage, although there is one caveat about this voltage. The caveat is that our LED also needs to consume power to turn on. But how much voltage do we need to inject for the best possible brightness? Fortunately, there are tables that provide approximate values of the voltage required for the LED to light up at its maximum capacity without risking damage. We will use this table shown on the screen. Let's take the value of 1.9 for our calculations. What we will do is subtract the initial voltage from the voltage we need to turn on the LED. Do we have any other data that will allow us to know the value of the resistor? Yes, we do. If you remember when we started the project of connecting the LED directly to the Arduino, we had a message with a black background. If we read carefully, we can see that the recommended maximum current is 20 milliamperes. This is a standard value for normal LEDs. So whenever you do calculations, you should use the value of 20 milliamperes for LEDs, which is 0.02A. Thanks to Ohm's law formula, we know that we want to calculate the resistance needed for our circuit. So we use the formula, resistance equals voltage divided by current. The result is 155 ohms. With this data, we can refer to a table of common resistors and find some resistor values close to the one we've obtained. When you go to your electronics store, it is almost certain that they will tell you they don't have several of them. So it is important to always know about different values that we could use in our circuit. Let's do another example. This time, let's assume we know the voltage and want to use a 2 ohm resistor just to see what would happen. Since we want to calculate the current, we will take the one from the bottom right. Current is equal to voltage divided by resistance. Calculating this, we find that the result is 1.55 amperes, which is a tremendous amount for our LED that can support a maximum of 20 milliamperes. This is something similar to what is happening in our circuit without resistors currently. Let's do another exercise, but this time, let's suppose we do not know the voltage, but we do know that the resistance we want to use is 220 ohms and that the LED's current is 0.02 amperes. We will use the formula from above, which states that voltage is equal to current times resistance. With the data we have, this will give us a total of 4.4 volts. With this new knowledge, let's proceed to correct our circuit with our LED. We are back in Tinkercad. Let's recall what we did last time. We placed an LED, in this case, a red one, and connected the cathode to the pin marked GAND and the anode to the pin marked with the number 13. What we'll proceed to do now is to add a resistor to our circuit to avoid the error we encountered previously. Let's look for the component called resistor in our list and drag a resistor into our circuit. Okay, here we have it. If we hover over this resistor, we can assign a value to it. If we change the value to, for example, 25, notice how the colors of the bands change to match the calculation with the value we are entering. We also have different units of measurement, such as kiloohms, ohms, and many more. In our case, we are interested in keeping this unit as ohms, and remember that the result of the calculation we applied was equal to 155 ohms. In the resistor table, we also saw that the closest value for this resistor is 150 ohms. So let's indicate that we want a 150 ohm resistor and how we will integrate this resistor into our circuit. Well, in our example, we can remove either of the two wires we see here. Let's remove, for example, this connection to the anode, and we will connect the anode directly to one terminal of the resistor. A resistor has no polarity. This means that you can connect your component to either of the two terminals and there won't be any problem. The next step is to connect terminal 1 of the resistor to the Arduino pin we are interested in, which is pin number 13. You can also apply some color to the wires for better visibility or to distinguish different sections of your diagram. For example, we can place this wire in black and the second wire in green without any problem. We are starting the simulation now to see what happens. Notice that this time we no longer have the message or problem that we had before. Now we have a LED that is lighting up correctly and poses no risk of malfunctioning. Notice that after the set time, the LED turns off and then lights up again. Let's leave this sketch as it was. In other words, we will set a delay of 3 seconds, start the simulation, and now we have a LED that turns on and off every 3 seconds. With this, I have to congratulate you, as this is the equivalent of the first hello world in the programming world. Congratulations! You now have your first electronic circuit functioning correctly and without the risk of burning out. To conclude this section, I would like to note a couple of additional points. First, as you may remember, as part of the code in our sketch, we specified, for example, in this digital write instruction, the number 13, which corresponds to the Arduino pin we want to energize or not, and later we set a high or low value. If you saw the slides where we discussed digital signals, you may recall that this high value is equivalent to the number 1, and the low value is equivalent to 0. Therefore, it would be entirely correct to specify a number 1 here instead of high, and a number 0 instead of LOW. I want to emphasize this as if at any point you see sample code in any forums or online tutorials, and you encounter this nomenclature, it shouldn't confuse you, and you should be able to understand it perfectly. On the other hand, in some forums or online tutorials, you might see that instead of using digital write and a value of 13, they use syntax like this, digital write, and instead of 13, let built in. What we see here is a special type of variable used to pre-specify certain values. In this specific case for the Arduino Uno, this value refers to the pin to which our built-in LED is connected by default, which as you recall is pin number 13. This value for the built-in LED doesn't have to be 13 on all Arduino boards, as different Arduino boards may have LEDs connected directly to other pins on the boards. In our specific case, let built-in does reference pin number 13. Therefore, I could copy this code and paste it instead of the number 13 that we have assigned directly. We start the simulation and notice how our circuit continues to function satisfactorily and without any issues. Let's stop the simulation, and I want to emphasize another point. We previously saw the use of variables as part of our sketch. Can we use variables in this sketch? The truth is yes, and it is recommended to use them. Earlier, we had this code where we assigned pin number 13. And as you could observe, when we wanted to change 13 to LED built in, we had to change each instance individually, even though this is a very small program. Imagine you have a longer sketch with dozens of lines of code. If you wanted to perform a replacement this way, you would have to make a change in each of the lines. Let's see how to simplify this using variables. I will position myself above the void setup, and we're going to specify a constant, since we actually do not want this pin number or value to change during the execution of our sketch. So let's write the word const, and we will indicate that we want to declare an integer type variable called, for example, letPin, and that it is equal to the value number 13. Let's copy this value letPin. We will change it in every place where we have the number 13. Let's test our sketch to see if it continues to work correctly. It still functions. And what is the advantage? We've introduced a variable into our sketch. Well, if for some reason we wanted to change the anode of our LED to any other pin on our board, we would simply need to change this constant value to, for example, number 12, and automatically apply the change throughout the entire sketch. If we start the simulation at this moment, we see that our circuit is no longer functioning, as the pin specified for the sketch actions is indicated by pin number 13. Let's change it back to the value we had, assigning LED pin to number 13. Finally, you might be wondering, what happens if we assign a different value to our resistor than the one we have at the moment? Well, this will greatly depend on the value you assign to the resistor. If you assign a very low value, for example, 5 ohms, and we start the simulation, it will behave the same as it did at the beginning of our practice. We have this error message indicating that we have a very high current and that our diode or LED could burn out. Let's begin this section by analyzing the component called protoboard or breadboard. This component, which could be translated as a test board, will allow us to develop rapid prototypes of projects or test parts of a circuit that make up a larger project. If we were to look inside the protoboard from the previous image, we would likely see something like the following: a series of tracks that will allow us to connect our electronic components. We can see that on the outer areas of the protoboard, we have a pair of rails that run horizontally. This pair of rails is used for circuit continuity, and as you can see in the image, the red rail is used as the power rail, while the blue rail serves as the ground or negative rail. These rails will allow us to easily connect to the power supply from any point on the protoboard, since as you can see in the image, the entire rail will be energized once we connect the power supply. On the other hand, in the center of the protoboard, we also have smaller extension rails. This area is called the circuit area. This is where we will connect our electronic components, such as LEDs, sensors, potentiometers, etc. Unlike the outer rails, these mini rails are connected vertically, so you need to be careful about how you connect your components. We can remove the cover of the protoboard to examine it more closely. This is how the rails I mentioned earlier are composed. If we want to take it a step further, we can extract one of the circuit rails as shown in the image. This is what the rail looks like. As we can see, everything is connected and has a type of clip that will allow us to grip the component. Here we see an example of this. The component can be any that we can insert into these rails. There are even some protoboards that are made of clear plastic, allowing us to see these clips directly. Lastly, let's talk about the sizes. Here we have the standard size, which is arguably one of the most used sizes, as its dimensions allow us to create circuits ranging from simple to more complex. With this type of protoboard, let's be careful since some versions have a discontinuity in the rails in the middle of the board, which could be resolved by placing some type of jumper or small wire between both sections to ensure a connection across the entire board. Another size is the medium protoboard, which is half the size of the large protoboard, with 30 rows and a total of 400 connection points. Some people prefer these over the standard size. There's also the tiny version for creating very small prototypes. However, unlike its larger counterparts, this protoboard does not have power rails. Incredible as it may seem, There are also micro versions with 4x4, 2x8, and 2x4 terminals for simpler configurations. Finally, there's the large version for really big projects, with an impressive total of 2,250 connection points, equivalent to 3 standard-sized protoboards. With what we've learned, let's head to Tinkercad to play around with the protoboard. We are now in Tinkercad, and we will first examine the different sizes of protoboards available as part of our simulation tool, which you can easily find physically. Here, if you search for the word tests, as you can see, we have different components that will allow us to insert these types of testing board components. First, we have a small breadboard, which is this one here. We also have other examples like the standard breadboard. We can drag it onto our circuit and see that it's larger than the board we have on top. We also have this mini breadboard. In the physical world, there are other boards that are either larger or smaller, but the ones we have here are the most commonly used in real life. The advantage of this simulator is that it shows us in real time where the different rails of each protoboard are located. For example, notice that if we position ourselves over one of the outer rails, it automatically highlights, marked in green, which rail corresponds to each pin. If we go to the red rail, we also see this green marker that indicates where the connection starts and ends for this line or rail that we see here. This means that if you connect something at one of these points here, in this case a power outlet, the power will be available along the entire rail we see here. The same happens with the lower rails. As we can observe, we have the same behavior. The only difference is that the bottom part is not connected to the top part. If you want to power both the upper and lower parts, you would need to connect a power outlet to both sections, unless you connect this rail we see here with the lower rail and the upper positive rail with the lower positive rail as well. We will look at this a bit later. In the center, we have different mini rails marked with different numbers. And as you can see, each of their ranges is smaller. In fact, there are only 5 points available for a connection. In the case of this protoboard, we can see that we have 30 columns available for making connections and 10 rows available for carrying out different connections. We can see that all the protoboards work in the same way. In this protoboard we have here, which is larger, we have exactly the same behavior, with the only difference being the size. Here we see that in the normal protoboard, we have more points available for connecting our components. But we also have this negative connection area in this positive area. In the smaller protoboard, we do not have these positive and negative connection rails. We only have these internal connection points. If we wanted to connect the two sections, both the upper section we have here for the components and the lower section, we could do so using a jumper wire or some other type of wire. For example, you can take a piece of UTP cable, extract the different wires that compose this network cable, and use each of them to make connections in the protoboard. In the case of the simulator, we can make this connection by clicking on one of the available points. When we click, notice that a line appears, which represents a wire. So if we press on one of the other points available on the protoboard, notice that a connection is created between this line here and that other line. What this means is that we would have a connection from this line number 6 to line number 18. This column that we have here will be connected to this other column. We can select the creation of this wire and delete it using the delete key. As I mentioned earlier, if we wanted to connect these two sections we have here, it would simply be enough to create a line, and with that, we would have a connection throughout the column. Let's conduct another test. We will remove this filter from the components, and instead, we will look for a 1.5 volt battery. We drag it onto our diagram. Once our battery is ready in the diagram, we will proceed to connect this positive pin to our protoboard on its positive line. With this, we will be supplying the entire line with a positive pole. We will perform the same action with the negative pole. We will drag a wire and drop it on the negative line or rail. We can position the wires for better visibility, and we can also select a color for the wire. For example, we can mark this wire with black for the negative, another wire for the positive with red, to follow a standard nomenclature. With this, when we start the simulation, we will be energizing our upper rail with the battery we have added. Let's see if this is true. We will look for our LED component, drag it onto our diagram, rotate it, and once we have it like this, remember that this is the cathode and this is the anode. Therefore, we can position it like this on our protoboard. As you may have noticed, our components align or fit perfectly at each of these points we have here. If we restart the simulation, notice that our LED is already lit. So with this, we can demonstrate that this line and the line we have here are connected. As I mentioned earlier, if we drag another LED, rotate it quickly, and position it at the bottom, then start the simulation, the upper LED lights up, but the lower LED does not. What could we do to connect these rails at the top and those at the bottom? We would simply create a new wire, or simulate a new wire, creating this connection, and then create another connection with the upper rail. Okay, if we start the simulation now, notice that both LEDs are on. As I mentioned earlier, you need to be careful about how you place your components. If you drag an LED onto the inner rails we have here, it will be incorrectly connected because we are connecting both the cathode and the anode on the same row. For example, if we wanted to power this rail with the positive terminal, we would be introducing the positive side to both the cathode and the anode, which is incorrect. What we need to do is rearrange our LED so that each pin of this LED occupies a different rail. This way, we can transmit power from one line to another and connect in this line, for example, to the negative side. If we do this and start the simulation, we see that our LED does not turn on here because this wire needs to go to the positive part and this one to the negative part. Remember, this is the anode and this is the cathode. If we start the simulation, we have our 3 LEDs successfully lit. To continue practicing with our protoboard, we will replicate the LED project, but now on a protoboard. If you remember, earlier we created a project in which we connected an LED directly to our Arduino. This time, we will recreate the same project, but now with a protoboard. Let's search for our Arduino development board in our list of components. We'll drag and drop it. We will also drag a protoboard component. We will use this small protoboard. Okay. Now let's find the LED component and insert it into our protoboard. Notice how easy it is to insert one of these components into our protoboard, which helps us maintain better organization in our project. As you can recall, we also need a resistor, so let's drag the resistor, assign it a value of 220 ohms, and rotate it. Remember that we need to insert the resistor into the anode leg, since we want to connect the resistor to our anode, and then to terminal 2 of the resistor, which goes to our Arduino board. We have this connection. We come from the anode to terminal 1, pass to another column, and here we can connect to our Arduino. Let's create a connection with pin number 13. And remember, we connect the cathode to the negative side of our Arduino. Therefore, we can connect directly to any of the pins marked with GND or ground. Let's color this wire black, and now we have our project recreated. I will proceed to open the code window. We will specify that we want to code with text, and I will replace this code with the code we created earlier. Let's initiate the simulation to see how our project behaves, and notice that we have a project that is successfully turning on our LED at specific intervals. With this, we have integrated a protoboard into our Arduino-based project. We have already learned how to connect components within this breadboard to create quick prototypes. Let's get to know the component called photoresistor, light-dependent resistor, or LDR. This component is a special type of resistor that depends on the light it receives. As we have seen earlier, the resistor component allows us to reduce the amount of current flowing through a circuit. A variable resistor, unlike a normal resistor, varies the resistance depending on some type of condition. In the case of the photoresistor, this condition is light, which causes the resistance to vary based on the amount of light it receives. A photoresistor is made of semiconductor material. To recall, conductive materials allow nearly free passage of electrons through the material, while insulators are those that restrict the flow of electrons. A semiconductor material falls in between these two categories. In a semiconductor material, electrons have variable energy levels and are organized so that those with similar energy levels are close to each other. These levels are called energy bands, which we can categorize into two types, the conduction band and the valence band. The valence band is the level with the lowest energy, where electrons move with less freedom. In contrast, the conduction band has the highest energy and allows for freer movement of electrons. Between both bands, there's an energy gap. Now, the resistance of the semiconductor depends on the number of electrons available in the conduction band. When light strikes the surface of the photoresistor, it excites the electrons in the valence band, increasing their energy levels and allowing them to cross the energy gap into the conduction band. Since there are more electrons available to conduct electricity, the resistance of the photoresistor tends to decrease. We will see an example of this later. Putting theory aside, each photoresistor will behave slightly differently from others, even if they are from the same batch. Therefore, they should not be used to determine exact light levels, but rather for basic light changes. Some projects where this component could be used include determining whether there is light or darkness in a room, or when we want to know if there is something in front of the photoresistor that might block the light. Let's go to Tinkercad and see a photoresistor in action. Okay, we are now in Tinkercad. And in the Components section of Tinkercad, we can see the specific component we have been discussing, which is the photoresistor. Let's drag one of these components into our diagram, and we will also look for a tool called a multimeter, which we have here. This multimeter tool will help us measure the resistance of the photoresistor very easily. What we will do next is connect the negative and positive leads of our multimeter to our photoresistor. As you can see, our photoresistor is not polarized, meaning we can connect either of these leads to our photoresistor. Let's go ahead and do this. We will connect the negative lead to terminal 1 and the positive lead to terminal 2. Let's change these colors for better visibility. Once we've done this, let's start the simulation in Tinkercad. We'll make a change to visualize the resistance in our circuit. We do this by clicking on this circle with an R in the center. As you can see here, it displays the current resistance of our photoresistor. If we click on our photoresistor, we see a drawing that allows us to simulate how much light is reaching the photoresistor. At this moment, we are simulating total darkness. This results in a higher resistance level. Meanwhile, if we move this slider to the right, it simulates that more light is reaching our photoresistor, and you can see how the resistance gradually decreases. If we do the opposite and slide it to the left, watch how the resistance increases again. Basically, this is how the photoresistor works. The more light it receives, the less resistance we will have, and the less light it receives, the greater the resistance will be. To continue our project, we need to understand a method that we haven't seen until now. This method is called analog read, and basically it will allow us to read an analog pin to get values between 0 and 1023 from one of the analog pins on our Arduino. If you remember, on our digital pins, we can only read high and low values. However, as you may have noticed, our resistor has a range of values that are neither high nor low, but rather a series of numbers that can vary depending on how much light is hitting our photoresistor. Let's see how to use this method, starting by assembling our project. We will use the project we have already created, and we will proceed to drag a small breadboard onto our diagram. We will also proceed to drag an Arduino Uno board. We will position it like this. On our breadboard, we will drag a second component, which is a photoresistor. Here it is. We will place our photoresistor on the breadboard like this. Next, we will energize our photoresistor. We will indicate that we want to connect terminal 1 directly to the negative rail of the breadboard. We will color this wire red and proceed to connect our terminal 2 directly to one of the analog inputs of our Arduino. It can be any of these. In my case, I will use input A0. Therefore, I will create a connection between terminal 2 and V0 on my Arduino. Okay, that's all we need for our project at the moment. Let's go to the code section. We'll indicate that we want text instead of blocks. We'll remove the contents of our setup method and the loop method. What we will do after carrying out this action is specify a constant for our Arduino pin corresponding to our analog input number 0. Let's declare a constant. Remember that the variables representing pins are integers, and we will call it, for example, photo, for photoresistor. It will be equal to, and here we need to use a special nomenclature for the Arduino analog pins. To access these analog pins, we need to write the letter A in uppercase, followed by the number of the analog pin. In this case, it is pin A0, as it appears on our Arduino board. We place the semicolon, and with this, we ensure that we are directly obtaining the pin number from our pin A0. If we wanted to see the value of this pin, we could initialize our serial monitor through serial.begin. Remember that we initialize it with 9600, and then we use serial.println to print the value of this analog pin. Let's start the simulation, and notice that this pin is actually number 14. It is number 14 because, as you recall, in our series of digital pins, we ended with pin number 13. So A0 is actually pin number 14. But to avoid confusion, we can access it using this nomenclature that I indicated earlier. Once this is done, we will be able to take readings from the analog pin we specified. How do we do this? Well, through the method I mentioned earlier, which is called analog read, we need to specify which pin number we want to obtain a reading from. In this case, it is the pin called photo, or the pin represented by the variable named photo. We can store this value in a variable. This variable will be an integer, and we will name it, for example, reading, which will be equal to analog read of the pin photo, and we'll print it to the console through serial.println of reading. Let's start the simulation to see what happens. And notice that we have a set of 0 values. We have this value because we haven't connected this negative rail to our Arduino. Let's do it quickly. Okay, we connect to ground, change the color of the wire, and restart the simulation. But even though we have connected this missing rail, we still have a reading of 0 values. This is happening because, as you can see, we are actually reading a value of 0 from our analog pin to 0. Since we reached the terminal QND or ground, we have no potential difference, and therefore, we are reading a value of 0, which represents 0 volts. If we were to change this leg to the positive rail, let's also connect this rail to the positive side of our circuit. Notice what happens now. We start the simulation, and we get a reading of a value of 1023, which means that this value can change according to the connection we have in our circuit. However, if we try again or restart the simulation and we attempt to vary our photoresistor or the value of the photoresistor, look at what happens to this value we have here. The value really never changes, since the voltage remains the same even if we vary the resistance value. This happens because, remember, the resistance only changes the current, not the voltage. As you may recall, what we read on the analog pins is the voltage, not the current. Therefore, we will always have this value of 1023. How can we solve the problem of reading a voltage that is not 5 volts and be able to vary this value we have here? Well, we will do it in the next video using a voltage divider. A voltage divider, as its name suggests, is a type of circuit pattern that allows us to divide a voltage within a circuit. This pattern is quite easy to recognize. When you find 2 resistors connected in series, you can identify that it is a voltage divider pattern. Let's see this in practice using a tool called Every Circuit. This tool will allow us to simulate any type of circuit in an easy and visually intuitive way. I'm conducting these different tests using a trial version since this tool has a cost. I will now play around with this diagram that we have here. I'll start by dragging a power supply, which is equivalent to a battery or an Arduino pin. So I'll place my power supply and I can change the initial voltage. I will set it to 5 volts to simulate an Arduino pin or the voltage on an Arduino pin. Next, I'll connect the negative side of my voltage to ground and proceed to add a resistor to my circuit. I will flip this resistor, connect it, and this closely resembles what we currently have in our Tinkercad circuit. Let's start the simulation to see how our setup looks. Notice that we now have a visual representation of the different values throughout our circuit. We can see a potential difference here with 5 volts at the source and 0 volts at the output, which creates the voltage difference. It appears that this resistor is not doing anything in our circuit, although it is actually functioning. If we increase the resistance, we now have 1 kilo ohm, but if we increase it to, for example, 5.5 kilo ohms, notice how these green points we have here move a bit slower. This happens because, remember, a resistor directly affects the current in a circuit. Let's increase our resistance even more, and notice that these points move even slower. We increase it further and observe how the green points decrease in speed, which is equivalent to reducing the current. Okay. But as you can see, the voltage across the circuit remains the same. Let's stop the execution of this circuit. And what we'll do now is add a second resistor to our circuit. We'll disconnect this connection we have here to connect our second resistor. As you can see, these two resistors are connected in series. Let's change the value of this resistor to a value, for example, of 1 kilo ohm. We'll leave this second resistor with a value of 2 kilo ohms. Okay, now that we've added this second resistor, let's restart the execution of the circuit. Okay, notice that we have our current flowing in the circuit. We have the same input of 5 volts from our voltage source, but notice that a new value has appeared that wasn't there before. This value of 2.5 volts, which represents the voltage between these two resistors we have here. This value is calculated using some mathematical formulas, but since we are not interested in knowing the exact value of this voltage at the moment, only the theory, we won't show that in this video. In our project, with our photoresistor, we will have a 10-ohm resistor. Therefore, we will change this value to 10 ohm. Notice that with this change, we have a resistance of 1 kilo ohm and a voltage of 4.55 volts across these two resistors. This first resistor will be simulated by a photoresistor. Remember that a photoresistor can change its value depending on whether it receives less or more light. Keeping this in mind, we see we have 4.55 volts. And if we change the value of this resistor to, for example, 8 ohm, the voltage decreases, giving us 2.78 volts across these two resistors. Remember that the less light a photoresistor receives, the higher its resistance will be. What this means is that we are simulating a situation where the photoresistor is receiving little light. On the contrary, if we point a light source at the photoresistor, we would be decreasing the resistance in our circuit, which would cause an increase in voltage in our circuit. So basically, this is the diagram we need to replicate in our Tinkercad circuit and in our physical circuit. We need to have this photoresistor change its value based on the amount of light it receives and have a fixed resistance of 10 ohm to create a change in voltage between these two resistors. Well, once we've seen what a voltage divider is, let's integrate one into our circuit that we created earlier. Let's hide the code section, and as you can see, we now have this circuit assembled, which was the first demonstration I showed you in the previous video. If you recall, what we did in the previous video was add a second resistor in series to our circuit to obtain a different voltage. That's exactly what we will do here. If you remember, we added a resistor to our circuit. We're going to do the same thing here. We'll drag a resistor, set its value to 10 ohms, flip this resistor, and integrate it into our circuit. We'll position this resistor below the photoresistor so that these three terminals align at the same point. Now let's close the circuit by connecting our resistor on its terminal 2 to the positive rail of our circuit. Let's change this color to red. Now we have successfully added our second resistor to create a voltage divider. With this, we will automatically obtain a different voltage when we take a reading from our pin at 0. Before starting the simulation, remember that we made a change with this wire. Let's return it to the negative rail to avoid conflicts, and we'll start the simulation of our circuit to see what happens at this moment. Okay, we start the simulation. We see our serial monitor, and immediately we notice that we already have a different value compared to what we showed in a previous video. This is happening because our photoresistor is receiving less light. Watch what happens if I slide this bar to the right. Okay, notice that the value decreases, which indicates that we are receiving a lower voltage as we increase the amount of light. We reduce the amount of light, and we have a higher voltage, which means we have successfully integrated a voltage divider into the circuit. The purpose of this circuit is to have an LED that shines according to the amount of light we are receiving in our circuit. Therefore, we need to add this LED to our circuit. We will integrate it in a very simple way. Let's proceed to drag our LED onto our protoboard. Let's connect the cathode to the negative rail of our protoboard. We will change its color to black and connect the anode to one of the Arduino pins. For example, pin number 7. Let's change the color to purple, and we have successfully integrated our LED into the circuit. Now, let's proceed to the code section to indicate that we want to use our LED as part of the project. For this, we will create a constant to represent the LED pin. Let's set its pin mode using pin mode, LED pin, and we indicate that we want this pin to have an output value. At this moment, we are facing a small issue. When we analyze the digital outputs of our Arduino, I mentioned that a PWM-type digital pin can receive a range of values from 0 to 255. However, as we can see in the serial monitor, these values we are handling are well above those 255 units. This means that these values, as they are not useful for our project. How can we solve this problem? Well, by using a new method called map. We'll see it in the next video. Let's analyze this functionality called map, which is part of the Arduino language. The description indicates that this method allows us to remap a number from one range to another. We can scroll down to see the definition and check the syntax we need to use. First, we use the keyword map, followed by entering a series of values. It seems like a lot of values, but this method is actually quite simple. First, we need to input the value we are going to map. In our case, it will be the value we receive from the analog pin. Secondly, what will be the lowest value we can receive as part of this variable or value? As the third parameter, what is the highest value we can receive as part of this value? Next, we receive what is the value we wish to map the lowest number received in this variable to. Finally, what is the highest value we want to map from the highest value we receive as part of our initial value or variable. Let's look at an example below. Here we have an example. We see that in this example, we are receiving a value through an analog reading. And here we map a minimum value of 0 and a maximum value of 1023 to a value of 0 and a value of 255. This means that as part of this variable called val, we can receive a range between 0 and 1023. What we want to do is perform a conversion of values from this range to the other range. As a practical example, suppose instead of having the example we saw on the Arduino page, we have this line here. Notice that we are performing a mapping. The minimum value we could receive as this first number would be a value of 0, and the maximum value would be 100. If we wanted to convert this range to a second range from 0 to 10, and assuming we receive an initial value of 50, since 50 is exactly the midpoint of this range from 0 to 100, the result of this variable, well, the val, would actually be the number 5, as this number 5 is exactly the midpoint of our second range. With this in mind, we can return to our Tinkercad circuit, and we can use this new functionality we have learned. Essentially, we will go to our loop method, and after reading our analog pin, we will proceed to perform a mapping. We will create a new variable called letValue, which will be equal to a mapping of the variable called reading. Although we have seen that the minimum value we read is 49 and the maximum value is 969, we will perform a mapping from 0 to the value of 1023. As we mentioned earlier, the minimum value is 0 for a PWM digital pin, and the maximum value is 255. We will state that we want to map these values from 0 to 255. With this, we would obtain a new value in this variable. Let's see what value we obtain. Let's copy and paste in our serial.println method the value of let to see what happens. Let's check the serial monitor and notice that we already have a set of values different from those we had previously. Let's modify this slider. Notice that the values printed in the serial monitor change as we adjust the amount of light hitting our photoresistor. However, these values range from 0 to 255, which we can use to adjust the brightness intensity of the LED we integrated earlier. Let's return to our sketch, and what we will do next is to call the analog write method, which will allow us to input a value to one of the digital pins to control the brightness intensity of an LED. In this case, we want to modify the intensity of LED pin with a value, LED value. Before starting the simulation, we will proceed to add a resistor as part of our circuit to avoid any issues. Let's drag the resistor, rotate it, and place it on our anode. Change the value to 220 ohms and connect it again to pin number 7. Okay, with this change we've made, let's start the simulation, and you'll notice that immediately our LED has turned on, as it has detected that there is no light in our environment. If we indicate that we want more light at our photoresistor, watch how the LED's brightness changes, decreasing the intensity of that LED. If we modify the value of this slider again, our LED lights up at its maximum intensity. This is how a photoresistor works, and this concludes the Tinkercad part of our project. Let's see this example working physically. Let's proceed with the connections from the diagram we saw in Tinkercad. Physically, let's start by connecting a pair of jumpers to the side power rails. We will connect these jumpers to the 5-volt and N pins respectively. Next, let's integrate our photoresistor onto the protoboard. You can connect it wherever you like. After that, let's connect the left leg of the photoresistor to the negative rail of the protoboard. Once this is done, we will connect the other leg of the photoresistor with the jumper to the pin marked as A0 on our Arduino. Now, let's integrate the 10-ohm resistor. We will connect it between the photoresistor and the jumper leading to A-. The other leg of this resistor will be connected to the positive rail of the protoboard. With the photoresistor in place, we will proceed to insert an LED into the protoboard. Let's connect the cathode to the negative rail of the protoboard, and the anode of the LED should be connected to pin number 6 on our Arduino board. This is how our circuit looks when physically assembled. Now, let's proceed to copy and paste the sketch we created earlier, but this time in the Arduino IDE. On this occasion, I have changed this LED pin, as pin number 7 is not a PWM pin. That's why I have changed this pin to pin number 6, which is indeed a PWM pin. Let's upload our sketch to our Arduino board. We will proceed to test our project. Okay, here we have our project running. We have the voltage output displayed on the serial monitor. Here we have our project working. Notice that when the room is completely dark, the LED shines at its maximum capacity. As we bring a light source closer to the photoresistor, the LED decreases its brightness, thereby responding to changes in light in a satisfactory manner. In this section, we will analyze and work with a component called RGB LED, a component that will allow us to create very interesting and visually appealing projects. We have previously discussed the individual LED component. Now, imagine if we could combine a red LED, a green LED, and a blue LED into a single component. Well, this is exactly what happens with an RGB LED. It is the fusion of three LEDs into one. Interesting, isn't it? If you're wondering why a red LED, a green LED, and a blue LED, and not, for example, a yellow LED or an orange LED, the answer is that with these three colors, it is possible to represent a color by mixing them. The cube we see in the image is the RGB cube, which represents some of the colors that can be created by combining red, blue, and green colors. We can see that, for example, if we combine red with green, we obtain a yellow color. If we combine blue with red, we obtain a magenta color. A combination of blue with green would give us a cyan color. A combination of all three colors would theoretically give us a white color. Another important point we need to know when working with RGB LEDs is the configuration of the pins. We can find two pin configurations in the RGB LEDs we purchased when buying this component. The configurations are common cathode or common anode. Previously, when we analyzed the LED component, we saw that each LED has an anode and a cathode. Well, the same applies to the RGB LED. The difference is that to avoid having two pins for each LED of each color, it is simplified by bringing either the anode or the cathode out to a single pin, which we will need to connect following the same configuration we have seen with a regular LED. The other pins that are common will allow us to control each of the colors of the RGB LED. When working with electronic circuits, these are some of the possible ways we can represent the RGB LED component. Let's go to Tinkercad to test the RGB LED component. Well, we are back in Tinkercad, and here we have our designer. If we look in the components list, we have a component called RGB LED. We drag it onto our design surface, and notice that this RGB LED has 4 pins. One pin that will allow us to control the red LED, one pin which is a common cathode, one pin for controlling the blue color, and one pin for controlling the green color. The operation of this LED is very similar to that of a normal LED. In fact, let's proceed to drag a 9-volt battery onto the surface. We will connect the common cathode of our RGB LED to the negative side of our battery. Let's color this wire black. We will connect one of the other pins to the positive side of the battery. Remember that we need to place a resistor to avoid damaging our LED, just like a normal LED. So, let's place a resistor. I'll set it to a value of 470 ohms to avoid any issues, and we will connect the other terminal of the resistor to the positive side of our battery. I will color this wire red, as this pin represents the red color. If we start the simulation of this circuit, notice how successfully we're lighting up the red LED. Let's stop the simulation, remove this wire connection, and copy this resistor. You can do it with Ctrl-C and Ctrl-V. We will paste this resistor once more to have a resistor for each of the pins. This second pin we see here represents the blue color, and the third pin represents the green color. We will connect the blue pin to our power supply. If we start the simulation, notice that our LED is blue. And finally, when we conduct the test with this last terminal here and connect it to the power supply, we can see that we now have a green color. How can we achieve color combinations? Or how can we create new colors? Well, we will connect not just one resistor or one pin of our RGB LED to the power supply, but we will connect two. For example, we will connect the red and green pins. Notice that we have two connections. Let's color these wires so we can see them better. We have the red and green connected to the power supply. And if we start the simulation, we have a new color, yellow. We'll do the same with the third pin. We will color the wire blue, and if we start the simulation, notice that we have a white color. If we remove one of the other pins, for example, this pin representing the green color, and start the simulation, we will have a magenta color. Okay, this is the basic operation of an RGB LED. How can we integrate this into an Arduino-based project? Well, let's stop this solution and proceed to drag an Arduino board. We'll also drag a breadboard. Now, let's find our small test board. We'll look for the RGB LED component once more and connect it directly to our breadboard. Okay, here it is. Let's connect resistors to each of the pins to avoid damaging the RGB LED. This time, we will use a 330 ohm resistor. We will copy this resistor 2 more times to position it on each of the remaining pins. Okay, remember that this second pin represents the cathode, so we will connect our cathode line to the Arduino pin marked with G and D. Let's color the black wire and proceed to connect each of the RGB LED pins to different Arduino pins. We will connect the first pin to pin number 13, for example, and color this wire red to represent that pin. Next, we'll drag a second connection from the second pin, which represents the blue color, and connect it to pin number 12, coloring it blue. Finally, we'll connect the last pin to the pin marked with the number 11. This pin will represent the green color. Once we have this connection as part of our project, let's go to the code section. We indicate that we want text, clear the initial content. The first thing we'll do after deleting this code is to specify which are the different pins we are connecting to, which are pin 11, 12, and 13. So we write constants to represent these pins. First, the red LED, which is equal to pin number 13. Next, the blue LED, which is on pin number 12. Finally, we'll declare a constant called green LED to represent pin number 11. We will configure the pin mode for each of these pins, starting with the red LED pin. We specify that we want an output value. We will copy this line a couple of times and change the constant name to blue LED and finally to green LED. Okay, let's go to our loop function. Here in the loop function, we can modify the pin value to write a low or high value. Let's do it. For example, we perform a digital right on the red LED with a high value to energize the pin. And if we start the simulation, notice that we have successfully turned on this LED, or the red part of our RGB LED. If we instead turn on the green LED and start the simulation, we now have the color green. Even better, we can create combinations of different colors. For example, we can indicate that both the red LED and the green LED turn on at the same time. If we start the simulation, we successfully get a yellow color. The question here is, how can we create a color different from those we have seen? For example, an orange color. Well, we will see this in the next video. In this video, we're going to talk about a method called analog write, which will allow us to work with the pins designated as PWM. In a previous lesson, we already discussed what the pins marked with this PWM nomenclature are, and we noted that they are used to simulate an analog output. We can send a value to this pin, allowing us to simulate sending 2.5 volts, even though we aren't actually sending 2.5 volts. However, to our human perception, it may seem like this is happening. This will be useful in projects where we need to send an intermediate value, or a value in the range of 0 to 255. To one of these pins marked as PWM. As we know, a digital pin can only accept low or high values. These PWM digital pins are marked by the line we see here. As you can see, at this moment, we are connecting 2 leads of our RGB LED to non-PWM pins. Let's start this section by changing the pins on our Arduino. We will change this first pin to pin number 9, meaning we will connect the green lead to pin number 9. We do the same with the blue lead, changing it to pin number 10, And we perform the same action with the red lead, moving it to pin number 11. Okay, we have redefined our circuit. How does sending signals to PWM pins work? Well, let's refer to the Arduino documentation. And here we have the reference for the method called analog write, which essentially tells us that we can send an analog value to a pin with a PWM wave. And at the bottom of this page, we can find the syntax to invoke this method. As you can see, it asks for a pin, which must be a PWM pin for this to work correctly. And we have a second parameter for sending a value. This value can range from 0 to 255. This specifies the duty cycle we want to manage. Once this is understood, let's look at a bit of theory about colors. Let's go to this page called homocolorcodes.com. Here we have a chart that allows us to select a color, and notice that at the top we have the RGB notation, which consists of the 3 colors we were using in our project. As you can see, we can select any color we want in this square, and notice that the different values specified as part of the RGB color change at the top. This means that these 3 colors, representing red, green, and blue, can form the color we are selecting. We can choose a yellow, a red, an orange, etc. If we do some tests, you will notice that the maximum number accepted in each of the scales of these colors is 255. This is very convenient for us. As you recall, the values we can use for invoking the analog write method range from 0 to 255. This means that we can send the different values we have here to one of the PWM pins and thus obtain the color we select here. This is indeed quite interesting. Let's see this in practice. Let's return to Tinkercad, go to the code section, and remove this pair of lines where we only invoked digital write. We will no longer invoke the digital write method, but rather the analog write method, since we want to send values from 0 to 255. So let's remove this pair of lines and see how to use the analog write method. We will write analog write and in parentheses specify which pin we want to modify, in this case the red LED for example, and we will send it a value of 70 before starting the simulation. Remember that we made a change to the circuit pins. However, we also need to modify the values of our constants to match the pins we changed. So the red LED is pin number 11, the blue LED is pin number 10, and the green LED constant is pin number 9. Let's start the simulation to see what happens with this change we made. Notice that we no longer have an intense red color as we did before. Instead, we have a red color, but at a certain intensity. If we refer to the HTML color codes, we can modify the red value. Let's set it to 70. We set the green value to 0 and the blue value to 0, since we are not assigning a value to the green or blue LED, which is why they default to a value of 0. So if we go back to the color palette, we can see that this is the color we are simulating in our Arduino circuit. For example, if we wanted to simulate another color, like a blue of this shade, we could copy these values. The red value is 42. We stop the simulation, go back to write analog, write to modify the green LED, which should have a value of 144. And finally, we do an analog write for the blue LED, which should have a value of 146. With these changes, we start the simulation again, and notice that we already have a blue shade similar to the color we specified as part of our color palette. With what we've learned, we can now do even more interesting things. For example, we will indicate that we want to set our RGB LED with values of 0, 0, and 0 on each of its legs, meaning we will not energize our RGB LED initially. We can introduce a delay to wait a certain amount of time, and to avoid writing the exact duration we want to wait, we can create a constant called time that will be equal to, for instance, 500. What we want to do with this constant is specify the amount in milliseconds that we wish to wait between each color change. So as part of this delay, we pass the time as a parameter. We can copy the lines we have created and modify the values of the different LEDs. We will indicate that first we want to turn on only the red color Then we want to turn on only the green LED, and afterward, only the blue color. For this, we place the value 255 in this line. Once we have displayed the three primary colors, we can start creating the light show. For example, we will indicate that we want to turn on the red LED and the green LED. After this, we can indicate that we want to color the green LED and the blue LED. Finally, we can specify, for example, that we want to turn on the red LED and the blue LED. This will create a light show. We will start turning on the RGB LED with different shades, and we'll give it a timing so we can correctly visualize the color display. Let's start the simulation to see how this looks. Here we have an error in the code. Let's see what it's about. This is because we missed the closing parenthesis and the semicolon here. We can see that we also need the closing parentheses and the semicolon at the bottom. Let's try to start the simulation again, and we see that our RGB LED is now successfully lighting up with different shades. If we want a slower transition, we can go to our constant we created called time and give it a duration of 1000 milliseconds, which is equivalent to 1 second. We start the simulation, and we now have an RGB LED with slower transitions. Once we have created the project prototype in Tinkercad, let's see how to connect it physically. Let's start by adding the RGB LED. In my case, it's a common cathode RGB LED, which is the pin I am pointing to with a green arrow. Let's begin by adding resistors to the other pins. First to the blue pin, then to the red pin, and finally to the green pin. You can see that in this RGB LED, the pins are reversed compared to how we had them in Tinkercad. While in Tinkercad, this third pin represented the blue color. Here in the physical model, this third pin represents the green color, and the last pin represents the blue color. Now, let's connect the common cathode with a jumper directly to one of the pins marked with GND on our Arduino. Next, we will connect the other pins of the RGB LED. In my case, to better differentiate the jumpers, I've connected one that corresponds to the color of the LED. First, I connected a red jumper, which goes to pin number 11, a PWM pin. Next, I connect a green jumper to the output of the jumper that will give us the green color. This jumper is connected to pin number 9 to maintain the same layout as in Tinkercad. Finally, we connect the blue jumper to the pin that will give us the blue color to the pin marked with the number 10. Done! That's how our project looks assembled. Once we have uploaded the sketch to the Arduino board, this is how our project looks functioning in real life. It looks great, but we can connect some material to diffuse the colors for better visibility of the effects. In my case, I will place a plastic tray to better appreciate the colors. In the following videos, we will create another lamp, but this time it will turn on when no light is detected in the room, and it will feature a color game that will give it more life. We are in the final stretch of our course, and to celebrate, we will create a mood lamp. This is a very eye-catching project that can definitely set a romantic scene to win over your partner. This is the finished project. Look at how we have those bright and vibrant colors coming from our Arduino. Isn't it amazing? To complete this project, these are the components we need. A breadboard, a common cathode RGB LED, a photoresistor, 330 ohm resistors, one 100K resistor, although this can vary. We'll see why later. 9 male-to-male jumpers, and of course, our Arduino Uno. With these components, let's take a look at the connection diagram for the project. This is the connection diagram for our project. They are basically grouped into two sections. The first section consists of our RGB LED that we have here. This LED is connected with 3 resistors to 3 Arduino pins, 9, 10, and 11. On the other hand, we have our photoresistor. The purpose of this is that when the photoresistor detects light, our RGB LED remains off. However, when darkness is detected, our RGB lamp automatically lights up and begins to show that colorful ambiance. So the photoresistor is connected to the pin marked A0, which is the analog pin 0. We also see that our Arduino has the GND and 5-volt outputs connected to the protoboard. So this is basically the connection diagram. Let's see how to physically connect the components in the next video. Once we have reviewed the diagram, we will learn how to connect it physically. Here we have the diagram we saw earlier. As always, we will simplify it to explain how to connect each component individually. Let's start by connecting our RGB LED. As we can see in the image, it is important to identify which is the common cathode, which is basically the longest leg of the 4. In this image, you can see the RGB LED that I will use. We can appreciate what I mentioned earlier. We see that we have 3 legs of equal length and one that is noticeably longer. This leg is the common cathode. We will proceed to bend the longest leg, which is the common cathode. This is to allow us to insert the common cathode leg into the negative line of the protoboard. Here we have the view from a different angle so you can see how it looks. Note that there should be a free space between the 3 legs. This, in our diagram, is equivalent to the image as we're placing the common cathode on the negative line of the protoboard. Next, we will protect the LED with 3 resistors, one for each leg that is not the common cathode. These resistors are 330 ohms. Looking at it physically, here are the resistors connected. The next step will be to connect 3 jumpers that will allow us to reach our Arduino. I have placed a red wire, a green wire, and a blue wire, which represent the colors of the RGB LED output. That is, the red wire is connected to the red color of the RGB LED, and the same applies to the other 2 jumpers. Here we have the physical connection I made with the jumpers. On the other side, we see that the wires go to pins 9 for the blue color, 10 for the green color, and 11 for the red color. We do the same thing physically for the same pins in the diagram. With this, we have completed the connection for our RGB LED. Let's now proceed to connect the photoresistor. The purpose of this component is to turn on our ambient lamp as soon as it detects a lower amount of light, based on the resistance. We will place the photoresistor at the other end of the protoboard to control the incoming light more easily. The orientation of the pins doesn't really matter. You can place them however you prefer. Here we have an image showing how far it is from the RGB LED's location. The next step is to connect the first pin to the negative rail of the protoboard. Here, we have the physical connection of the jumper for the first pin. How does this jumper reach the negative rail of the protoboard? The next step is to connect the other pin of the photoresistor to the pin marked A0 on the protoboard. Physically, this is done by placing the jumper in the same line where the second pin of the photoresistor is located and connecting the jumper from the other end to the pin marked A0 on the Arduino. Once we've done this, we will connect a resistor in the same line as the pin we connected to A0, in my case, in the same line as the yellow jumper. As an additional note, I am using a 100K resistor, but you can use a different value. I'll explain. The higher the resistor value, the less sensitive the project will be to changes in light. That is, if you want the lamp to turn on with just a little darkness, you will need to use a resistor with a lower value. Conversely, if you want the lamp to be less sensitive to light, you will need to use a resistor with a higher value. Here, we can see the connection of the resistor. As I explained, it is connected on the same line as the jumper that goes to pin A0. From the other end of the resistor, we will connect a jumper that goes to the positive line of the protoboard. Looking at it physically, here we have the jumper connection. One end comes from the resistor line, while the other reaches the positive line of the protoboard. With this, we have completed the connection of the photoresistor. Finally, we need to connect a jumper from one of the pins marked with, again, the Arduino to the negative line of the proto board. Here we see it physically. I'm connecting a black jumper to one of the pins marked with G&D. From the other end, I have connected the jumper to the negative line of the proto board. Similarly, I have connected a gray jumper from the pin marked with 5 volts on the Arduino to the positive line of the proto board. Once again, looking at it physically, we see a gray jumper coming from the Arduino from the pin marked with 5 volts and reaching the positive line of the proto board. Lastly, but importantly, we need to place a jumper connecting the 2 negative lines of the proto board in order to close the circuit with the RGB LED. Here, it is important to note that we are connecting our jumper before the break in the proto board so that we can reach the pin of the RGB LED. With this, we have achieved a connection of all the components for our project. Additionally, we will create the outline of our MUT lamp by joining the 2 ends of a regular sheet of paper. In my case, I have taped the ends with duct tape, and basically this will help us reflect the colors of our RGB LED. With all this done, let's see how to code our project to make our lamp shine. Now, let's create the sketch to animate our ambient lamp. The first step we need to take is that in the attached files, I've left a compressed file for you to unzip. We will then right-click and select Extract the RGB mode. You will see a folder like this. You need to cut this folder. We must navigate to C, Program Files, x86, find the Arduino folder, and here we have a folder named Libraries. Here we will proceed to paste this folder. In my case, I've already pasted it previously, so you'll need to paste this folder. The next step is to ensure you restart your Arduino IDE, as it will not recognize the new library we installed if you don't restart it. Once we have restarted our Arduino, we are ready to start coding our program. The first thing we'll do is include the library we just installed. This library will allow us to make changes to our lamp easily. There's no need to reinvent the wheel, as libraries already exist that will make our lives easier and increase our productivity. So we include this library via an include statement, Arduino, just as it is written. That is how you should write it as well. Next, we will declare the pins to which our RGB LED is connected. So we specify int red pin equals 9, int green pin equals 10, and finally int blue pin equals 11. These pins must correspond to the red, green, and blue wires that we have connected to our Arduino. Next, we will declare a new variable called LDR pin, which is basically the pin for our photoresistor, connected to analog pin 0. For this, we will set its value to 0. Once this is done, we will need to declare a variable of type RGB MUT. Note that the M is uppercase, and, well, all of it is uppercase, while the W and the D are lowercase. Let's call it, for example, MUT, and in parentheses, we will declare the initialization of this variable, which basically consists of the pins connected to our RGB LED. So the first parameter is the pin for the red color of your RGB LED. In my case, it is defined by the variable red pin. The second parameter is the pin that represents the green color. And in this case, it is in the variable green pin. Lastly, as you can guess, it is the pin connected to the blue color. In this case, it is connected to blue pin. We'll do a quick check to see that everything is all right up to this point. And we see that it has compiled successfully. Okay, let's proceed to code our setup method, which is used to initialize various components. Or in our case, we will specify how this LDR pin will behave and how our MUT variable will be initialized. We will then set pin mat to indicate that the photoresistor will act as an input. That is, we will be able to read information from this device or sensor. Subsequently, we will initialize the values of our MUT variable, which will allow us to make color transitions with our ambient lamp. First, we will configure m.set in lowercase and subsequently mount with an uppercase at the beginning. Notice how it is written. This method will allow us to specify how our ambient lamp will behave. Here, as a comment at the beginning of this sketch, I'll leave you this note, which basically specifies the different modes you can use through this library. First, we have a fixed mode where the color will not change. Next, we have the random hue mode where the color fades in a random hue. We also have a rainbow mode where we transition through reds across all the values that make up the HSV spectrum. Additionally, we have different fading options in red, blue, and green. Finally, we have a fire effect, which behaves like an electronic lamp. In our case, we will use the second mode, random hue mode, where we will have random fading. To carry out this action, we'll return to set mode that we had previously, and we need to access through RGB, and here specify which mode we are using, which in one case is this one. So I will copy it and paste it after these two colons. These colons are mandatory, so you must place your code exactly as it appears here. With this, we specify how the color transition will behave. We will configure the second method through m.set in lowercase, h with uppercase, holding, t with uppercase, time, and basically this method will allow us to specify how long we will keep the same color before carrying out another fading. In my case, we will indicate that we want to maintain the same color for only 2 seconds. Subsequently, we will indicate through m.set painting steps, and this method will allow us to specify how many steps we want to take to complete a transition between colors. We will indicate that we want to do it in 150 steps. We will also specify through m.set fading speed, and in parentheses, we will indicate the amount of 50. This method will allow us to specify how long each step will last. Thus, these two methods complement each other, as a complete transition will take the amount of time of each step times the number of steps we have specified here. That is to say, basically what will happen is a multiplication of 150 by 50. This amount of set fading speed is specified in milliseconds, so 150 times 50 equals 7 seconds. Each transition will then take 7 seconds, and if you want to reduce this amount, you can do so by decreasing the number of steps or by reducing the duration of each step. Finally, we will specify the set HSB method. Basically, with this method, we will be able to specify an initial random color. In this case, we need to pass 3 values. The first value is the hue of the color. To make this a bit clearer, let's check this site, colorizer.org. Here we have the color scale we'll use, which is the HSB scale. We see that we have 3 possible values: hue, saturation, and brightness. In other words, hue, saturation, and brightness. What we will do is choose a random color based on the hue. So if we play with this slider, we can see a wide range of colors that look quite nice. We will set the saturation to 100% and the brightness to 100% as well. And we will have different shades. We will then specify that this hue be random while keeping saturation and brightness at 100. Another important thing is that the hue values range from 0 to 360. Therefore, we will specify that the first value, which is the hue, will be set to random with parameters 3, 50, and 9. As we saw, this value will take a random value between 0 and 359. The second value will be 255, and finally, the last value will also be 255. With this, we have specified the different values for our variable RGB MUT. Here we need to change the variable names, as I have used M here, and we have used the word MUT here. So let's quickly change M to MUT to avoid issues. We compile, and we see that we have another issue. I forgot to include RGB MUT, which is the name of the class we have here. We compile again, and now we have a successful compilation. Now that we have successfully coded this setup method, let's move on to our loop method. First, we need to read the value of our photoresistor. We will declare a variable called ambient light, which will be equal to an analog reading from our pin that we specified earlier, namely LDR pin. Now that we have read from this pin or our photoresistor, we will check if ambient light is greater than 600. What we are doing here is comparing the reading level from the photoresistor against a value of 600. Basically, what will happen is that if this condition is met, a lower amount of light has been detected. Therefore, it is advisable to turn on the lamp. We will do this through mode. We have a method called tick, which will update our ambient lamp values based on the configuration specified here. This library will take care of everything automatically. In the event a greater amount of light is detected, we will proceed to perform a digital write red pin low. In other words, we will turn off the red LED. We will copy and turn off this line 2 more times, and we will change this instruction to indicate that we also want to turn off the green pin and the blue pin. Let's verify the program. We see that it has been compiled successfully, and now all that is left is to upload this sketch to our Arduino board. Let's test this code then. Ready. We have uploaded the sketch, and here we have our physical project set up. We see that I have placed a lamp to illuminate my photoresistor, ensuring that the lamp does not turn on while there is sufficient light. I will proceed to turn off this lamp, and we will see how our ambient lamp reacts. Great. We see that our ambient lamp has turned on and how it begins to display those beautiful colors that light up our environment quite well. Let's leave it, or let's fast forward the video a bit to see how our lamp looks. In this section, we will learn about a component that is widely used in the world of electronics, namely the potentiometer. There are different shapes and sizes in which we can find this component. In the image, we see several of them. I'm sure you have used some of them, for instance, when we increase or decrease the volume of a sound device. When DJs create their music by mixing different tracks, or when we need to adjust the gas coming from a stove, all these are examples of the use of potentiometers in real life. The question that arises, how do these potentiometers work? Well, as you have seen so far, potentiometers have 3 terminals. Let's call them A, B, and C. Following this numbering, if we looked inside the potentiometer, we would see something similar to 2 combined resistors, although they are not resistors as we know them. The value between A and C is a constant resistance, which determines the value of the potentiometer. For example, they come in 10 ohm, 100 ohm, etc. In between we have point B. This point B allows us to vary the resistance between points A and B and C, while A and C will always maintain the same value. Inside the potentiometer, we can actually find a resistive track. The wider this track is, the greater the resistance of the potentiometer will be. When we turn the knob of the potentiometer, the length of the resistive track varies between the points we mentioned earlier. So, if the knob is turned to the right, the resistance between points A and B increases, and if turned to the left, the resistance decreases. At the same time, the opposite occurs with points B and C. With this in mind, we can conclude that we can connect the potentiometer depending on the measurement we want to make regarding the movement of the knob. Let's go back to Tinkercad to examine this component more practically. We are now back in Tinkercad. What we are going to do is look for a potentiometer in the component list. It is this blue component that we have here. We will drag it onto the surface and look for our tool called multimeter. We drag the multimeter, and now we have these 2 components to conduct some tests. With these 2 components, I will proceed to make a connection between terminal 1 and the negative pole of our voltmeter, and I will also connect this pin marked with whipper to the negative pole of our multimeter. Okay, here it is. I will quickly color these wires for better visibility, and we will start the simulation to see what happens at this moment. I will change the type on the voltmeter. I will indicate that I want to measure resistance. Notice that at this moment, I have my knob completely to the left, and therefore we have a resistance of 0 ohms. However, if we start moving this knob, notice how the resistance changes and increases as we turn the knob to the right. In this case, we reach up to 250 ohm, which is the total value of this potentiometer that we have here. If we stop the simulation and hover over the potentiometer, we see that this is the total value of this potentiometer. So remember, if I turn the knob to the right, we have the maximum resistance available. If I stop the simulation, I will remove this black cable, and instead I will proceed to connect the last pin, or the one named terminal 2. We will connect this terminal to the negative pole of our multimeter. I will change the color to black. If I start the simulation right now, notice something very curious happening. At this moment, we have a resistance of 0 ohms. This is in contrast to what we had when connecting with terminal 1. And this is happening because between terminal 2 and this whipper, we have no resistance. Remember that the level of resistance between these 2 points is determined by this knob we have here. As we start moving to the left, notice how in this specific case, our resistance increases when we turn the knob to the left, as we have a greater degree of resistance, while from terminal 1 to the whipper, we have less resistance. Therefore, our potentiometer acts according to how these pins of the potentiometer are connected. Once we understand how a potentiometer works, we can start doing more interesting things. For example, in this lesson, we will proceed to change the brightness of a regular LED based on the position of the knob on the potentiometer. Let's stop the simulation and search for an Arduino Uno component. We drag our board onto the surface, move it a bit lower, and now let's also drag a small breadboard component, positioning it at the top. Next, I will drag a potentiometer component onto my breadboard. Okay, I'll place it on the protoboard. The first thing we need to do is ensure we can satisfactorily read the values from the potentiometer. We will first connect terminal pin 1 and terminal pin 2 of the potentiometer. So I connect the first pin to the negative rail, coloring this cable black, and I will connect terminal 2 to the negative track of the protoboard, coloring that cable red. Once I've done this, I will connect the protoboard directly to the 5 volts and GAN pins of our Arduino. Okay. I connect our positive rail to the pin marked with 5 volts on our Arduino. I will color this cable red, and I will also proceed to connect the negative rail to the pin marked with GND on our Arduino. Okay, I will better position these cables. All right, we have connected our breadboard to our Arduino board. The next thing we want to achieve is to read the value based on the change we make in the potentiometer. Well, remember in a previous lesson when we discussed voltage dividers and saw that when we had a pair of resistors in series, we could find the voltage between those 2 resistors? Well, we can achieve something similar with our potentiometer. Let's recall that in the slides we saw we actually have 2 resistors as part of the potentiometer, which means we can connect to this wiper pin and obtain a different voltage from the incoming voltage. That is, from the 5 volts that enter, depending on the value we are adjusting on our potentiometer. This is what we're going to do. We'll connect this pin called wiper to one of the analog pins on our Arduino. I will proceed to connect this pin to our Arduino at the pin labeled A0. Okay. Okay, here we have it up close. I'm going to adjust these wires a bit better, and I will color this wire, for example, purple. Okay, with this, I now have our potentiometer connected to one of the analog pins. The next step is to read this analog pin to ensure everything is functioning correctly. I will then proceed to the code section, specify that I want only text, and remove this pre-made code that appears. I will declare a constant that is of integer type and call it pot for potentiometer, and this will be set to 0. This represents analog pin number 0, which we have here. Within our loop method, I will declare a new variable called pot value that will equal a reading from the analog pin A0. So in parentheses, I'll input pot to perform the reading from pin pot, which is pin A0. As I want to see the value we are reading as part of this variable, let's initialize the serial class using begin 9600. And after the reading, I will indicate serial.println to print the value of pot value. Once this is done, let's start the simulation to see what happens. We go to the serial monitor and we see a value of 0. Now let's adjust our potentiometer and start playing with it. Okay, notice that we are successfully reading a different value every time we increase the potentiometer's value. Notice that the maximum value we are receiving is 1023, which, as you might remember, is the maximum value our analog pin can receive. So we're reading from a value of 0, which is the minimum value of the potentiometer, to a value of 1023. With this in mind, you can probably imagine what we can do with the LED. We can add an LED and map this range of values to a set of values on a digital pin using digital write to change the intensity of the LED. That's what we're going to do right now. Let's stop the simulation. I'm going to remove that part of the code. I will focus on the design part. I will proceed to insert a regular LED at this moment. I drag my LED. I will also drag a resistor. I will set this resistor to a value of 330 ohms. I connect the cathode lead of my LED to the negative rail. I will then connect the anode lead of my LED to one of the PWM pins on our Arduino. I will connect this lead to pin number 11, for example. I will color this wire black for better visibility. Now I have my LED connected to pin number 11, which is a PWM pin. Let's go to the code section and enter this pin in code. We declare a constant to represent this pin through a variable called a LED pin, which is equal to 11, the pin value I connected to the Arduino. Next, I will configure the pin mode. I indicate that I want to set lead pin with a value of output. I return to my loop method, and the next thing I will do is read the value of my analog pin. I will convert it to a range between 0 and 255, which, as you remember, is the range we can send to a digital pin with PWM. I designate int lead value, or it can be lead value if you prefer, and this will equal the mapping of the value entered in the variable pod value, which is the value we read from our analog pin. Here, I indicate that the minimum value I am reading as part of this analog pin is 0, and the maximum value is 1023, which, as you may recall, are the values we read from this pin. Then I indicate that the range I want to convert it to goes from 0 to 255. With this, I will map these values and obtain a new value. Finally, what I will do is invoke the analog write method to utilize this PWM feature and send to the pin lead pin, the LED value, which is the conversion I made earlier. Okay, let's test that everything compiles correctly. The simulation has started. I will hide this part of the code, and notice that since I have the knob all the way to the right, my LED is lighting up at its maximum capacity. If we start turning the knob to the left, notice how our LED loses intensity. If we reach the far left, our LED completely turns off. We can then play with these values to increase or decrease the intensity of this LED. We have seen how to increase or decrease the brightness of an LED using a potentiometer. What else can we do with LEDs in a potentiometer? Well, we have previously examined the RGB LED component. What we're going to do in this section is take a step further and control each color of the RGB LED with 3 different potentiometers. Each one will control a different color, allowing us to visualize different values on the RGB LED. The next step is to modify our circuit. First, we'll add a couple of additional potentiometers, since each one will control a color of the RGB LED. The first will control the red color, the second will control the green color, and the last will control the blue color. Now we'll go back to the components list and drag a couple of additional potentiometers. Okay, Here's the first one, and I will drag the second. The next step is to connect the left and right pins of our potentiometer to the corresponding rails. We will connect the first pin to the negative rail and the last pin to the positive rail. I will do the same with the third potentiometer, and that's it. The next step is to connect the wiper of each potentiometer to a different analog pin. In this case, I will connect the second potentiometer's wiper directly to pin A1. Okay, and I will connect the last potentiometer to the terminal marked with A2. I will now arrange these wires a bit better so that this example is clearer, and I will use a different color for this wire. Okay, I will also color this wire, which goes to the wiper of the third potentiometer, and I will arrange it better. All right, here we have the corresponding connections set up. We have connected our 3 potentiometers. The next step will be to remove the red LED we had previously, and in its place, we will replace this regular LED with an RGB LED. We'll find it and drag it onto our surface. In this case, I have kept the cathode on the same line that connected to the negative rail of the protoboard. I will proceed to make the connections for my RGB LED. I will connect the first pin, which corresponds to the red color, directly to the Arduino on the pin labeled with the number 11. I will change the color of the wire to red. Now, I will proceed to connect the second output of our RGB LED. I'll make a change. As it was previously connected to pin number 11, I will change it to pin number 10. Lastly, I will proceed to connect the green output. Here, remember that in Tinkercad, this pin corresponds to the blue color, and the third pin corresponds to the green. I will proceed to connect this resistor to the pin coming from the green lead, and I will do the same with the lead that I have with the red output. I copy the resistor, paste it, and then I will connect the last color, which is green. Here, I will color this wire blue, and I will proceed to connect the last pin of our RGB LED to a pin marked with the number 9. Okay, with this, my circuit is ready. I've connected the 3 potentiometers, and I have connected my RGB LED. As you can see, without realizing it, we are creating increasingly elaborate and complex projects. I can assure you, my friend, that you are perfectly understanding what we are doing if you have seen the previous lessons. I will proceed to go to the code section, since we want to modify this sketch to interact with the components we have added. I will go to the top part and modify the name of the first potentiometer. I will name it, for example, Pot Rojo. I will keep this value as A0, since we are still connected with the first potentiometer to the pin marked with A0. I will create a couple more constants. The second constant will be called Pot Verde, and the last one, Pot Azul. I will proceed to change the pin of Pot Verde to A1, and this constant of Pot Azul to A2. The next step will be to define a set of constants for each of the pins for the RGB LED outputs. I will change the name of this first constant to LED Rojo. I will proceed to copy and paste this constant a couple of times. The second constant will be called LED Verde, and the last one, LED Azul. I will proceed to change the pin number of our green LED to 10 and the blue one to 9. I will swap the pins for the purpose of not getting confused when we do this physically. I will change the blue wire to pin number 9 and the green wire to pin number 10. So the red is on pin 11, green on pin 10, and blue on pin 9. Okay, with this change we made, let's go back to our setup function and proceed to define or change this pin mode to affect the red LED. I will copy this line a couple more times and indicate that I want to initialize the green LED pin and the blue LED pin as outputs. Once we've configured the pins, we will move on to our loop method. Here we create a variable called pot value. Let's change this name to red pot value to indicate that this value corresponds to the first potentiometer or the red potentiometer, and we will read from our pin called pot rojo. I will copy this line a couple more times and create a couple of additional variables. The second variable we called green for reading the value of the green potentiometer. And finally, blue pot value to read the value of the last potentiometer. I will read from the potentiometer located on the green pot pin. and finally from the potentiometer located on the blue pot pin. Once we read the different values from the potentiometers, we will map each of them to obtain a value between 0 and 255. I will change the name of this variable we created to red value. I will proceed to copy this line a couple more times and change the value we are getting from the potentiometer. In this case, the first value is red pot value. In the second functionality, we change it to green pot value, and we will also change the last map to blue pot value. This way, we will convert a value from the potentiometers into a value that we can display on our RGB LED. Finally, we will perform the writing through analog write. Here, we will change the name of the pin. The name of the pin is Ledrojo. We will indicate that we do not want to pass LED value, but red value, which is the conversion we made earlier. We'll paste this line a couple more times, but this time we will indicate that we want to write or change the value of Ledvert, and also the value of LED Azul in the last line. At the top, we have not changed the names of the variables. We will change these names to green value and blue value. These values are the values that have been previously converted from the range 0 to 1023 to the range 0 to 255. These are the values we will send to each of the colors of our RGB LED. We will comment out this last line of serial.println and start the simulation to see how what we have done behaves. Okay, we see that everything is compiled successfully. Let's close these sections so we can see our project better. And notice that we have our completed project here. If we turn all the knobs to the left, we see that we have an LED that does not really have a color or is turned off. If we start moving these knobs, notice that when we turn the first knob, the LED changes to red. Let's return to value 0. If we test the second potentiometer, we see that our LED emits a green light, and if we change the value of the third potentiometer, we get a blue color. We can create combinations of these colors by turning the knobs at different degrees. If we turn the second and third knobs, notice that we get a lighter blue color. If we include the first knob, we see a different color behavior. This is how we achieve the dynamic color change of our RGB LED based on the adjustment of these knobs that are part of our project. Once we have verified that the project works correctly in Tinkercad, let's assemble it physically. Let's start by inserting our RGB LED into the prototype board. In my case, it is a common cathode RGB LED, which is in the second pin. Let's connect its corresponding resistors. I have connected a 220 ohm resistor to each output, except for the common cathode. Let's also connect the common cathode to the negative rail of the prototype board. Later, we will return to this section of the project. Now, let's proceed to connect the potentiometers. In my case, there are 3 potentiometers of 10K. I will insert them like this into the prototype board. I connect the second one. I'll provide an image for you to see the pin insertion. I will also connect the third one. Let's connect the first pin of each potentiometer to the negative rail of the prototype board. Now let's make the connection from the third pin of each potentiometer to the positive rail of the prototype board. Let's power the prototype board by connecting a pair of jumpers, one for each rail of the prototype board. We will connect these jumpers to the GND and 5-volt outputs of our Arduino. As you can see, our potentiometers would obstruct the connection of a jumper to the signal output. We can resolve this by removing the section of the prototype board with the unused rails. In my case, I can remove this part from bottom to top. The truth is, there are so many types of prototype boards that ultimately each person has to solve this issue according to the one they have. I have resolved it this way, but you will surely find the best solution for your problem. With what I have done, we can bend the legs of the potentiometer so that they appear as in the image. This allows us to connect a jumper to the signal rail of the potentiometer. We will connect the first jumper to the pin marked A0 on the Arduino. Let's connect a second jumper, this time to the signal pin of the second potentiometer. We connect this jumper to pin A1 on the Arduino. Finally, we will connect the signal of the third potentiometer to the pin marked A2 on our Arduino. It's time to return to the RGB LED section. Let's connect the jumper to the pin that will control the red color. We will connect this jumper to pin number 11 on the Arduino. For the green color pin, let's connect a jumper that will go to pin mark number 10 on the Arduino board. The last pin, which controls the blue color, will be connected to pin mark number 9 on our Arduino. We have connected to PWM pins to vary the intensity of each color of the RGB LED. Once we have assembled the circuit and uploaded the sketch to the board, this is the final result. You can see that as we turn the knobs, the colors change. This forms a new color each time a knob is turned, creating combinations that look really nice. This is a practical way to use potentiometers in an Arduino-based project. Thank you. Making decisions in our daily lives is common. Real-life examples include when you ask yourself, or when you're driving and reach a traffic light. You ask yourself, is the light red? There are two possible answers, yes or no. If the light is red, it is logical to stop. If the light is not red, it is logical to continue driving. What we have here is a decision-making process. Let's look at another example. Here we have another question you might ask in your daily life. You can ask yourself if the temperature is above 25 degrees, and if the answer is yes, we will turn on the air conditioning. If the temperature is below 25 degrees, we will not turn on the air conditioning. Another example of decision-making comes from this scenario I have outlined here, where we might ask at some point if 5 equals 5. This is a very simple question, and the answer will always be yes. If you notice, the answer of no will never apply, since 5 cannot be different from 5. 5 will always be 5. On the other hand, focusing on a programming example, we can define a variable called x with an initial value of 40. After this assignment, we can ask, is x equal to 45? Upon analysis, we can see that this answer is false. As x is not equal to 45, it is equal to 40. Therefore, the answer to this question will lean towards the left, indicating no, x is not equal to 45, as they are different values. This means that this yes will never apply. Let's see another example. Here we have another assignment, x equals 40, and we can ask, is x less than 45? The answer to this question is yes, since 40 is less than 45. These diagrams we have here help illustrate decision-making in our daily lives. They even prepare us to face the concepts we will explore in the following videos. Lastly, these expressions are called Boolean expressions, meaning they can generate a true response or a false response. Notice that in all these paths we've seen, or in all these diagrams, we only have two possible outcomes, a yes response and a no response. So remember, this is called a Boolean expression. We will begin the practical part on the if decision statement. The first thing we need to do is identify the Boolean variables. We have seen this in a previous video, but to refresh our memory, we will carry out a practical exercise that will help us identify this type of variable. To practice in this section, we will open a file called Practica-if, which you will find as part of the attachments for this lesson. Basically, what we have here is an Arduino with 4 LED lights, and we have the configuration of the constants that reference each of the pins of our Arduino, along with their corresponding pin mode configuration. Here, we have each of them set up as an output format. This is within a method called configurer, which we invoke once our Arduino sketch is initialized. Here we have the setup method, and we call the configurer method within it. Okay, let's see how we can create a Boolean variable. We will leave a space after the configurer method, and what we will proceed to do is declare a Boolean type variable. We do this by specifying the data type and then indicating the name of our variable. It can be any name. For example, icing. We can assign it a value of true or false. So we could write true or false in case we want to initialize this variable with a false value. What we will also do as part of the project is configure the serial monitor. So we write serial.begin and in parentheses 9600. This is to display the value of this Boolean variable in the serial monitor. Then we'll write serial.print is on. We place the semicolon needed and we will start the simulation. Here we have the serial monitor, and notice that it is displaying a value of 0. This is different from the value we specified here, which is false. Why is this happening? Well, basically, the value behind this false is a value of 0. If we were to write true instead of false, notice that when we start the simulation, it displays a value of 1. Thus, 1 represents a true value, while false represents a false value. Let's stop the simulation. This is to make it a bit more readable for us regarding what this variable is doing. However, we could directly assign 1 to a Boolean variable, and notice that automatically it would also display a value of 1. Alternatively, we could assign that it's on equal to 0, and the output would be a value of 0. On the other hand, if we wanted to assign a different value of a non-Boolean type to this variable, for example, if we wanted to assign a character, notice what happens. We start the simulation, and here we have a displayed value of 1. However, even though our simulator did not show an error, we are unsure about what this letter A represents. Is it representing a true value or a false value? Even though it displayed that we have a true value, we really do not know for certain what this character A represents. Therefore, I always recommend that you write either a true value or a false value as part of Boolean variables. So instead of a character A, let's write a true value. And with that, we have a variable that is well identified and properly initialized with a Boolean value. To fully understand the if control statement, we first need to learn or recognize certain operators that we will be able to use with this control statement. In fact, these operators are extremely important when creating your sketches, as they will allow you to execute different conditions to determine whether one thing is happening or another, or to know if we are going to execute a certain instruction or another set of instructions. Let's first get to know an operator called the NOT operator. Let's add a comment here indicating that this represents Boolean variables. Later, we will write another comment to indicate that we will learn about the operator called NOT, which is represented by an exclamation mark. This operator will allow us to negate a Boolean value. This means that if you want to represent a true value and apply this operator, you will get a false value as a result. Let's see this in practice. Here we indicate, for example, that we have a variable called icing. And below this NOT, we will state that we want to assign to the variable icing, which is the same variable we have here, the value that is equal to the negation of icing, followed by a semicolon. Here, we are directly applying this operator to the variable called icing. As we mentioned earlier, the NOT operator negates the value we have in this variable, meaning we would equivalently negate the value true, since that is the value assigned to this variable. This would then result in a false value. Let's return these values and let's see it in a practical way. We will keep this serial begin at the beginning before creating this variable, and we will move this serial.print to the end to perform different tests. So we will print the value of this isOn to see what is displayed. First, we will clear what is in the serial monitor to avoid incorrect information. Let's start the simulation. Notice that we have a 0 value or a false value after applying the NOT operator to the isOn variable. This is how we can negate a Boolean value or a variable with a Boolean value using this operator called NOT. Now, let's explore the equality and inequality operators, which will determine if a value is the same in a pair of comparisons. Next, We'll write a new comment after this not assignment to describe the equality operator, as it will be the first operator we cover in this lesson. The way this type of operator works is as follows. I will declare a new variable. Let's call it is equal 1. This will be equal to 42. And the equality operator is represented by two equal signs, meaning two symbols equal to the one we have here. We will then write equals, and we need to write a second number or value that we want to compare. For example, let's perform a comparison of 42 against 42. And what we'll do here is ask if 42 is equal to 42, with the result of this evaluation being directly assigned to the variable called is equal 1. So remember, this equality operator will return only a Boolean value, true or false. In this case, the condition is true, therefore, this equal 1 should have the value of 1. Let's copy the name of this variable and write it to our serial monitor. We will clear the content, start the simulation, and notice that we indeed have a value of 1 as the output or assignment of the variable is equal 1. Now, let's try a different test. We will change this value to 43. When asking if 43 is equal to 42, what do you think the resulting value in the variable is equal 1 would be? The resulting value would be 0, since 43 is not equal to 42, meaning this evaluation is false. Let's see it in action. Indeed, here we have a value of false. Now, let's look at the inequality operator. This works in a very similar way. We will create a new variable equal to 42. To establish this operator, we have to use a not symbol and the equal symbol. So what we are doing here with this pair of symbols is asking, is 42 not equal to 42? In other words, we will have a final result that is different from asking, is 42 equal to 42? If you remember, 42 is equal to 42 is a true value. However, since we are asking if it is not equal to 42, the result must be a false value. Let's verify this. We copy the variable name, paste it into serial, print, erase the content, and start the simulation to see the result of this operation. We see that we indeed have a false value as part of the output from this assignment that we see here. If, on the other hand, we evaluate a different number, for example, is 43 not equal to 42, we would have a true value, since 43 is indeed not equal to 42. Let's start the simulation to see this, and we see that we indeed have a true value as output. Let's clear the console output, stop the simulation, and now let's do one last exercise, but this time with variables. Suppose we have an integer variable named number 1 that is equal to 100, for example, and we create a second variable that is also equal to 100. We could have a third Boolean variable called is equal 3 that is equal to whether number 1 is equal to number 2. What do you think we would get as a result of this operation? The result would be true, since this is equivalent to having number 1 equal to 100 and number 2 in the same way being equivalent to having 100. Therefore, if we copy the variable name and paste it into serial print, we indeed have a true value as number 1 is equal to number 2. If we replace the values of these numbers 100, we have here with number 1 and number 2, and start the simulation, we see that we have again a true number or a true value. The type of operation we see here, where number 1 equals number 2, is one of the most common operations you will see in your sketch. Typically, we do not directly compare numbers. Instead, we compare the values of two different variables to determine if they are equal or not, or if a condition has been met. Now let's learn about logical operators, which will allow us to extend the use of equality and inequality operators to compare two or more expressions. We will then refer back to our sketch, and after the equality and inequality operators, we will write a comment to see what these logical operators are. The first operator is called AND, represented by two ampersands, as we see here. We also have a second operator, which is OR, represented by a double pipe symbol. As you know, AND means Y, and OR means O. Let's look at an example of the first operator called AND. We will proceed to declare a variable named logical that is equal to, here's where we will utilize previous knowledge. That is, using the equality operator and the inequality operator to concatenate different expressions and achieve a resulting value of true or false based on these comparisons. Let's conduct some comparisons. For example, we will compare if 3 is equal to 3, and as you might expect, the value of this assignment is true. However, with the operators we have seen before and or, we can concatenate more expressions to create a set of validations and determine if the result of all these comparisons is true or false. In this case, we will write the AND symbol. This will help us concatenate a second expression. As the second expression, we can ask if 4 is equal to 4. What this operator does is validate if all expressions are true. If all are true, we will return a true value to this variable named logical. We can concatenate as many expressions as we want. For example, we can append a third expression stating that 5 is equal to 5. Remember to place a semicolon at the end. So what we will do here is compare this expression, and as you will notice, it results in true. Subsequently, with this AND, we compare true and see that 4 equals 4, which also results in true, and 5 equals 5, which again results in true. Therefore, since all these expressions yield a true result, the variable logical will hold a true value. In the event that just one expression does not hold true within this set of expressions, the result of this variable will be false. For example, if we compare 4 equal to 3, even if the first expression evaluates to true and the last expression evaluates to true, we have an expression that yields a false value. Therefore, our AND operator indicates that we must return a false value for this variable, since one of the expressions has not been fulfilled. That is, if any one of the expressions does not hold, the entire result will be false. Let's test it. We'll copy the name of a variable, paste it in serial.print, clear the content of the serial monitor, start the simulation, and as you can see, we indeed have a false value. If we change this value from 4 equal to 3 to 4 equal to 4, it causes all expressions to be true. We will have a true value since all conditions are true, and therefore the value of this assignment will be true. Let's examine the second logical operator, called OR. To perform this exercise, we will declare a second variable named logical2 that is equal to, and we will start making some comparisons. For example, 3 equal to 4. We apply the OR operator, and in parentheses again, 4 equal to 4. We place the semicolon, and what we're going to do here is compare if 3 is equal to 4 or 4 is equal to 4. What is the purpose of this OR operator? Well, this OR operator helps us determine that if any one of the expressions is true, a true value should be returned to this variable called logical2. In other words, if any of the expressions is true, this logical2 variable is assigned a true value. The only case in which the result of logical2 will be false is when all the evaluations are false. In this case, we ask if 3 is equal to 4, which gives us a false result. However, in the second expression, we have a true value, which is 4 equal to 4. Therefore, since one of the conditions is true, the value of logical2 will also be true. As you can see, the difference between and OR is that and requires all expressions to be true, while OR only requires one expression to be true in order to assign a true value to this variable. Now, let's analyze relational operators, which you will surely remember from your math classes in school. We will recognize these operators as they are represented by the symbols for less than, less than or equal to, and greater than or equal to. We will do some practical exercises to see them in action. Suppose we declare a variable called age that is equal to 30, and we create a second variable called result that is equal to. Here we'll use two different values to carry out this comparison. In the previous section, where we discussed equality and inequality operators, we directly compared two values on the extremes to determine if they were equal or not. With relational operators, we can perform another type of comparison to evaluate different ranges of values. As part of the assignment for the result variable, we can ask, is age less than 30? Here we will evaluate whether age is less than 30. In this case, the value of age is equal to 30, so it is equivalent to asking if 30 is less than 30. And the result of this is false, as 30 is not less than 30. It is equal to 30. Therefore, the assignment of this result value would be false. If, in this case, we wanted to consider the value of 30 for the range we are handling here, we could use the less than or equal to operator. In this case, since age is equal to 30, this would yield a true value, as 30 is less than or equal to 30. For the greater than operator, we simply need to replace it with, is age greater than 30? In this case, 30 is not greater than 30. So the answer is false, as 30 is again equal to 30. If we wanted to consider this value of 30 as part of the comparison we have here, we could indicate that age is greater than or equal to 30, meaning that the value of age, which is equal to 30, would be included in the assignment we have here. Therefore, it would return a true value for this assignment we have here. Let's print it quickly to see it in action. Okay, and as you can see, we have a true value here, indicating that 30 is indeed greater than or equal to 30. We must be careful to know whether we will consider the value on the right in our operation using the greater than or equal to or less than or equal to operator, or whether we will only compare the ranges upwards or downwards using greater than and less than. This is the use of relational operators. Once we know the different operators that we can use as part of programming in Arduino, we can move on to the next point, which is to analyze the if control structure. Let's proceed to comment on all this code we have here. Remember that we can comment in a multi-line format by placing this pair of symbols, and we can also close it with an asterisk and a slash. Okay, with this, we have commented on everything we did in the previous videos, and we are ready to proceed. The only thing we need to keep available is this invocation of the configuration method. The if control structure will help us compare a set of values to determine if certain conditions are met and carry out specific execution if these conditions are met, along with another set of instructions if these conditions are not met. To use this control structure, we will write the keyword if, and within parentheses, we can write the expression or set of expressions that we are going to evaluate. If you've noticed, I've also written a pair of braces to specify inside what instructions we will execute if the set of conditions is met. So, inside this if statement, we could ask very simple questions, like, for example, is 5 equal to 5? Here, as you can see, we are using one of the operators we reviewed earlier, which is the equality operator. We are asking if 5 is equal to 5, and as you may recall, this gives us a true value. Therefore, this condition is met, and the series of instructions we have here will be executed. We can perform a very simple task, such as turning on an LED through a digital grid. Let's turn on, for example, LED number 3. We assign it a high value, start the simulation, and notice that we are indeed turning on one of the LEDs corresponding to LED 3, which is actually assigned to port or pin number 11. In case the condition of the if statement is not met, we will simply continue executing the sketch. There may be occasions when you want to perform a different execution if this condition is not met. For this case, we will use another keyword called else. We also write an opening brace and a closing brace, and inside, we will write a series of instructions that will be executed if the instructions we see here are not met. As I mentioned earlier, within this if statement, we can have a series of expressions. For example, we can ask if 5 equals 5, if 4 equals 4, and if 1 equals 2. In this specific case, as you can see, we have a condition that is not met. Let's see then if our LED turns on or not. We see that our LED is not turning on as part of the evaluation of this if condition is not being met. Therefore, the final result of all these operations will be a false value. This first if will only execute if we have a true value as the result here. So as part of this else, we can carry out a different action. For example, turn on our LED number 1. When we start the simulation, we see that our LED number 1 turns on. This is because this series of expressions corresponding to our if statement hasn't been fulfilled. Remember that STLs are entirely optional. If you only want to evaluate a certain condition to execute or not, you can skip STLs. However, if you want to force the execution of another set of instructions, in case these instructions are not met, then you can write STLs without any issues. Remember the syntax. If, parentheses, and inside the parentheses, the set of expressions you want to evaluate, followed by a series of braces. And then inside these braces, a series of instructions to carry out the execution in case this set of instructions we evaluated is met or not. With what we've learned so far, I assume you were assigned this task that we see in the box here. The instruction states that each LED is represented as follows. The LED on pin number 13 has a value of 1. The LED on pin number 12 has a value of 2. The LED on pin 11 has a value of 3. And the LED on pin number 10 has a value of 4. The specific task is to light up the LED corresponding to its value based on an input value stored in an integer variable called LED encendido. In other words, this exercise tells us that we need to declare a variable called LED encendido, assign it a value, and based on the assigned value in this variable and the information provided above, we will light up one of these pins. For instance, if we assign the value 3 to the variable LED encendido, which, as you remember, is an integer variable, then we would need to light up the LED on pin number 11. This is because the value 3 corresponds to the value of the variable LED encendido. With what we know so far, we would have a flowchart similar to the one we have here. We would create the variable, and then we would create an if condition and ask if LED encendido, which is an integer variable, is equal to the value 1. If this condition is met, we would light up LED number 1. But if you remember, we can only establish one if and one else, in case this condition is not met. However, as you can see from above, we have a set of other comparisons that we want to perform. We want to compare against the number 1, the number 2, the number 3, and the number 4. Therefore, with what we know so far, we cannot solve this problem. Let's get to know a new control structure that is very similar and allows us to expand this tree we have here. This is the else if statement. By knowing this control structure, we have something similar to what we see here. As you can see, we now have a larger tree. What this allows us to do is to perform something like what we have here. We check if the variable LED encendido is equal to 1. If so, we turn on LED number 1. However, since we have assigned the value 4 to the LED encendido variable, this condition is not met. Therefore, we'll move on to the next comparison, which is the else if statement. What this will allow us to do is ask a second question. So, if LED encendido is equal to 2, and if this is true, we will turn on LED number 2. But in our case, since LED encendido is not equal to 2, but instead equal to 4, this condition is not met. Therefore, we can skip to another of the questions and ask again. So, if LED encendido is equal to 3, and if this were true, we would turn on LED number 3. But again, this is not met in our case. So we must go to the last comparison we have here, where we ask if LED encendido is equal to 4, and if this is true, we would turn on LED number 4. If this condition is not met, and since we have no more comparisons, we will turn on all the LEDs we have as part of our circuit. Let's return to Tinkercad. We will create a multi-line comment. We will create this multi-line comment to summarize what we did in the previous video and start from scratch. After configuring the pins for our order, we will solve this exercise. As you may remember, the first task we completed as part of this diagram is to create a variable called LED encendido, which has a value of 4. Let's declare this variable, int LED encendido equals 4. The next step is to compare LED encendido against the value 1. If this condition is met, we will turn on LED number 1. So let's check if lead encendido is equal to 1. Remember that we need to use a double equal sign to perform a comparison. If we wrote a single equal sign, we would assign the value 1 to lead encendido. So be sure to place a double equal sign to check if lead encendido is equal to 1. In this case, it would look something like what we have here. If 4, which is the value of lead encendido, is equal to 1, then we would turn on our LED 1 using digital write. We set the value to high. But as you can see, this if condition is not met since 4 is not equal to 1. Now, as you may recall, what we previously knew was to use an else. However, to expand our scope or the tree of different comparisons we have here, we will add a space to this else and then ask again with an if for a second condition. The second condition is that lead encendido is equal to 2. And within this, we will write a set of operations in case this condition is met. In our case, we will turn on LED number 2. As you can see, this else if that we have here allows us to perform a series of evaluations to see if certain conditions are met and execute specific actions if they are. We can write another else if in case neither this condition nor the other condition is met. Since 4 is not equal to 2 in this second condition, we can ask again, else if LED 3, and we will write digital write for LED 3 high. As our condition is still not met, since 4 is not equal to 3, we can create another else if, asking if LED on equals 4. And here we will write digital write LED 4 with a high value. In this specific case, the condition would be met since 4 is indeed equal to 4, and thus we could turn on our LED number 4. In fact, if we test our simulation, we see that the LED that lights up is LED number 4. If we change our LED on variable to a value of 3, for example, we see that the LED that lights up is LED number 3, and so on. Here we have LED number 2 and LED number 1. What would happen if we entered a value, for example, 8? As you can see, none of these expressions are being met. Therefore, we would skip this entire if structure and continue executing the corresponding code of our sketch. But if we want to be more precise and carry out a series of actions, in case these conditions are not met, we can create an else. This else will allow us to execute a series of operations in case none of these conditions are met. In our case, if you remember, in our diagram, we specified that if none of these conditions were met, we needed to turn on all the LEDs. Therefore, that's what we will do. Here, as part of this sketch, we have a method called EncenderLEDs, which turns on all the LEDs. We will invoke this function. We invoke this functionality, start the simulation, and notice that we are indeed turning on all the LEDs since none of the previous conditions have been met. This is how we can create something called nested ifs. As you can see, it is a series of ifs that are stacked one after another, and the tree we see as part of the flowchart is structured this way. You can see that we are nesting different ifs each time we create additional conditions. Reviewing what we covered in the last lesson, we had something called nested ifs, which actually adds complexity to our code. What we're doing here is evaluating a variable, comparing it, and carrying out different actions based on whether that condition is met or not. In the Arduino code, we have a set of else-if statements, which may seem a bit straightforward since we have only one instruction being executed. However, if we had a set of instructions that we wanted to execute depending on whether one of these conditions was met, it would create more complex code. To solve this issue, we have an alternative, which is the structure called switch. The control structure called switch looks like this. As you can see, it represents this problem in a simpler way. Well, here we have nested evaluations. In this case, we only have a tree that is at the same level for each evaluation, allowing us to easily see the result when a certain condition is met. Let's take a closer look at this diagram. We have the creation of a variable called lead encendido, which in this case is assigned the value of 4. Here, we evaluate the variable lead encendido. How do we carry out this evaluation? Well, Just like an else if instruction, we ask if the value of lead encendido is equal to 1. And if this is true, we turn on LED number 1. Or we check if it is equal to 2, and if this is true, we turn on LED number 2. As you can see, we are evaluating the different expressions here. We even have an instruction that allows us to specify in case none of the previous evaluations are met. And in this case, we learn all about the LEDs. Here, in a simpler way, we can evaluate this variable, LED on, to match it with a number 4 its corresponding evaluation. As you can see, we can quickly see that this conditional equals 4, which is the one that most closely resembles the condition we have here. Therefore, we will turn on LED number 4. This is different from our previous tree structure. Here, we had to traverse the entire tree to know when we reached this specific condition. How does this look in code? Well, let's go back to our Arduino sketch, and let's comment out what we had previously. We will place a multi-line comment. Let's go back to the top after invoking the configure method. To create this control structure, we will write the keyword switch, followed by parentheses and an opening and closing brace. What we will do inside this switch is specify what we want to evaluate. And within those braces, we will place the different cases that will evaluate the expression associated with the switch. We will copy this variable called int ledon, as it is the first step in our sketch. Let's assign it a value of 4, for example. As I mentioned earlier, within this switch, we need to specify what we want to evaluate. In this case, it is advisable to use a variable. We will evaluate our variable called ledon. Without further ado, we will not place any type of operator. We will only specify what we want to evaluate. The way to evaluate a switch is through something called cases or a case. So we will write case. And after writing the word case, we will specify the value we want to match or check against the value of this variable LED on. If you remember in the conditionals, we compared our variable against numbers 1, 2, 3, and 4. Well, we will do something similar here. However, instead of placing an equality operator, we will directly place the number, in this case, the value 1. After this, we will place a colon in the series of instructions we will execute if this condition is met. As you can recall, if the condition that LED on equals 1 is met, we needed to turn on LED number 1 through digital, right, with a high value. To recap, within the switch, we're evaluating the value of LED on. That is, it would be equivalent to having these switches evaluating the value 4. Within the switch, we are placing a case to evaluate the different scenarios in which this value we have here could fit. In this case, since this 4 is not equal to this one, this will not be executed. Since this does not execute, we need to write a series of additional cases that we want to compare in order to meet all possible conditions. So we'll copy this line and paste it 3 more times. What we will do here is change this case value to 2, 3, and then to 4. We will indicate that in the event this condition is met, we will turn on LED number 2. If this condition is met, we will turn on LED 3, and so on. Okay, we have this ready. Now, let's change the value 4 to the variable LED on. For this test, we will change the value 4 to 1. Theoretically, what should happen here is that we evaluate the variable LED on. And when there is a match for this case with the value LED on, which in this case should correspond to this line we have here, only LED number 1 should turn on. Let's see if this is true. We will start the simulation. But notice that at this moment, all the LEDs are turning on. Why is this happening? Well, in the case of the switch, what happens is that if we do not place a keyword within these cases, they will execute one by one, according to how many we have declared. The keyword we need to place is the word break. This will break the execution of this switch and skip to the end, so it will not execute the remaining cases we have here. Let's then place a break at the end of each of the cases so that we do not have any issues. Let's start the simulation, and notice that now we are indeed only turning on LED number 1. This also happens if we change the value of this variable to 3. For example, here we turn on LED number 3. Well, what would happen if we assigned a value of 5 to this variable? Okay, we see that nothing turns on, and in our diagram we indicated that in the event these conditions are not met, we should turn on all the LEDs. We will achieve this thanks to a special case defined by a keyword called default. This default will execute when none of the conditions stated above are met. Therefore, if no condition is met, we will invoke our function and send our LEDs. Now, let's start the simulation, and we can see that we are successfully illuminating all the LEDs in our circuit. The push-button component, or simply button, is a component found in countless places, although it is commonly seen in electrical and electronic systems. You have likely interacted with them. After all, who doesn't remember playing with those classic machines? Or you use them constantly when doing calculations on your calculator. In the case of the simplest buttons we can find for our electronic practices, this is their internal structure. The button is equipped with a spring that can be either pressed or released. Thanks to this spring, in this image we can see that the pins aligned in the same direction are connected internally while those parallel to each other are not connected. When the button is pressed, the parallel pins connect, allowing us to close the circuit. Here we have another image that demonstrates what we have discussed so far. In the image, we see the most common representations of a push-button component in an electronic diagram, clearly showing that the circuit does not close unless the button is pressed. Let's move on to the practical part and explore the push-button component. We are now in Tinkercad, and we'll examine the component called push-button in a practical way. What we'll do first is search for a flat 3-volt battery. We will drag it onto the circuit, and the next thing we'll do is drag an LED and a resistor with a value of 220 ohms. Now that we have these components, let's start by flipping the battery. Similarly, let's also flip this resistor that we have here. This is for creating a circuit. Let's drag our resistor and the LED as well. We will connect the anode of our LED to the resistor. Let's connect the positive terminal of our battery to the right side of the circuit we have created. We will color this wire red and connect the cathode to the negative side of our battery. Let's color this wire black. If we start the simulation now, we see that our LED is functioning or lighting up satisfactorily. Let's stop the simulation and integrate a push button as it appears here in Tinkercad. Let's drag the component, remove the wire we created earlier, and place this push button in this position. Next, let's connect terminal 2 to this pin, terminal 1B of our button, and connect terminal 1A of the button to our battery at the free terminal. Let's color these wires red and see what happens when we start the simulation. We see that satisfactorily, we are lighting up our LED again. This is happening because, as you may recall in the slides, we mentioned that these pins we have here are connected to each other. Now, if we remove this wire here and connect the wire to terminal 2A, as it appears here, let's connect our battery. Color the wire red. Notice what happens when we start the simulation. Our LED is not lighting up because, as you may recall, the pins on the left and the pins on the right are not connected, and the connection will only take place when we press our button. So, if we press our button, notice that our LED is lighting up satisfactorily without taking any other action. And this is because the pins on the left are being connected to the pins on the right. This is how a push button works in practice. Now we will proceed to study a method called digital read. As you may recall, we previously studied a method called digital write, which allowed us to change the output voltage of one of the digital pins. In the case of digital read, this method will allow us to read the voltage present on that pin. We will test it in a very simple way by using the same diagram from the previous lesson, and we will drag an Arduino Uno board. We won't connect any additional components. We will simply go to the code section, specify that we want text code, remove the default code, and in our loop method, we will declare an integer variable called lecture that is equal to invoke the method digital read. Here we can read any digital pin, for example, pin number 12, which as you can see is not connected to anything. Now we will proceed to use our serial class, and for that, we need to initialize it first via serial.begin 9600. Once we have obtained the reading from this digital pin, we will print its value using serial.println and the value of lecture. If we start the simulation right now and look at the serial monitor, notice that we have a display of a set of values, 0. This means that our pin number 12 is not energized, or it has a value of 0 or a low value. Let's stop the simulation and clear the console content. Now let's return to our development board and proceed to connect pin number 12 to the pin marked 5UB. If we restart the simulation and go to our serial monitor, you'll notice that this time we have already displayed an output with a value of 1. This means that our pin has a high value, which is because we are directly powering this pin with the 5-volt pin. With the knowledge we've acquired in the previous videos, we're now ready to integrate a push-button component into a project. The final project will involve having an LED, a button, and when this button is pressed, we will send a signal to turn the LED on or off according to the button's state. Let's then integrate our first components into the project. The first component we will integrate is a development board Arduino. We will also integrate a development board. In this case, it will be a small prototype board. Lastly, we will drag a button component onto the board. The button on the proto board is typically placed in this middle section, as this allows us to connect the two sections of the proto board and save space. If we positioned it this way, notice that we would lose some space since the push button occupies a certain amount of space. However, if we place it in the center of the proto board, notice that it does not take up much space and fits perfectly. With these components, we'll connect the terminal called 1A to the negative rail and connect the LED called terminal 2A to one of the pins on our Arduino, which in this case will be pin number 8. Let's use different colors for our wires to distinguish them. Finally, we will connect the rails to our Arduino. First, let's connect the negative rail to the pin labeled as GND. If you double-click on our wire, you can create a new bend in the wire for better designs. Let's color this wire black and connect the positive rail to our pin labeled as 5-volt. Let's do the same. We will create different connections to improve the visibility of our circuit. And we will color it red. Okay, with this, we are energizing our rails and have connected our button. The objective, first of all, is to test our button and see that it functions correctly in code. We'll go over some theory later. For now, let's move to our code section. We will remove this setup section and this piece of code from our loop. Instead, let's declare a constant of the integer data type called pushPin, which will be equal to 8. This variable will represent pin number 8 on our Arduino ID. In our setup, we will configure this pin using pin mode. Pushpin, comma, and we will set it as input, since what we want to do is read the value of this pin. We do not want to modify it to perform actions outward, as we did before when we changed the value to either high or low to turn on or off an LED. In this case, we want to read the pin state, which is why we configure the pin mode as input. We will also initialize our serial class using serial.begin 9600. The next thing we will do in our loop is create a variable called pushSignal, which will be equal to digital read of pushPin. As you may recall, this method will read the value of the digital pin, in this case, pin number 8. We will print the value of this variable using serial.println, passing pushSignal as a parameter, which will be the value we read from our pin number 8. Let's start the simulation to see what happens with this diagram or with this project we have here. If we look at the serial monitor, we see that we have an output with values of 0. What I ask you to analyze is this really correct? Take a look at our diagram. We have an output This digital pin, by default, has a low value, or a value of 0. What we are doing is tracing through our circuit with a value of 0. We reach this line and our button, but as you may recall, our button does not have a direct connection to this line here, to this column. Instead, we bypass it since we only have these two terminals connected. Therefore, what happens with this pin we have here? This is called a floating pin, as we really have no certainty about the state of this leg. It could be in a high state or a low state. We really don't know, since with the slightest interference, we could read either a high or low value on this leg. Even though we cannot see it clearly in the serial monitor of our Tinkercad-based project, we can see what happens in the physical world. Let's recreate this same project, but in a real setup. We start by connecting our G&D pins and the pin marked for 5 volts. These pins go to the breadboard where we connect them to the corresponding rails. Next, we connect our button, or push button. Remember, we connect it in the center of the proto board. We connect one of the left pins to the negative rail, and we connect a jumper from the output of the right pins directly to pin number 8, just as we did in Tinkercad. Remember, this is everything we did in Tinkercad. Once we have made the connections, we will upload our sketch to our Arduino board and check the serial monitor. Okay, as you can see, we are not certain whether we have a high or low value as part of the output. We have a set of zeros and a set of ones in a random manner. This is what our Arduino is returning to us once we read the corresponding pin. What this means is that we won't be able to satisfactorily control whether the LED is turned on or off. Let's see this in practice. We will return to Tinkercad and integrate an LED. For that, we go back to our circuit, look for an LED component, and place it on our proto board. We connect the cathode to the negative liner rail, color the wire black, then drag a resistor, flip it around, position it at the anode line, assign it a value of 220 ohms, and connect this column of our anode directly to pin number 13. Once we have added our LED, we will return to the code and modify our sketch to control whether our LED turns on or off. Let's begin by defining a new constant, which will also be an integer named LED pin equal to 13, as it is the pin we want to control. We will initialize this pin, LED pin, through pin mode with an output value, as we want to modify this pin's value to turn our LED on or off. In our loop method, once we have performed the push signal print, we will check if push signal is equal to low. In the case that we receive a low signal on this pin, we will indicate that we wish to send a digital write signal on LED pin with a high value, meaning we'll turn our LED on. Otherwise, we will send a signal to our LED pin with a low value. Okay, with this change we made, let's see how our simulation looks in Tinkercad. We can see that it appears as if the LED never turns off. Even if we press our button, the LED remains on. Why is this happening? Well, let's observe it physically for better understanding. First, let's carry out the physical connections so you can do it too if you wish to recreate this project. First, we connect our LED. In this case, the anode is the right leg and the cathode is the left leg. We add a resistor to our anode. Then we connect the cathode directly to the negative rail of our protoboard. Next, we connect a jumper in the same line as the output from the resistor that connects with our anode. We connect this jumper to pin number 13 on our Arduino board. Once we have uploaded the same sketch to our Arduino board, and with these connections, notice that we have an LED that blinks while we do not press our button. If we press the button, this blinking disappears. However, this is definitely a problem, since our LED blinking indicates that a satisfactory reading of our button cannot be carried out. And this is a result of what we saw earlier on the serial monitor. The series of zeros and ones that appeared on our serial monitor is causing the behavior we see in the video. The solution to this issue is to integrate one of the two possible resistor configurations. we have a configuration called pull up and one called pull down. What these resistors will do is solve the problem I mentioned earlier, since, if you remember, I pointed out that we did not have a satisfactory output from this terminal here. In other words, we have a floating pin, as we are not certain about what needs to be done with this terminal here. What we will do is ensure that we have either a value of 1 or a value of 0 at the output of our pin number 8, depending on whether the button is pressed or not. We'll start by looking at a resistor configuration called pull-up, which, as its name suggests, pulls the voltage up. As you can see at this moment, when the button is pressed, this circuit closes. But as you may recall, we have 0 volts output on pin number 8. Therefore, without a potential difference when the button is pressed, we actually read a low value. What we need to do is indicate that when this button is not pressed, we read a high value. How do we achieve this? Well, we will connect a resistor. With a value of 1 k ohm, it's perfect. Let's flip our resistor. We will insert it in the same line between the button and our cable that connects to pin number 8, and we will connect this resistor to the positive rail of our circuit. Let's color it red. And what this will do is ensure that as long as this button is not pressed, the current will follow this path. It will start from pin number 8, follow this path, reach the resistor, move to this line, and go directly to the positive rail. As you may remember, we have the rail powered with 5 volts and this pin powered with 0 volts, which creates a potential difference and causes this pin to actually output 5 volts. So when this push button is not pressed, we will have an output with the value high. And in our code, if you recall, what we will do when we read this value is turn off the LED. Therefore, by default, we will have an LED turned off. In the opposite case, when we press this button, having 0 volts at the output of the pin and a negative load, that is 0 volts and 0 volts. When we press the push button, we will turn on our LED. This works this way because current always seeks the path of least resistance. Therefore, upon encountering greater resistance here, the current will be directed straight to our button, which is why this circuit will close. Let's start the simulation to see how this looks. Notice that immediately our LED no longer lights up, which is a good thing. If we press the button, notice that our LED is lighting up satisfactorily. Remember, this is the pull-up configuration, which means we will pull our circuit towards 5 volts. Let's stop the simulation and look at the configuration called pull down. In this case, what we want to achieve is to lower the voltage to 0 by default. That is, when the button is not pressed, we have 0 volts at the output, and when we press our button, we have 5 volts. Let's go ahead and create this task. So let's remember, we start with 0 volts. It makes sense to think that instead of energizing or going to the rail marked with 5 volts, we go to the negative rail. This is what we're going to proceed to do. Let's change the color to black. And with this, we will have a default initial output of 0 volts, since 0 volts here and 0 volts on our pin do not create a potential difference. Therefore, we will read a low value by default. But here we have a problem that we have created, which is that if we press our button, we will have 0 volts on the pin output and 0 volts on the rail, which will cause the same behavior as if we do not press the button. Therefore, we need to modify this, and what we want to achieve is the opposite of what we are currently causing. That is to raise the voltage on our pin to 5 volts. We will achieve this by connecting to the positive rail instead of the negative rail. Let's drag our wire to the rail marked with positive. Change the color to red. And with this, when the button is pressed, we will have 5 volts on one of the outputs of our button. And we will have 0 volts on our pin marked with an 8, which will create a potential difference, allowing us to read a high value. Let's start the simulation to test what we have done. Notice that, indeed, by default, we are already lighting up the LED, and if we press our button, the LED turns off automatically. This is the pull-down configuration. This is how we have successfully completed this project to turn an LED on or off based on the status of our button. If you want to see it physically, here we have the connection of the resistor we added for the pull-up configuration. Here we have connected our 1 kilo ohm resistor. Here we have the connection to the positive rail. Here we have our project in action. Notice that while the button is not pressed, we have an LED that is off. Once we press our button, we can turn on the LED, allowing us to control when it turns on and off. On the other hand, in the pull-down configuration, we need to connect the output of our button to the negative rail. Additionally, we will connect the other pin of our button to the positive rail to create the opposite effect of what we had in the pull-up configuration. Here you have the project running. Now we have our LED turned on by default, and if we press the button, we can turn this LED off at will. To carry out the project for this section, we need to understand the component called buzzer, also known as a beeper, speaker, or piezo. They come in various shapes and sizes, but fundamentally, they all work the same way. If we were to open a buzzer, we would see something like the image on the screen. The part that makes the buzzer work is the disc highlighted with a red arrow. It is a piece similar to this. This disc is made up of two parts, a ceramic disc and a metallic plate that surrounds it, usually made of bronze. When current is applied to the buzzer, it causes the ceramic disc to contract or expand, which causes the external metal disc to vibrate. This vibration is actually the sound we hear coming from the speaker. If the frequency of the buzzer is changed, the speed of the vibrations changes, which alters the resulting sound. Let's see how the buzzer operates in Tinkercad. We are now in Tinkercad. What we'll do this time is search for a component called piezo, which is basically a buzzer or a beeper. We will drag it onto our surface, and we'll also look for a battery. Let's find the flat 3-volt battery. As you can see, our buzzer has two leads, one positive and one negative. The only thing we need to do to get our buzzer working is to supply it with current. So let's flip our battery, and all we will do is connect the positive side of our buzzer to the positive side of our battery, and we'll do the same with the negative side. Let's change the colors a bit for better visibility. Let's start the simulation. With this, we can hear a buzzing sound that is coming from our speaker here. As you can see, the operation of the buzzer is really simple. We just need to apply current to our speaker for it to function and produce sound. We are going to create our next project, which is an electric piano. We will achieve this thanks to a series of buttons and a buzzer element. What we're going to do is simulate a piano. Here we have a piano, and we have different notes that sound different from each other. What we have here is called a scale of notes. We have the notes C, D, E, F, G, A, B, and C. What we're going to do is recreate the sound of the notes from C to B on a proto board. As I mentioned earlier, these keys will be represented by buttons or push buttons. Let's go back to Tinkercad and proceed to create this project. Let's remove these components from the last session, and instead we will drag a proto board. We will also look for our Arduino Uno board. As I mentioned earlier, we need a set of buttons, so we will drag our buttons. I will position the first button in the first row or first column, and I'll drag a total of 7 buttons, which means I need to drag 6 more buttons. Here I need 5, 4, 3, 2, 1, and that's it. You can see that I left one column blank for space. What I will do now is connect the left pin of each button to the negative rail. I will color the corresponding wire black. I will do this with each of the buttons. Perfect. Next, I will connect each of the buttons to an Arduino pin. I will start with the leftmost button and connect this pin to pin number 12. I will connect the second button to pin number 11, and so on. Okay, I have connected each pin of each button to an Arduino pin. Next, I I will also drag a speaker component, which we find as piezo in Tinkercad. Let's drag it to our diagram. I will proceed to flip my speaker. I will connect the pin marked positive to pin number 5. Okay, I will color the wire red, and the other pin, the one marked negative, I will connect to the pin marked D. I'll color the wire black, and the next thing I will do is power these rails on our proto board. So I will drag a wire from the pin marked D and D or ground, and I will bring it to the rail marked with the negative symbol. Of the proto board, I color the wire black, and now we have this connection as well. Okay, this is all we need to recreate this project and the electronics part. Now, let's proceed to create our Arduino sketch. Let's open the code section, indicate that we want to write text, remove the content from setup, and remove the content from our loop cycle. What we're going to do now is create a set of variables, each representing the pins we're using on our Arduino. We will start by specifying with an integer variable the pin where our buzzer is located. We will indicate that it is on pin number 5, and we will also declare an integer variable named noted_down. This is because the note do, or the initial note, will be this. The notes will be do, re, mi, fa, sol, la. Since the first button is connected to pin number 12, we will indicate that the value of this variable will be equal to 12. We will proceed to write each of the variables. Note E equals 11, note E equals 10, note fa equals 9, note sol equals 8, note la equals 7, note si equals 6. And with this, we are specifying a variable for each of the pins on our Arduino that are being used. The next step is to initialize the pin mode of each of them. So we go to our method called setup and proceed to write pin mode, indicating that our pin where the buzzer is located will be configured as output, since we want to modify our pin to receive current, allowing us to turn on this speaker. Subsequently, we will configure each of the pins of our buttons, starting with Notado, which will have an input pull-up configuration. Remember, this will cause the internal pull-up resistor configuration to be used, which is part of each of the digital pins on our Arduino. We will make the same configuration for each of the pins of our buttons. So, no tree, input pull-up as well. We can copy this line and paste it, modifying only this section of the notes. So, I write my fa, sol, la, and si. With this, we have finished configuring the pin mode for each of the pins on our Arduino. It's good to test before proceeding to ensure we have no errors. If we start the simulation and it indicates no problems, it means everything is good. If you have any errors, you need to ensure that the names match and that this pin mode definition is just as we see here, input pull-up. Okay, let's move on to our loop method. I will leave some spaces here for better visibility. And what we will proceed to do in our loop method is to check if digital read of note is low. What we're doing here is reading the state of our digital pin. In this case, where our button representing note 2 is located. This means that this is pin number 12. Remember, this first button represents note 2. So if the button is pressed, that is when this action will take place. Remember that we have an internal resistor, which means that when this button is not pressed, we will have a 5-volt output, creating a potential difference, resulting in a default high state. When we press the button, we see that we have 0 volts at the output of pin number 12 and 0 volts on this rail. Thus, there is no potential difference, and we would execute this section that we see here. So, in the event that the button is pressed, what we want to achieve is to make our buzzer sound. We will indicate digital write to send power to our Arduino pin output, and we will specify buzzer, comma, high. Ideally, this note should last only an instant and not sound indefinitely. Therefore, we will place a delay of 5 milliseconds here. What we will do is once we stop the execution of our sketch, or once this if statement is executed, we will indicate that we want to turn off our buzzer. We will do this by using digital write with buzzer and a value of low. If we start the simulation now, notice that if we press our first button, we already have a sound coming from our speakers. This sound is produced by the buzzer we have here. Okay, we're doing well. Let's stop the simulation, and we will write the condition to detect when each of these buttons is being pressed. What we'll proceed to do is copy this line of the if statement, the digital write, no, just the if section, and we'll paste it, changing this note to note underscore underline R. We will do the same for all the notes. In this case, note underscore MI. We will paste this section again, and we will compare note FA. We will do this again, but with note SOL. We will do this once more with note LA. Finally, we make one last connection, but comparing the note. With this change we made, if we start the simulation, notice that if we press any of these buttons, they sound satisfactorily, except for the second button we have here. Since we have a bad connection here, we've connected it to the column between the two pins, which is incorrect. We're going to change the position, and with this change, this button should sound as well. And indeed, it is sounding. Okay, we are progressing in our project. However, when we press one of the buttons, we see that it always produces the same sound, and that's really not what we need. What we want is to emit a different sound, just as we saw on the digital piano we have here. If you play one key or a different one, it produces a different sound. So this is what we want to achieve with our electronic piano that we see here. How can we accomplish this? Well, in the Arduino reference, we see that there is a functionality or a function called tone, which is already part of the Arduino language. This tone function briefly indicates in its description that it allows us to execute a different sound according to the frequency we specify. Here we have the syntax for using this method. If you look closely, it asks for a pin, which is basically the pin where your speaker is connected, and it asks for a frequency. What is this frequency about? Well, let's take a look at the link we have at the top, which takes us to a page called GitHub. And basically here we have a table with the different notes and their respective frequencies. We can take this table to execute a tone with a different frequency for each button. Let's perform this task. Let's return to Tinkercad. Let's look at the first comparison or the first if statement we have here, where we compare this note C. We will keep this table open, and we're going to look for the note C that we want. The note C in the musical scale is represented by the letter C. So let's look for some of the frequencies. For example, this note C4 means this is a musical note C in scale 4. We copy this number we have here, return to Tinkercad, and what we're going to do is change this functionality. Let's stop the simulation first. Let's change this method to tone. If you remember, the method accepts the pin where the buzzer is connected, which means this is correct, and we will change this value of height to 262, which is the frequency we saw on the GitHub page. If we start the simulation now, notice what happens if I press the first button. Okay, we have a sound that doesn't stop. This is because the tone functionality sends the signal, but we need to explicitly tell it to stop the sound using a function called noTone. Let's go down to the bottom, and instead of the digital write that we specified earlier, we will write the noTone functionality, which takes as its first parameter the pin where our speaker is, in this case, the buzzer. If we start the simulation now, press the first push button, and we have a brief sound that, as you can see, is different from the second push button. Let's stop the simulation and change each of the conditionals we have at the top. Following this nomenclature, we can copy this line and replace it in each of the comparisons. We only need to change the tone here. For the second tone, we need to use note and a base of 4. Let's copy this value and paste it. We copy this line again, paste it here in digital write, and move on to the next musical note, which is note and a base E4. We copy the value 303 and paste it here. We will copy this line again and paste it instead of digital write. Let's go back to the table and look for the note nod F4. We paste this value, and we'll do the same for this conditional note sol. Let's find the note sol, which is nod G4. We copy the frequency, paste it, copy this line again, and then look for the frequency of the note A, which is note A4, with a value of 440, and we copy this line one last time and paste it. Next, we will search in our table for the note called No B4 and copy the value 4094. If we start the simulation, let's hide the code. Let's focus on our project and notice that each of the buttons will return a different sound. We can even play some songs. With this, we have completed our electric piano. Once we see that it works satisfactorily, we will recreate this project, but in a physical form. Now, let's move on to our third beginner project with Arduino. On this occasion, it's a project that I personally like a lot because it relates to music. It's nothing less than a mini digital piano. Here, we can see it in action. We can manage the notes of a complete scale. The last button seen on the right, which appears to be abandoned, is actually a button that will allow us to play a pre-recorded song in the Arduino program. Ideal for when you want to drive your girlfriend crazy, right? To carry out this project, these are the components needed. A proto board, 9 push buttons, 19 mail jumpers. In my case, I will take 9 jumpers and swap them for 9 copper wires. You'll see why later. A buzzer, and finally, an Arduino Uno. With these components, we will look at the connection diagram for the project. Here we have shown the connection diagram of our project. Basically, we see that it is a set of buttons located in the center of the proto board, and each one has a specific function to play a note of a scale. In this case, we have the notes C, D, E, F, G, A, B, and C, and we see that on the left side, there is a button that is slightly separated. This button or switch will work so that when we press it, a melody pre-recorded in our Arduino will play. If we zoom in a bit more on this view, we can see that each button in the middle of the proto board actually contains a set of pins. Basically, these pins are connected in such a way that we could say that all of this line is connected to the other line through these pins, since these pins are connected to each other, just as the pins on the left are connected to each other. As they're not connected horizontally, these pins are not connected to the pins on the right. The only way they will connect is when we press the push button. When we press the push button, the circuit will close, and they will now be connected to each other. That is the basic operation of a button. So, taking this into account, we see that the pins on the right are each connected to a different pin on our Arduino. In the case of the first push button, this wire is connected to pin number 2. For the second push button, it is connected to pin 3, and so on. The other pins we have on the left side are connected to the negative side of our proto board. Here we see that we have a connection which extends to the left side, and this connection exits through a jumper to our Arduino at the pin marked as GND. Similarly, in the diagram, we have connected this pin marked with 5 volts, although we are not actually using it as part of our proto board. If we notice, only the red cable is connected, but there are no components connected to this power line. Therefore, we can eliminate this cable or jumper that is unnecessary. This is essentially being done with each of the push buttons. The pins in use are from number 2 to pin number 11. We also see that we have a component, which is a speaker, connected directly to our Arduino. The negative wire, marked with a negative sign, is connected directly to one of the ground pins on our Arduino. And on the other side, the positive terminal of our speaker is connected to pin number 11. Thus, pins from 2 to 10 function for the push buttons, while pin number 11 will be used to send the instruction to play a sound through the speaker. This is the overall connection diagram. We will learn how to connect it in the next video. Now that we've seen the project's diagram, let's learn how to connect it physically. This is the diagram we reviewed in a previous video. And as always, we will simplify it to explain how to connect the different parts. Here we have reduced it to the first connection of the first button. We see that it is a very simple connection, But before physically connecting the components, let's review a little theory about this component. Just in case you're asked at school or simply out of curiosity. In this image, we can see the general operation of the component. We can observe how the pins are inserted into the component, and based on this, we can determine how to insert them into our protoboard. I want you to pay attention to the following. When the push button is pressed, the circuit closes, allowing current to flow between the upper and lower pins. With this in mind, we can deduce how we should place the component on the protoboard, which is as follows. Remember that in this case, the current lines of the button, according to the connection we made, cover lines 15 and 17 of the protoboard, which I have outlined in orange. Following this concept, let's assume we want to light up the LED that is part of the Arduino and is directly connected to pin number 13. To carry out this task, we could connect a jumper from pin number 2 to the first end of the button. In this case, the jumper is green. Now, let's connect a jumper from the other end of the button, which is orange, and it will be connected directly to the pin marked with 5 volt. This seems like a piece of cake, right? Theoretically, when pressing the button, the LED should turn on since the circuit closes. On the other hand, theoretically, when the button is released, the circuit would open, causing the LED to turn off. It seems simple, doesn't it? However, there is a hidden trick. Let's see how this circuit works when the button is pressed. The green jumper connects to one end of the button, and when the button is pressed, the circuit closes. Thus, the switch connects from line 15 of the protoboard to line 17, causing the LED to light up. So far, so good. However, when the button is not actually pressed, the other end of the button's terminals is somewhat left floating. This can lead to the slightest interference, such as passing your hand nearby, being interpreted as a closure of the circuit, when none actually exists. This results in erratic behavior in the circuit's operation. To solve this issue, we will review 2 possible solutions, and by the end, you will understand why so much theory for this project. Here we have the design we saw in the previous slides. If you remember, we have a pair of terminals, which are the ones on the right, connected directly to 5 volts, and on the other side, we have the other pair of terminals connected to pin number 2. This is to identify when the push button is pressed. As I mentioned earlier, when the push button is pressed, theoretically, the integrated LED as part of the Arduino should light up, which is this one right here. However, when the push button is released, we see that the circuit does not fully close and this line remains open or floating. This is because nothing is connected on this side, so what we need to do is connect something to this side of the terminals to actually perform the function we desire. In this example, we will connect a resistor coming from this terminal of the pins, and after connecting this resistor, we will connect a wire directly to ground. So, when the push button is not pressed, the path followed is from pin number 2, across to the other end of the protoboard, through the resistor, and then directly to ground. Thus, we will indeed be closing a circuit. In the event that the push button is pressed, the path followed will be this one, but instead of going to the resistor, we will go to line number 17 and continue down this path to trigger the LED. So this is the first solution known as a pull-down configuration. Here we have our second configuration, which is called a pull-up configuration. So if we increase this circuit, we see that similarly we start from pin number 2, but this time, notice that the first pins go directly to the resistor, which does not go to ground, but goes directly to 5 volts. On the other hand, the second pins, or the second set of pins, are connected directly to ground. With this behavior, we will achieve that while the button is not pressed, the LED will remain on. When this button is pressed, our LED will turn off, meaning we will have the opposite behavior compared to the pull-down configuration. We can even start a simulation of this and notice how the LED has turned on. When we press our button, we see how the LED turns off. If we return to the pull-down schematic and start the simulation, we see that this time our LED does not turn on. When we press our button, that's when our LED which is integrated as part of the Arduino, actually turns on. So these are the two configurations that are important for you to know when working with buttons. After all this, what I want to convey is that Arduino has built-in resistors in the 8 mega chip, which we can access through software, eliminating the need for physical resistors that could complicate the project. These resistors have a value of 20 kiloohms on the Arduino Uno, although it may vary on other boards. Finally, the configuration they have is a pull-up type configuration. In the next video, we will see how to activate the resistors and how to handle this pull-up configuration. For now, let's continue assembling our project physically. Referring to our diagram, if you remember, we have the first connection like this. So the first thing we'll do is connect our button with the pins vertically to the ends where the numbers are on our protoboard. Here's another image from a different angle to clarify the connection. Once our button is secured, it should look as follows. After doing this, we will connect the jumper to the output of the right pins. I've highlighted a yellow line as a guide for your reference. Or here's another image to show you the correct connection. The other end of the jumper will be connected to pin number 2, as depicted in the image. We will connect another jumper to the other pins. This jumper will simply be connected to the negative rail of the protoboard. As you can see in the image, it becomes a bit complicated to have this jumper, since, considering we'll need to connect a total of 9 buttons, the jumpers will overlap, making it a little more challenging to manage the circuit. Now, if you want to work with jumpers, there's no problem. You can continue with the jumpers. In my case, to avoid too many cables getting tangled, I'm going to use some copper wires that I obtained from a UTP cable. I repeat, if you don't have them, it's perfectly fine to continue using jumpers. The important thing is to make the connection. We will replicate what we have done 8 more times, connecting to the Arduino pins 3 to 10. In my case, I left one push button further to the left so that it stands out from the rest, indicating that it is the button that will play the pre-recorded melody. After connecting your push buttons, you need to connect a jumper to the negative pole of the breadboard to complete the circuit. On the other end, connect this jumper to one of the Arduino outputs marked with GND or ground. We must also ensure that a bridge or jumper is connected between the power cut on the breadboard, which I have enclosed with a blue circle in the image. Finally, we will connect the buzzer, which in my case I have connected directly to the Arduino. I connected the red wire to the pin marked with 5 volts and the black wire to one of the pins marked with GND. This is a closer view of the connection of the buzzer to the pins. Great. With this, we have assembled our circuit and are ready to program it. Let's get to it. Now, let's write the code to make this wonderful project work. To do this, we will start by declaring our variables before the setup and loop methods. For this, we will declare some integer type variables. The first variable will be called pin buzzer, which will be equal to pin where our speaker is connected. In our case, it is pin number 11. We will also declare a pin for the LED, which will be equal to 13. This is to turn on the built-in LED on our Arduino whenever we press one of the buttons on our electric piano. Next, we will declare a set of variables that will represent the different buttons, which, if you remember, correspond to musical notes in a scale. So we declare int, and we'll call it button C, indicating that this is a musical note, it's C, and it will be equal to pin number 2. In other words, pin number 2 will represent the note C. If you know about music, you surely know what I'm talking about. We will also declare button D, which is the second musical note, connected to pin number 3, and so on. So button E will be equal to 4, button F will be equal to 5, button G will be equal to 6, button A will be equal to 7, button B will be equal to 8, button C 2, and this is because we reached the end of the scale and repeat note 2. And this will be equal to the button connected to pin number 9. We will also proceed to define a variable called musical, which will represent the button that, when pressed, will play our pre-recorded melody on the Arduino. Okay, with that, we finished declaring the different variables. Let's continue with our setup method. If you remember, in the setup method, we need to specify how the different pins of our Arduino will behave. To make this a bit simpler and faster, we will use a for loop, starting with int I equal to 2, I less than or equal to 10, I plus plus. We are doing this because, as you recall, the buttons we have here are connected to the Arduino from pins 2 to 10. We also have this musical button here, so the pins from 2 to 10 must behave the same way. Returning to the for loop, we have specified that we start at pin number 2 and want to go only up to pin number 10. Within this loop, we will call the method pin mode, and within this pin mode, we will specify the pin number represented by the variable I as the second parameter. As we have done so far, we have only used the values input or output. However, we also have a third value we can use to activate the internal resistor of our AddMega. To use this internal resistor, we must specify input pull-up. If you notice, it changes color immediately as it recognizes that this is a completely valid value. This will enable the resistor for the pin we are specifying. With this, we can avoid having to connect external resistors for either pull-down or pull-up configurations. We will do this for each of the pins associated with the push button. Also, if you remember, we are using a LEDI pin and a buzzer pin. Therefore, we need to initialize them after this for cycle. So we will call the pin mode method and indicate that the LEDI pin, which is the name we specified for pin number 13, will behave as an output. This is because we want to emit a light signal every time we press a push button. In other words, we are not inputting information, but rather, we want to output something to the outside world. On the other hand, we will also use pin mode to configure our buzzer. Then, within the pin mode method, we will indicate the buzzer pin output since we want to produce sound for the outside world. Now, we have completed the setup for this method, where we initialize the behavior of each of the pins. Now, let's move on to our loop method. I will remove this comment. Here, we need to start detecting when there is an interaction with each of the buttons. Basically, the code to accomplish this task will be defined by a while loop digital read. And within the digital read, we will check the value of each push button. In this case, we will start with the push button called button C, which is the first one we defined, and we will compare it against a low value. In other words, we are indicating or asking, while there is a reading of this button called button C at a low value, we will carry out a certain task. If you're wondering why we're defining a low value in this comparison, because as you remember, we have a pull-up resistor configuration. We discussed this earlier in the slides. So, in the event that this button called button C is pressed, we will call an Arduino function called tone. We can visit the Arduino page to review this tone method, which essentially indicates that it generates a square wave at a specified frequency. What we're mainly interested in is the syntax, where we need to specify the pin, the frequency, and the duration. This last data is optional. So, to complete this method, we will add the pair of parentheses that are missing and the semicolon. Inside the tone method, we will call our pin where our speaker is defined. This is the first parameter, indicating which pin your speaker is connected to. As the second parameter, if you remember, it is the frequency you want to emit when this method is executed. As part of our Arduino documentation, we have a reference that states, for technical details, we should check the notes by Brett Kahneman. The notes in this repository basically indicate, in a table at the bottom, what the musical note is and what frequency corresponds to that musical note. This is so we can copy and paste into our program if we want a specific note. In my case, I will use the note indicated as note C4, which is a musical scale, If you notice, each of these four represents a musical scale, so I will use these different frequencies in my Arduino program. We see that the first frequency indicated here is 262, so this is the second parameter I'll use for this tone method. Finally, I can specify a duration, for example, 100 milliseconds. Once I have issued the command to execute a sound, I will indicate that the LED should turn on. So using digital, right, I will specify the LED pin. Let's pay attention to how I wrote it. As the second parameter, we will indicate that we want it to turn on. Basically, with this, we will verify that when this button is pressed, or while it is held down, a musical note of C will sound. We need to carry out this task for each of the buttons, so I will copy the entire while loop and paste it a second time. I will change the button definition to the second button, and the only thing I will do is change the different frequencies. Then I return to the repository, look for the note of 4, copy this value, which I will paste as the second value. This is all I need to do to configure the second button. I will copy this configuration again, paste it, and indicate that the third button I want to configure is the button called button E. I will look again for the frequency value, which in this case is 330. Paste this value, and again copy the while loop. I will change the button name to button F. Check the frequency of this button, which is 349. Paste this value, copy the while loop again. Change the button I want to configure to button G. Return to the table and see that the node has a frequency of 392, which is the value I will paste here. Again, I copy the while loop, change the button I want to configure to button A. Go to my table, copy the value 440, paste it here, and I will continue doing this until I finish this scale. So, the next button is button B. The frequency is 494. I copy this while loop once more, change the button name to C2, which is the last button in the scale. I copy this value from node C5, which marks the start of the next scale. This is the value I paste here. With this, I have configured the different push buttons that are part of my circuit. Lastly, after all these while loops, I need to call a method called node tone. This is basically to stop the sound and allow us to play a different musical note on another one of the pins. We're going to pass pin buzzer to indicate that we want to execute this method with this pin. Finally, digital right pin LED low. This is to turn off the LED and ensure it doesn't light up again. With this, we have successfully configured each of the buttons or push buttons that are part of the circuit. However, we still need to configure this button called musical. How do we configure this? And how can we preload a song we want as part of the Arduino? Well, what we're going to do is return to the end of this method, and after the last loop we have defined here, we will define an if statement using digital read. And this time, we will try to read the pin defined in the musical variable. If we detect that this push button has been pressed, we will call a method that will have the functionality to execute our preloaded song. You may be wondering how I can preload a song. Well, basically, we have a site defined under this domain extramaster.net/tools/MIDI for your Arduino. I will leave this link as part of the resources. This page allows you to convert a MIDI type file to a format where it uses exactly what we have seen previously. That is, these tone functions with different delays to execute a musical song. So here you can click on Browse, and we can upload a file with the .mid format, which is a MIDI or music file. We can click on Open, and then we can click on the button that says Submit. While this file is being processed, if you want to download a MIDI file, you can easily search for any melody you like in MIDI format on Google. For example, I searched for The Legend of Zelda MIDI, and we see that there are many results with downloadable files of this type. We can click on, for example, the first link. We can see that here we can download different files that refer to the song I specified. Here we have the different files with the .mid extension. So, you can search for the song you like to play as part of your Arduino. We then return to the page we were on, and basically it indicates that I have successfully uploaded the file legendasoldaverworld.mid. Next, we need to specify which track to export to the Arduino. A MIDI file, like any musical file, contains different tracks that make up this music file. For example, a MIDI file may have a piano track, a trumpet track, etc. Basically, it tells us below that if we don't know which track we're looking for, we can select or leave the default option, which is the most complex option. In this case, I will keep the option that this page recommends. Alternatively, if you have knowledge about such files, you can open this file in a program to see which is the main track or the track that interests you. Let's scroll down this page, and we can see this section of options where we can adjust two things. The first is how fast you want your melody to play once it's on the Arduino. For example, if you want the music to play just like the MIDI file, you can set it to 1x speed. If you want the melody to be faster, you can increase this slider. On the other hand, we see the second setting that indicates the percentage of tones to be played. This is basically to make this song sound better on our Arduino. It's essentially to specify how different we want the notes to sound once the file is generated as part of the Arduino. If we want only distinctly different musical notes to be played, or if we want some notes that are not so different, which could potentially confuse the end user, we will leave this default setting. Finally, at the bottom, it indicates which device we want to generate this file for. In our case, it is an Arduino, and we will use the library or method called tone. So we leave this option selected and click on the button that says Convert MIDI to Arduino. Okay, we see that the process has been quite simple, and we now have a method called MIDI that contains the definition of all the notes to be played with their respective delays so that the music sounds great. So what we need to do is copy this method called MIDI. We will copy the entire method up to the closing brace. Make sure not to copy anything else, as it could cause problems in your original Arduino file. So I'm only copying this method called MIDI. I return to my Arduino sketch, and at the very end, after the last closing brace, I will proceed to paste everything I copied. Okay, here we have it. I will scroll up to the definition of this method. We see that we have a regular method that is part of our sketch. So, since it is a method, we can call it from other parts of our sketch. Basically, we are interested in calling it when this musical button has been pressed. To do this, we will indicate that we want to call this method called MIDI. An important point to consider is that you must ensure that when you generate your MIDI file, there are different delays, as there are cases where this delay or all delays in this MIDI function have a value of 0, which, as you can imagine, produces a single ugly sound and does not actually play a melody. Therefore, if you input a MIDI file and it returns a result with 0 delays, I recommend trying a different file or a different track. The second thing you need to keep in mind is that the frequencies of this tone method should be different for each one. As in different tests, I found that sometimes all frequencies were the same, resulting in a single sound. So these are the two things you need to consider when generating a file of this type or a MIDI function like this. With this, we have completed our sketch 100%. Let's validate it to ensure everything is correct. Okay, here I have a problem. This is basically because it tells me that a pin has not been declared in this scope. This is because, as you remember, we defined this method on an external page. Our buzzer pin is called pin buzzer. Therefore, what we need to do is go to Edit, Find, and indicate that it should search for tone pin in our file and replace it with pin buzzer. Once we have done this, we will select Replace All. Okay, you can see that each of the previous definitions has been replaced with the definition of our buzzer pin. Let's check the sketch again. This time it has compiled successfully. The only thing left is to confirm that we are connected to a board and a port of our Arduino. Once we check this, We upload our sketch to the board. Great. Now that we have uploaded the sketch, let's test it. We can hear a melody while we press different notes as if we were playing a small piano. Now, let's try that button that is separate from the others and listen to her beautiful melody. Isn't this project amazing? Congratulations. You now have a mini piano that you can play as much as you want. Let's begin discussing structures in programming that are extremely important in any programming language. These structures are loops, and they will allow us to repeat functionality as long as a condition is met. Let's start by talking about the while control structure. This is the syntax in programming for this structure. As you can see, it is very similar to an if, since we can evaluate one or more conditions, and while this condition is met, the code within the braces will be executed. The key difference lies in the fact that this expression will not be evaluated just once, but multiple times while the condition remains valid. Here we have a visual example of the flow of this loop. Don't pay special attention to the syntax. Focus on the steps being taken. We start by defining a variable called a, which is equal to 1. I want you to see how, as long as the condition that a is less than 10 holds true, the value of a is printed to the console. Let's see this in action. This animation we have seen is quite representative and visually shows us how a while loop executes. Now, let's go back to Tinkercad and experiment a bit with this while loop. Okay, we are back in Tinkercad now. What we're going to do is drag our Arduino Uno to the workspace. We'll go to the code section, specify that we want to use plain text, and we'll conduct some tests with this while loop. We will start by removing all the pre-existing code and focus basically on our setup method, as we want to see these tests run only once at this moment. We will make a change later. We will begin by declaring a variable, for example, call value, which will be equal to 1. This variable can be named whatever you like, and the important thing we need to focus on is how to declare a while loop. Notice that we will write the keyword while, place the parentheses, and an opening and closing brace. This is the structure of a while loop, and basically while means as long as. So we will indicate that while a condition is met, we will be executing a certain set of instructions over and over again. The conditional we will place in the parentheses can be any condition you want. It can be a very simple condition, such as directly passing a true value. As you may recall, in a previous section, we talked about Boolean expressions, and this Boolean expression results in either a true or false value. This final result will help us evaluate whether this while loop will execute or not. Thus, by directly placing a true or false value, we can start the execution of a while loop. Let's say while true. We will proceed to initialize our serial class through serial.begin 9600, and we will print something within the while loop. For example, serial.println and a message such as hello. If we start the simulation and go to the serial monitor, notice how the word hello is being printed repeatedly in the serial monitor, even when we are not inside our loop method. In fact, this loop method is actually a cycle, but here we are creating within the setup functionality a cycle that will allow us to write the word hello indefinitely. This is an infinite loop, since we are not establishing any rule to stop it. Let's stop the simulation. The idea of the while loop is that we have some more elaborate condition. In our case, for example, we can ask, while the value is less than 10. Here we are creating a Boolean expression. We are asking if the value of our variable value, which is 1, is less than 10. What we will proceed to do within the while loop is print this value of the variable value, not the value hello. So we indicate that we want to print the value of the variable value. And if we start the simulation, we are now printing the number 1 indefinitely, as that is the value of our variable. What we want to do is increment this value by 1. To increment the value by 1, we could do something like this. Value equals value plus 1. Let's place this line at a higher level. And with what we've done, if we start the simulation, notice that we are now printing only the values from 1 to 10. Let's stop the simulation and run it again. Notice that we are printing from the number 2 to 10, and this is because we are successfully incrementing the value of the variable called value. There is a way to simplify this line. If we only want to increment the value by 1, we can use value plus plus. First, let's stop the simulation, and we will change this value equals value plus 1 to value plus dot. I'll actually comment on this line to keep it as a reference. I'll add the plus plus, the semicolon. This line we have here is equivalent to the line we have above. If we start the simulation, notice that we get the same result as part of our console. So if you want to simplify this operation we have here, you can use this expression highlighted here. If you wanted to decrement this expression or value by 1, you could use value. In our case, we will leave the value as is, and we are incrementing this variable by 1. With what we have done, we can begin experimenting to create more complex things in our protoboard or project. What can we do? Well, instead of specifying a value of 10 here, we can specify a value of 255, which, as you may recall, is the maximum value accepted by a PWM pin. If we start the simulation, we can see that we have a range of values from 1 to 255. Now, let's proceed to add an LED to our project that we have here. We will add it directly by dragging the LED component. Then we'll drag a resistor. Let's place the resistor on the input and change the resistor value to, for example, 220 ohms. We will connect this lead to a PWM pin, for example, to the pin labeled with the number 11. Okay, and let's connect our cathode to the pin marked with GND. We will color this wire black, and now we have our project set up. Let's return to our code and remove the serial monitor. What we will proceed to do is first create a constant to specify which pin our LED is connected to. So we declare an integer constant named LED pin that is equal to 11, which is the value of our PWM pin that we have here. After creating this variable value, we will indicate that we want to set the pin mode of our LED pin to output. Now that we have done this, we can work with this value to modify the value of our pin where our LED is connected and perform different tests. Once we have printed the value of our variable on the serial monitor, we can set the analog write of the LED pin with the variable value. This value will be constantly changing according to the execution of this coil cycle, affecting the brightness of our LED. Let's start the simulation to see this in action, and notice that we are indeed changing the intensity of the red LED we have here. Let's stop the simulation. We have seen how to increase the intensity of the LED. We can repeat this same task, but now to decrease the intensity from 255 down to 0. To carry out this task, we can, for example, copy this same coil cycle, paste it again, and this time the condition will be that while the value is greater than 0, that is, while it is within the range of 1 to 255, we will decrease the value of this variable by 1. We will proceed to decrease the variable value by using value minus minus, print the value as well, and indicate analog write of the LED pin with the value. As you can see, we didn't have to make a significant change. Let's start the simulation and observe the values on the serial monitor. Notice how the value of the LED increases, and at some point, the LED value starts to decrease until it reaches 0 again. Let's stop the simulation, and we can make this repeat indefinitely. How do we do this? Well, we're going to cut all the code we have here, meaning the 2 while loops. We will cut them and paste them into our loop method. This will cause this pair of loops to repeat over and over indefinitely. Now, let's proceed to start the simulation. Here we have an issue with the variable named value. We'll also cut this variable from the setup method and paste it into the loop method. Once this change is made, we will start the simulation, check the serial monitor, and see that the brightness of the LED starts to increase. At a certain point, it begins to decrease. But when it reaches 0, the brightness starts to increase again. This action occurs repeatedly and indefinitely. With this, we now have an LED that is increasing and decreasing its brightness indefinitely. Let's continue practicing with the coil cycle. To carry out this activity, we will start with a project we created earlier. It is this project called LED Reactive to Light. Here is the diagram, and basically, we will proceed to create a copy of this project. Once I have created a copy of this project, notice what we had in the previous project. We had a photoresistor, which allowed us to vary the intensity of the LED based on the value of the photoresistor. However, we had a problem in this project, and we will see it in practice. Let's start the simulation. We position ourselves over the photoresistor, and notice what happens if I move to the right. We see that we begin to decrease the brightness of this LED, but as you can see, the brightness of this LED does not completely turn off. It remains slightly lit. If we move to the left, the value we have on our LED is not the maximum brightness we can obtain from this LED. This is happening due to the value we are reading from our photoresistor. As you can see, we never reach the value of 0 when decreasing the intensity. We reach the value of 5, and if we move to the left, we reach the value of 1024, just as we were specifying in our map method, which we have available here. Here, we were mapping a possible minimum value of 0 to a maximum value of 1023 to a new range from 0 to 255. We will resolve this issue in this exercise by using the while loop. What we will do is modify these values at runtime, meaning we need to determine the minimum value we can read from our photoresistor and the maximum value we can read from it, so that we can turn off our LED and make it shine at its maximum intensity. Let's get to work. I'm going to stop the simulation, and the first step that we will take is to add a button. We will add our button to the project, and the idea is that when I press this button, it will trigger a calibration to detect the maximum and minimum values of the photoresistor, just as calibration implies. I will proceed to connect this push button. I'll connect terminal 1A to the negative rail of the project, color the cable black, and then connect terminal 2B to one of the pins on our Arduino, specifically the pin marked with the number 10. Okay, here we have the wiring. I will color this cable orange, for example, and we have added our button to the project. That's all we'll do in the wiring section. The next step we will take is to return to the code section, and we will first add the pin where we connected our button. So we'll declare a constant called button, which will be equal to the value 10, as that is the pin where we connected our button. I'll also take this opportunity to add a second constant called indicator, which will be equal to 13. The purpose of this indicator variable is to control the built-in LED, which as you might recall is connected to pin number 13, allowing us to see in real time if the calibration of our values is taking place. Once I've added this pair of constants, I'll return to the setup method and add the different pin modes. I start with pin mode of the constant indicator, indicating that I want an output value, and I also add a pin mode for my constant button. In this case, I will specify that I want an input pull-up value to utilize the internal resistor of my Arduino pin. Once I have done this, I will go to my loop method, and before performing the first reading of my sensor or photoresistor, I will add a while loop. Here, I will proceed to ask while digital read of the button is equal to low, and I will carry out a series of actions. This means that while it detects that I am pressing my switch, what will I do? Well, to do a quick test, I will value a digital write of the indicator, which is the LED on pin number 13 with a high value. Once I stop pressing my switch, I will indicate digital write, indicator, comma, low. This is to turn off my LED. If I start the simulation now and hide the code, we have a problem here. I wrote digital read incorrectly. It should be digital read. Okay, let's start the simulation again. Now we have satisfactory code. Notice what happens if I press my switch. The LED that is part of the Arduino board lights up, and when I stop pressing the switch, the LED turns off, which means it is functioning correctly. I stop the simulation now and return to the code. However, this time, instead of simply turning on the LED that is part of my Arduino board, I will invoke a function called calibrate. I haven't created this function yet. I will proceed to create it in a moment. Before proceeding to create this functionality, I will change the variable called lectura to valor sensor. This variable will be responsible for reading the value of the photoresistor. Once this is done, we will proceed to create this function called calibrar. For this method, we will write until the end of the code void calibrar. We will write the pair of parentheses and the pair of braces to ensure it's a valid method. Instead of creating a local variable called valor sensor, we will change it to a global variable. So I will remove this int from the definition of the loop method, and we will proceed to create the same variable named valor sensor as a global variable. I go up to the top, write it, and write the variable name, which is valor sensor, initialized to 0. Once this is done, I can return to my calibrar method and carry out the sensor reading. I will copy this line I have here, then go to the bottom and paste the same line. I'll proceed to start the simulation to ensure everything is functioning correctly. We see that we have a small problem with the map function, so we need to indicate that we want to pass valor sensor as the variable since we changed the name of this variable. We also have an issue in the last line, which we will proceed to comment out. If we start the simulation now, we see that we already have a satisfactory simulation. To understand the algorithm that we will use within this calibrar method, let's go back to the slides. Okay, we are back in the slides. What we will proceed to do in order to solve our problem is the following. We will declare a couple of variables. One variable will represent a minimum value with an initial value of 1023. We will also create a variable that represents the maximum value that our photoresistor will be able to handle. This variable will have an initial value of 0. Let's assume the following scenario. Suppose we have our photoresistor slider all the way to the left, which means we are in a dark room. However, the sensor value does not read 1023 as we expected, but rather has a maximum reading of 900. The algorithm we will use is as follows. We will check if the sensor value, which is 900, is greater than the maximum value, which is this variable we see here. If it is, then the maximum value will be equal to the sensor value. Otherwise, if the sensor value is less than the minimum value, then the minimum value will be equal to the sensor value. Let's see this in practice. We will run with this sensor value equal to 900. Here, I have changed the different values we have on the left to numerical values. So according to the algorithm, we ask if 900, the value we are reading, is greater than 0, which is the value of this maximum variable. Then the maximum value will be equal to 900. And since 900 is less than 1023, which is the minimum value, then the minimum value will also be equal to 900. With this new information, we now have a minimum value variable with a value of 900 and a maximum value variable also with a value of 900. Now let's assume we move the slider all the way to the right, and as part of the sensor value, we have the number 40. If we run the algorithm again, we will check if 40 is greater than 900. And since this is not the case, we will not assign the maximum value to 40. It will remain at 900. Next, we will check if 40 is less than 900, and since this is true, the minimum value will be set to 40. Therefore, we will have a pair of variables, one variable with a minimum value of 40 and a maximum value of 900. We will be able to map these variables in such a way that they cover the range from 0 to 255 based on the values being read from our photoresistor. Let's return to Tinkercad to code this. We are back in Tinkercad. The first task we will perform is to create the variables we mentioned earlier, one to store the maximum sensor value and another to store the minimum sensor value. Let's proceed to create this pair of variables. We create an integer variable named sensorMax, which will be set to, remember, 0, and we create the second variable, sensorMin, which will be set to 1023. Next, we will go down to where we had left the calibrate method pending, and we will proceed to write its configuration. First, We'll turn on our indicator LED using digital write indicator with a value of high. Then we will read our sensor. Once we have read the sensor value, we will check if the sensor value is greater than sensor max. And if this is true, we will set sensor max equal to the sensor value. I agree with the algorithm we reviewed earlier. Subsequently, we will check if sensor value is less than sensor min. If so, sensor min be assigned the value of sensor value, semicolon. It is that simple to code our method that will calibrate this pair of variables. Let's return to our loop method. Once we finish executing our while loop, turning off our indicator LED, and taking a sensor reading again, we will print the values to our serial monitor for better visualization. So I'll use serial.print and write to our console, sensor value, followed by a space, and in the next line, serial.print, and we will print the sensor value. I will proceed to copy this pair of lines and paste them once more. In this second line, I will specify instead of the sensor value, a space, minimum value, and a space. Here, we will print the minimum sensor value, which is sensor min. I will again copy this pair of lines, paste them once more, and write maximum value, followed by a space. And here we will write name of sensor max. As I mentioned, this is not necessary, but it makes the output clearer and demonstrates how the values change as we press our button. Lastly, what we will do is redefine the call to our map method, since we do not want to map values from 1023 to 255. Instead, the minimum value we wish to map is the sensor min variable, and the maximum value is the sensor max variable. Okay, with what we have done, let's start the simulation to see what happens. Let's hide our code and notice that the photoresistor simulates being in a dark room. Our LED is turned on. We will also check the serial monitor. Here, to have a better display, we will return to the last serial.print and replace it with serial.println. Let's start the simulation. As we can see, the information is now displayed more clearly. We will proceed to make our circuit smaller. Remember that our photoresistor is on the left side. Let's press our button. Okay, notice that the value of our photoresistor is being read. It has set the value 657 in both the minimum value variable and the maximum value variable. If we proceed to slide to the right, we see that the sensor is reading a value of 5. If we press our button, notice that the sensor value is 5, the minimum value is 5, and the maximum value is 657. Let's hide this section of the code and see what has happened. Our LED has successfully turned off. This is because we changed the maximum and minimum values of our photoresistor at runtime. With this, it won't matter which font resistor you use. You will always be able to calibrate your circuit to obtain the minimum and maximum in a very simple way. Let's carry out the physical connections for the project. We'll start from scratch in case anyone doesn't remember a specific connection. First, we'll place our photoresistor on the breadboard. Next, we'll connect the left pin to the negative rail of the breadboard. We'll connect a 10K resistor to the right pin. From the output of that resistor, we'll connect a jumper to the positive rail of the breadboard. Once this is done, on the same rail as the second pin of the photoresistor, we'll place a jumper, in my case, green. This jumper will be connected to pin A0 of our Arduino. We'll integrate an LED into the project. The arrow indicates the cathode of the LED. Let's connect a jumper to the output of the cathode, which will go to the negative rail of the breadboard. On the other hand, we'll connect a resistor from the anode output. In my case, it's 220 ohms. And from that resistor, we'll connect a jumper that will go to pin number 6 of our Arduino. Next, we'll integrate a push button into the breadboard, connecting the left terminal to the negative rail of the breadboard, and the right pin of the push button will go directly to pin number 10 of the Arduino board. Finally, we must remember to power the breadboard by connecting the positive and negative rails to the pins marked with GND and 5V respectively. Once we upload the sketch to the board, we can see the project functioning. The advantage of what we have done is that we can test it even in daylight. Let's turn on a lamp above the photoresistor to detect a greater amount of light. The next step will be to press the push button to read the new value when a greater amount of light is detected. Let's turn off the lamp and press the button again to detect the minimum light value and store it in the variable. With what we have done, if we turn off the light, we see that the LED lights up, and the opposite happens if we turn on the light. To better appreciate whether the LED is on or off, I will place a piece of plastic which will allow us to see if the LED is lit or not. Now it's time to talk about the structure of Control 4. This is what it looks like in programming code. It seems like a more complex and confusing structure, doesn't it? But the truth is, it's the same as what we did in the previous section. Let's review a bit. We had this section of code that allowed us to increase the brightness of an LED. I want you to pay attention to the lines I marked with different colors. These 3 lines we used in the while loop are the ones we will replace to create a for loop. I have replaced these lines in the structure of the for loop. You can see that we have a more compact structure, and we have the creation of the variable that controls the loop, the Boolean expression, and the value increment all in one place. This makes it clearer, doesn't it? In this animation, I want you to see how a for loop behaves. The initialization or creation of the variable happens only once. Then, the evaluation of the Boolean expression takes place, and if it is true, the instruction is executed, in this case, printing a number. Subsequently, the value of the variable that controls the loop is incremented and the Boolean expression is evaluated again. This continues until the condition is no longer met. Let's go back to Tinkercad and experiment with this loop. Okay, we are back in Tinkercad. What we will do first is drag an Arduino board to our designer, and we'll proceed to the code section. Here, we specify that we want to use text instead of blocks, and we will go ahead and remove all this pre-created code. Let's start experimenting with the for loop, and we'll do it within the setup method. The first thing we'll do is initialize the serial class using serial.begin 9600 as a parameter. Inside the setup method, we'll begin writing a for loop. The for loop is written using the keyword for. We place the parentheses and the braces that are part of the for loop. In this for loop, we need 3 instructions or 3 expressions. The first instruction is initialization, the second expression is the conditional, and third, we need the increment or decrement that will be applied to our control variable. But we could even initialize a for loop using a semicolon. Notice that if we execute this program, we don't have any issues, only that here we don't have any kind of expression. And therefore, this for loop is practically useless. As I mentioned, we need 3 expressions. First, the initialization. This initialization will be a control variable, which will allow us to manage when we exit this for loop. We can directly create a variable here, for example, I, that is equal to 0. Or we can have a previously created variable, just like we did with the for loop, using int I equals 0. Here, there's no need to create this variable, although it is common to create the variable inside the for loop itself. So that's what we will do here. The variable we are creating, which is called I, can start with any initial value you want. For example, this variable can start at the number 50, the number 20, or the number 0. This completely depends on the execution of your sketch and what you need to achieve. Secondly, we need to identify the condition or the Boolean expression that will allow us to evaluate when to stop executing this for loop. We can then write I is less than 10. Here we are stating that as long as I is less than 10, this I that we are creating here will allow us to execute this for loop indefinitely. However, we need a third value as part of this for expression, which is how this variable that we are declaring here will be incremented. We can specify that we want to increment this variable by 1. As you can see, these 3 pieces of data we have here are the elements we use in a for loop. We're simply arranging them in a different way. We have the initialization, the condition, and the increment of the variable. With what we have done, we could go directly to serial and execute the print using print lane for the variable I. If we start the simulation, you can see that the serial monitor is already printing the numbers from 0 to 9. If we want to print the numbers from 1 to 10, we can change this variable I to start at 1 and specify that our condition should be less than or equal to 10. With this, we will print the numbers from 1 to 10 just as we see in this result. Okay, we're going to do something similar to what we did with the while loop exercise. Namely, we will turn on an LED or increase the brightness of an LED according to the value obtained from our loop. We will change this value of 10 to a value of 255, which is the maximum value for a PWM pen. If we start the simulation to see what is being explained, we can see that a sequence from 1 to 255 is already being displayed satisfactorily. Okay, I will change this I to initialize with a value of 0. And I'll proceed to add an LED to my diagram that I have here. Let's search for an LED component. We will also drag a resistor component. We will connect the resistor to the anode, setting a value of 220 ohms as part of the output from the anode. Let's connect the anode to one of the PWM pins, for example, pin number 11, and connect the cathode to the pin marked with GEND. Okay, let's color these wires differently. We return to the code section, and this is to indicate that after performing the print through serial.println, we want to execute an analog write with a value I to pin number 11. So we need to create a constant called, for example, lead pin, which is equal to the pin value, in this case number 11. Once in the analog write method, we will write lead pin and the value of I. With this, we have started the simulation to see what happens, and we can see that satisfactorily, we are increasing the brightness of our LED. Let's stop the simulation, return to the code, and perform the opposite action, that is, to decrement the brightness of the LED through a for loop. So let's write that for int I, which equals, since we ended this cycle with a value of 255, we will start the second cycle with a value of 255. This time, we will indicate that while I is greater than or equal to 0, since we will decrease the intensity from 255 to 0. As the third part of the for loop, we will indicate that we want to perform a decrement instead of an increment, as we did earlier. Finally, we can copy this pair of lines, as we will be performing the printing on the serial monitor, and through an analog write to lead pin, we will set the value of our variable I, which will decrement in this for loop. We start the simulation. Notice how the brightness of the LED increases, and at a certain point, it begins to decrease until we reach the value 0. Okay, as we did with the for loop, we can cut these two for loops we have here, go to our loop method, paste this pair of instructions or these sections of code, and if we start the simulation, you'll see that our LED lights up and turns off again indefinitely. Here, we are decreasing the brightness of the LED until it turns off and then starts to increase the brightness of this LED again. This is how this for loop works in a very basic way. Remember that you need to initialize a variable, require a Boolean expression to evaluate when this for loop will execute and when it will not, and also need to increment or decrement or perform the necessary operation directly on the variable you created earlier or the control variable. Let's move on to the practical part of our section, where we will recreate the effect of a car from a very well-known TV series. This effect is called Knight Rider, and it involves using a series of LEDs to simulate the movement seen in the image. We will proceed to carry out this action. Returning to Tinkercad, I will remove this LED and this resistor. I will leave only my Arduino board. Next, let's drag a breadboard as part of our project. We will begin to insert a series of LEDs into our breadboard. Now, let's search for the LED component and start inserting them into the breadboard. We will insert a total of 6 LEDs in Tinkercad. So let's drag a total of 6 LEDs for our project. Once we've dragged and dropped our LEDs, we'll connect the cathode directly to the negative rail of the breadboard. I will color the wire black for each of them. After doing this, we will connect a resistor to each of the anode outputs of our LEDs. This resistor will have a value of 220 ohms. We can copy and paste this resistor so we don't have to drag and change the value for each one individually. Thus, we copy a resistor and paste it to the anode output of each of the LEDs. Okay, we now have this ready. The only thing left is to connect each of the LEDs to a different pin on our Arduino. Let's start with the first LED. Connect the anode directly to pin number 13. Connect the second LED to pin number 12, the third to pin number 11, the fourth to pin number 10, the fifth to the pin marked with number 9, and the last LED to the pin marked with number 8 on our Arduino. Don't forget to connect this negative rail so that everything works correctly. Now, take a new wire and connect it directly to the pin marked G and D on the Arduino. Let's color this wire black so we can differentiate the different sections of our project. Once we have made the various connections, let's go to the code section. We will remove the code that we previously had inside our loop method. We will redefine this variable called lead pin to lead pin 1 with a value of 13. This constant will represent our first LED connected to pin number 13. And we'll create a different constant for each of the following pins. So I will copy this line and paste it 5 more times. To have a total of 6 constants, I will proceed to change the name of each constant to lead pin 1, lead pin 2, lead pin 3, lead pin 4, lead pin 5, and lead pin 6. Let's also change the pin numbers to 12, 11, 10, 9, and 8. This is to control each of the pins from our Arduino sketch. We will also create a variable called timer, which will be set to 100. This variable will help us define the transition time between each of the LEDs. The next step will be to set the pin mode for each of these pins. To do this, we will go to our setup function and write pin mode with the pin number in parentheses represented here with constants. We will use lead pin 1 and indicate that we want it to be an output type. We will copy this line and paste it 5 more times, changing the constant name to lead pin 2, lead pin 3, lead pin 4, lead pin 5, and lead pin 6. This way, we will change the pin mode for each of these pins that we will use. Once we have done this, let's move on to our loop method. Inside the loop method, our goal is to turn on an LED. For example, the LED located on pin number 13. Wait for the time defined by the timer variable, and once that time has elapsed, turn off the LED. We will repeat the same action with the second LED, and so on for each of the other pins. Now, let's go to our loop method and write digital write lead pin 1 to turn on this LED. We specify that we want to wait for the time set in the timer variable, and once that time has passed, we will indicate that we want to turn off our LED located on lead pin 1 using a low parameter. We will copy these 3 lines since we want to perform the same action, but this time with lead pin 2. We will leave a space, paste these lines again, and repeat this task for each of our LEDs. So we have lead pin 4, lead pin 5, and finally lead pin 6. Okay, now that we have done this, let's start the simulation to see what happens in our project. Notice that we already have a project that looks quite good and is satisfactorily simulating our Knight Rider effect. We can stop the simulation, go to the code, and modify this timer variable to, for example, 500 to provide more spacing and the transition of each of the LEDs. Okay, notice that we now have a slower transition for each of the LEDs. Let's stop the simulation. What problem do we see with the code we've entered? If you noticed, we had to copy and paste a lot of code. In fact, if you look even closer, you'll see that we have different patterns that repeat over and over again. For example, here we are repeating the assignment of the output parameter to each of the pins. And also, as we saw earlier, we are repeating the same action for each of the pins of our Arduino. This leads us to have many lines of code. We have a total of 45 lines of code that could very well be simplified using a for loop. This is how we have a sketch without using a for loop. In the next video, we will see how to create a sketch and simplify it using a for loop. You'll be amazed at the amount of code we are going to create. We have seen how to create this project without using a for loop. Now, let's see how to leverage this loop to significantly reduce the number of lines of code in this sketch. First, let's analyze our setup method. As I mentioned before, we are repeating the same task over and over. As you can see, these pins marked here have a sequence. They start with pin number 13 and decrease down to pin number 8. We can use this pattern and incorporate it into a for loop to reduce the number of lines we have here. How can we do that? Well, we will create a for loop and indicate that for a variable named I, which has an initial value, we will set the minimum value to 8. So for int I equal to 8, semicolon, while I is less than or equal to n, here we define the highest pin, which in this case is pin number 13. We write 13, semicolon I plus plus to increment the value by 1 on each iteration of our for loop. This way, we will start at 8, increasing to 9, then 10, 11, and so on until we reach 13. Within our for loop, we will merely invoke the pin mode method, passing the value of I, which, as you remember, we were doing manually by entering lead pin 1 up to lead pin 6, representing the numbers from 13 down to 8. So we will carry out the invocation of this pin mode through the variable I, which will essentially hold the number of the pin we want to initialize with pin mode. We will specify an output value for each of them. As you can see, it is the same assignment for each of these pins. That's it. This is all we need to do to carry out the initialization with an output type. With this, we can remove the 6 lines we had previously. And notice that we now have only 4 lines in which we carry out this entire set of operations. If we remove this pair of braces here, we are left with just 2 lines, which may have taken some effort to write, but we are greatly simplifying this sketch. Isn't it surprising to use a for loop to perform these types of tasks? Well, you'll be even more amazed by the number of lines we will eliminate from our loop method. Inside the loop method, we will proceed to create another for loop. As you can see here, we are performing the same action repeatedly, but only changing the pin we are handling. We can then take these 3 lines and place them within a for loop. We will specify that we want to create the for loop with an initialized variable called I, which will be equal to, in this case, since we want to start with our lead pin 1, which has a value of 13, let's replace the content of this initial variable with the number 13. We place the semicolon, and the condition will be that while it is not equal to the constant called lead pin 6, which corresponds to the value 8, this for loop will continue to execute. Therefore, we write while I is greater than or equal to 8, place the semicolon, and write the assignment of a decrement, I, as this is a decrement, since we will start with pin number 13 and want to reach pin number 8. Okay. What we can do within this for loop is copy these 3 lines from our loop section, paste them inside the for, and replace lead pin 1 directly with our variable I, which will change in each iteration. So we remove lead pin 1 from these 2 lines and keep the variable I. This variable I, on its first run, will have a value of 13. On the second run, it will have a value of 12, and so on until it reaches the number 8. Okay, let's keep the variable I. By creating this loop, we have simplified this entire set of lines that we have at the bottom, as we are executing all these lines, but in a simplified and automated way. We can then proceed to remove these lines. Notice that we now have a loop method with only 6 lines of code compared to what we had before. And if we start the simulation, you will see that we have the same behavior as before. We can stop the simulation, increase this timer value to, for example, 100, and then we will have a faster execution of our LED transitions. To make this project more interesting, wouldn't it be better to control the speed of the LED transition, that is, this timer variable, but through a physical component that allows us to control this speed? Well, we can integrate a potentiometer to achieve this. Let's see how to do it practically in the next video. In this video, we will see how to integrate a potentiometer component to regulate the transition speed between the different LEDs. In other words, we will learn how to control this timer variable dynamically with the potentiometer. Let's hide this section of code and proceed to find the potentiometer component. Here it is. We will drag a potentiometer and place it on our breadboard. Let's wire the potentiometer. We will connect terminal 1 directly to the negative rail of the breadboard, and we will also connect terminal 2 directly to the positive rail of the breadboard. Since we are using the positive rail of our breadboard, we will connect it to our Arduino board. We will take a wire from our breadboard, specifically from the positive rail, and connect this wire to the pin marked with 5 volts. We will color this wire red, and now we have the connection. We will also proceed to connect the wiper terminal of our potentiometer to the pin marked with A0 on our Arduino board. We have done this previously, so we'll connect it to our pin A0. We'll color it orange, for example, and our connections are now ready. With this change we made, we will modify this section of constants. In fact, we could eliminate this part of the constants since we are not really using them in our code. So we will remove this section of code, and notice that we now have a cleaner code. What we will proceed to declare as part of this section is a new integer constant called, for example, pot, representing the analog pin 0 on our Arduino board. We will indicate that the initial value will be equal to 0. Now that we have declared this constant, let's go directly to our loop method. Before entering this for loop, we will declare a variable called, for example, reading, which will equal the analog reading from our potentiometer. Once we have taken the reading from our potentiometer, we will set our variable timer to be equal to a mapping of the variable reading. What we want to do is map the values from 0 to 1023, which are the possible values our potentiometer can receive, to value 0 and the maximum wait time between the LEDs. This means, for example, if we set the number 1000, it indicates that the maximum value we can input from the potentiometer will be a 1-second wait. So let's map 0 to 1023 to the values 0 to 1000. Thus, this second section we have here will represent the time interval in milliseconds that we can input or control as part of the potentiometer. Since we are modifying the timer variable directly here, there is no need to change anything within our for method. Let's start the simulation to see how what we have done looks. Okay. And notice that immediately we see that all 6 LEDs are lit simultaneously, but in reality, not all 6 LEDs are on. The transition is so rapid that we cannot perceive it. If we start turning the knob to the right, you can see the transition between the LEDs more clearly. Let's move further to the right, and as I move further to the right, we have a longer time interval. We have a longer transition of 1 second. And as we move to the left, we have a faster transition. Once we have verified that the project works correctly in Tinkercad, let's proceed to assemble it physically. For fun, I have added a total of 9 LEDs to the project instead of 6. Let's start by connecting the cathodes of the LEDs to the negative rail of the protoboard. We will do this for each of the LEDs we add to the protoboard. Next, an important step is to place a 220 ohm resistor or a similar value at the output of the LED's anode. We will repeat this step for each of the LEDs. Then let's connect the anode leg of the first LED to pin number 13 of our Arduino. We will need to calculate each of the anode's outputs to a different pin. In my case, I have used pins number 5 through 13 on the Arduino board. Let's also connect the potentiometer, which will allow us to adjust the speed of the LED transitions. We will connect the left terminal to the negative rail and the right terminal to the positive rail. The signal pin, on the other hand, will be connected to the pin marked A0 on the Arduino. Finally, if you haven't connected the rails of the protoboard, now is the time to do so by connecting a pair of jumpers from the protoboard to the pins marked G and D and 5 volt respectively. Here we have the project working. We see how the LEDs gradually move since we have the potentiometer fully turned to the right. We can turn the potentiometer and we can see how the movement speed increases. At a certain point, the movement is so fast that it seems to us that all the LEDs are lit at the same time, something similar to what happens with a PWM signal. This is how the forward cycle works in practice, combining different knowledge we have acquired throughout the course. Fantastic, isn't it? This is the first way to declare an array. There's a second way that, in my opinion, is a better method, as it will prevent us from having to execute this type of initialization from the start. Let's stop the simulation, and the second way is as follows. I will proceed to remove this code or these variables that are no longer useful. And after the declaration of this first array, let's comment out this line and create our array using the second method. The second method involves writing the data type of our array, stating the name of our variable. In this case, we'll name it the same as before, but this time we'll leave the brackets empty, place an equal sign, and after the equal sign, we'll place a pair of braces, one opening brace and one closing brace. Inside this set of braces, we will include the numeric elements with which we wish to initialize our array. In this case, these will be the assignments we have on the right side at the bottom. So let's do this. We write 3, 34, 10, 892, 22. In this way, notice that we avoid all these lines we've had here to initialize each of the indices of our array. It is a more simplified way as we summarize the name of our variable or array and its different values in a single line. We can then remove these lines we have here. Let's proceed to start the simulation, first clearing the serial monitor. We start the simulation. And notice that we have the number 961 printed again, which means this is correct. With what we've learned about arrays and our prior knowledge of loops, we can combine this knowledge to further simplify our code. How can we do this? Well, imagine we have an array with a set of 100 numbers, not just the ones we have here, but 100 numbers, 200 numbers. Imagine we needed to sum each of them to store the result in a variable, just like we have here. We would need to write a lot of lines of code, and this would be prone to error since we could mistakenly write a number that doesn't correspond. However, thanks to the for loop, we can avoid this tedious code. How do we do this? Well, we'll keep the variable we created earlier called result_audio. We will remove this addition of values and instead indicate that the result will be equal to 0. Next, we will use a for loop to iterate through each of these elements in our array to perform the sum and store it in the result ado variable. To carry out this operation, we will proceed to create a for loop after this serial ... begin. We will remove this pair of serial ... print that we previously created, and then proceed to create the for loop. What will the different values or sections of our for loop be? Let's visualize it. The idea is for us to traverse our array. Remember, we start with index number 0. We will traverse from index number 0, moving to index 1, index 2, index 3, and index 4 in order to obtain each of the values from our array. Therefore, the initialization will correspond to the starting index of our array, which in this case is index number 0. Next, we will specify the condition, and the condition is established by the index of our array. The condition will be that while I is less than or equal to index number 4, the increment operation will be I++, as we want to traverse each of the values in the indices of our array. Within the for loop, we will perform the operation of taking each of these values and summing them to obtain a final result in the result variable. To do this, we will set for int I equal to 0, I is less than or equal to 4, semicolon, and increment I. To see this quickly, we will use serial.println to display the value of I. We start the simulation and notice that we have the count from number 0 to number 4. Let's clear this content, stop the simulation, and change this serial.println of I to display the value of our values variable at the index specified by variable I. We will change this I to values and use square brackets with variable I, which will allow us to extract each of the values. When we have a value of 0, we will actually say that we want to index number 0 of our values variable, where the value is 3. Subsequently, when we indicate that we want to index number 1 of the values variable, we will access exactly the number 34, which is the value stored at index 1, and so on. So let's keep this variable I, start the simulation again, and notice that we are now successfully displaying each of the values that are part of our values array. Let's stop the simulation. And once we see that this works correctly, we will set the result variable to equal result plus values at index I. We will perform the sum of the value obtained in each of the iterations and add the new value, thus summing each of these values we have here. At the end of this for loop, we will print the result using serial.println. Let's start the simulation to see what this displays. And notice that we again have a value of 961, which is the result of the sum of the previous values. This is basically how an array works. This is how we can access and set values at each index of our array. Through a for loop, we can iterate through an array either to retrieve values or to assign different values to our array. In this section, we will explore another topic that will help us optimize our code and manage a series of data types that are the same with less code and fewer complications. This topic is arrays. To understand the concept of arrays well, let's look at an example. I suppose we will need a set of integer variables to perform some type of calculation. We have already seen how to declare variables in Arduino. Making an analogy with the real world, what we are doing is equivalent to having an Excel file where we could only write in column A in row 1. That is only one cell in each file. If we wanted to write or create these 5 variables with their respective values, we would have to create a new file for each value. You might think this is extremely inefficient. In the memory of our microcontroller, we would see these variables with their values arranged randomly. Well, let's remove this clutter, and let me introduce you to arrays. This is how an array looks in memory. We see that first, we have stopped defining a variable for each value we needed, and instead, we have a single variable now. The values are being stored contiguously, meaning one next to the other. If we count the elements of the array, we see that we have a total of 5 elements, or 5 values in our case, although any type of data can be stored in these arrays as long as all the elements are of the same type. Another important aspect of arrays is that they have an index which starts numbering from 0. This can be a bit confusing, but that's how it is in the programming world. Indexing starts from number 0. So if we asked which element exists at index number 3, the answer would be the numeric value 4. With the creation of arrays, if we make the analogy with Excel documents, we no longer need to create multiple files to store values, as we would have one available row in the same document to store them. Let's learn how to declare arrays and create a project with them in Tinkercad. All right, we are back in Tinkercad. What we are going to do is drag an Arduino Uno component into our designer. In this section, we will work only with code to fully understand this part of arrays. We will indicate that we want to work with text, so let's delete this pre-created text and begin analyzing our topic on arrays. First, as you will recall, we have previously seen how to declare different variables. Let's declare a set of variables, for instance, one called value1, which has the value 3. A second variable named value2, which has the value 34. Another called value3, equal to 10. A fourth variable named value4, equal to, for example, 892. And a final variable called value5, which is equal to, for example, 22. Okay, we now have 5 variables, all of them of integer type. Now suppose we want to sum each of these variables to get the total. We could create a variable named result that is equal to value1 plus value2 plus value3 plus value4 plus value5. Okay, we put in the semicolon. We can initialize the serial monitor to see this in real time, so we indicate serial.begin, 9600. And at the end, we use serial.println to display the result. If we start the simulation, we see that the serial monitor shows the number 961, which is the sum of these values we have here. Make sure to remember that value, 961, to verify that the subsequent calculations we make with the arrays are correct. Okay, now that we've seen how to do this with normal variables, let me introduce arrays. An array is declared by specifying the data type of the array you wish to create. In this case, since our variables are of integer type, our array will also be of integer type. It is important to note that an array can only contain elements of the same type. Thus, we indicate that we want an array of integer values, and we will assign values to this array, for example. You can see that it is declared almost like a normal variable. The main difference is that after declaring the name of the variable, we will place a pair of brackets. These brackets will identify or indicate that this is an array. There are different ways to initialize an array. One way is to specify the size of the array. That is, how many values we will be able to store as part of this array. An example of this would be to specify the number 4. This indicates that this array, named Valores, can contain only 4 elements. We place a semicolon, and we have created an array in our Arduino sketch. The next step is to specify the different values for our array. To accomplish this, meaning specifying each of the values of our array, we can access the array by writing the name of the array and within brackets the index we wish to access. Remember that an array starts with index number 0 and ends at the index specified by the element count -1. Keeping this in mind, we can state that our index number 0 will be equal to, and here we will enter the first value, which is the number 3. Now, let's store this second value, which is 34. To do this, we will access values. But this time we will save this data in another one of the boxes we saw earlier in the slides, specifically in the box corresponding to index number 1. As we can see, the box at index number 0 already contains the value 3, so now we will specify that we want to fill this element or index number 1 with the value 34. We can perform each of these actions for every index. For example, at index number 2, we will store the value 10, and in values at index number 3, we will store 892. We still need to store the value of the variable called value 5, which has a value of 22. What do you think would happen right now if we declared an array with a size of 4 elements? Do you think it would be valid to add it as it is here, or would that be invalid? The truth is that since we have already filled the 4 available spaces declared during the initialization of this array, we can no longer add more values. Therefore, we need to change the size of this array to accommodate the 5 values we need from this previous exercise. So now we can access values at index 4 and store the value 22. Well, we have already seen how to assign values to each of the indices of our array. Now, let's see how we can retrieve the information to perform operations with the data we have previously stored in our arrays. We'll proceed to change this operation so that instead of directly accessing this variable or these variables in the section above, we access our array according to its index. So we'll modify this operation. Instead of value 1, we will specify values, accessing the array by invoking this section we have here. This way, we will automatically retrieve the information, which in this case will be the number 3. If we want to access index number 1, we do it like this. This way we get the value of 3, 4, and so on, retrieving the value from index 2, index 3, index number 4. Okay, let's test our sketch to see that everything works correctly. We start the simulation and notice that we have the number 961 printed successfully again. One question you might have is what happens if I don't initialize any of these values? Well, let's test it. Let's comment out some of the lines, start the simulation, and notice that in our serial monitor, we have a very strange number, which is -321. This is happening because we haven't initialized one of the indices of our array, causing us to get a completely random number which is affecting our operation below. Another question you might ask is, what happens if I try to access an index that is greater than or does not exist? Here we have created an array with a maximum of 5 elements, which translates into what we see in this section below. What would happen if we tried to access index number 10, for example, which we know does not exist since we declared a maximum of 5 elements as part of our array? Well, let's see it practically. After printing the result, we will try to print through serial.println values at index number 10. Let's clear everything on the serial monitor, start the simulation, and upon returning to see the result on our serial monitor, we notice that we have a number 0, which is part of the output of values at index 10. Although this does not indicate any kind of issue with our Arduino per se, you should be cautious with these types of things, as it can cause noise in your results or measurements. Always try to work with an array within its valid dimensions, meaning, in this case, an index greater than 4, just as we have here. Let's continue practicing with the topic of arrays. On this occasion, we will reuse a project that we previously created, the Knight Rider project, where, if we start the simulation, we can control the speed of the transition of our LEDs using a potentiometer, as seen in this example. Okay, let's stop the simulation. Here, we have a small problem that you may not have noticed. The issue arises if for some reason a pin on your Arduino gets damaged. For example, let's assume that pin number 10 is damaged and can no longer be used. In that case, we would need to remove the connection to one of our LEDs and connect it to a new pin. Let's color this wire orange or maybe yellow. If we start the simulation now, notice that we have an LED that isn't lighting up. You might think the solution is very simple, but as you can see here in our loop 4, we are heavily reliant on the idea that we have a set of pins from pin number 8 to pin number 13. This is undoubtedly a serious problem, as there is no way to integrate this pin that we've swapped into this for loop. If we were to add the number 3 here, we would be sending signals to the other pins between pin number 3 and pin number 13. And perhaps in this set of pins, there is another pin you may wish to use later for another task. Therefore, this is not a viable solution. What is a possible solution? Well, a very valid and commonly used solution in the Arduino world is to create an array with the definition of all the pins we will use to execute our project. We will now proceed to declare a constant that is of type integer array. We declare const int, we name it, for example, pins, indicate that this is an array. Remember that this is the syntax for an array. Within the initialization of our pins in this array we have created, we will also define the order of the pins we want to include in this array. So let's start with pin number 8, since as you may recall, pin 8 is the minimum pin we have as part of cycle 4. Next, we will place 9, replacing pin number 10. We will then add pin number 3. We are not including pin number 3 from the beginning, because if we included pin number 3 from the start, we would have a disordered sequence in our EPS sequence. We can see this a bit later. For now, we will order our pins in this way: 8, 9, 3, 11, 12, and 13. Once we have done this, we will proceed to define another constant, which will be of type integer, and we will call it size. This will represent the size of our array. In this case, since we have 6 elements, we will set the initialization of this constant to the number 6. Once this is done, we will reconfigure our for loop. We will specify that for int equals 0, no longer 8, as we will iterate through our array. Remember that the lowest index of an array is index number 0. Next, we will specify that while I is less than or equal to the size of our array minus 1. Why minus 1? Because if we start from index number 0, the maximum index we want to count is index 5. If you remember, there are 6 elements. So the indices are 0, 1, 2, 3, 4, and 5. Thus, we could have this declaration we see here, or we could indicate that while I is less than 6, this way the maximum index would be number 5. Then we place or leave this I++ to iterate through each of the values in our array. We will also modify this pin mode, as we don't want to directly initialize the variable I, but rather initialize each of the elements in our array of pins. Therefore, we will indicate pins with the variable I. With this, we will initialize each of these pins with an output value. Let's go to our loop and see what we can correct. This line for reading is correct. This line for the timer is also correct. We will proceed to correct this for loop. In this case, we will specify that the starting value will not be 13, but since we're going to read our array again, the maximum value will be 5, as it is the maximum number of indices in our array. Here, we can also change this to size -1 if we wanted to have greater control from the variable. Let's leave it like this, but you know that this is equal to the number 5, as we subtract 1 from the number 6. Subsequently, the condition will be that while I is greater than or equal to, in this case, the replacement will be 0, since 0 is the minimum number of the index values of our array. We execute a decrement on I. However, here in this digital write, instead of performing a digital write on our variable I, we will carry out this operation on pins and in brackets I. This indicates which pin we want to set to a height value. We'll proceed to turn off the same pin on this third line that we see here. Okay, with what we have done, we will start the simulation to see what happens. Notice that we successfully have our project running correctly once again. This is how we have fixed our project through our arrays and a for loop. Let's see how to create another project, reusing our components from the Knight Rider project. The idea of this project is that as we increase the value of the potentiometer, we can also increase which LEDs are turning on. So if we turn the knob all the way to the right, we will turn on all the LEDs, and as we decrease the value of the potentiometer, we will reduce the number of LEDs that are lit at any given moment. Now, let's go to the code section to modify our project, since this modification will be solely based on code. We do not need to change anything in our circuit. Even this pin, which we changed here and has completed the sequence of our LEDs, can remain as it is, because remember, we are using an array to represent our different LEDs. We will modify our code, and specifically, we need to go to the loop section to alter this behavior I've mentioned. Let's read the value of our potentiometer. This time, instead of modifying a variable called timer, we'll perform a mapping from 0 to 1023, which are the minimum and maximum values of the analog input of our Arduino. We will map these to the value 0, with a maximum set to the number of LEDs we have on our breadboard. In this case, we only have 6 LEDs, but you will see that in the physical project, we will integrate more LEDs, so this value will change. Therefore, we will specify the size here. With this, we will be able to calculate how many LEDs will light up at the same time. Subsequently, we will iterate through each of our digital pins that are part of our array, or rather the indices that belong to our array. Let's remove these 3 lines that are part of our for loop, and instead, we will check if I, which remember is the number of the digital pin, is less than level. If this condition is true, we will use digital write to turn on the digital pin indicated by I. So we set pin I to a value of high. Otherwise, we indicate digital write, pin I, low. Here, instead of having this timer variable, we will create a new variable called nivel. Basically, what we will do is according to the input we have from our potentiometer, we will indicate how many LEDs will be lit. For example, suppose in this variable, this mapping gives us a value of 3. Here, we traverse each of the pins, and if the digital pin is less than the level we obtained, we will turn on the LED. The logic is really quite simple. Let's start the simulation to see how this looks as explained. We have an error here. We will correct this pin to pins, since that is actually the name of our array, pins. Okay, let's try to start the simulation again. We have another problem. I placed an opening brace instead of a closing brace. Okay, let's start the simulation, and we can now carry out a successful compilation and execution. Okay, we have our potentiometer fully to the left. As we move to the right, notice that each of these LEDs starts to light up. We can light up all the LEDs, or we can light up fewer depending on the position of our potentiometer. This is how we created this simple project called LED-bar. The assembly of this project is identical to the previous section. In fact, I will be using the same physically assembled project. Look how, as I move the potentiometer to one side or the other, the lights turn on or off, creating a nice effect. Doesn't it look great? Hello, I am Hector Pares. We're going to start the course by creating our first project for beginners with Arduino, and what we will build is a nice binary clock. Here it is, alive and well. We see that this is a simple project, but it really attracts a lot of attention because it is quite colorful. If you want to assemble it and have yours as well, these are the components. A proto board, 6 red LEDs, 6 green LEDs, 6 yellow LEDs, although in the end you can choose any colors you like. We also need 17 resistors of 330 ohms, 17 jumpers, and of course an Arduino Uno. With these pieces, we will see what the connection diagram of our circuit looks like. Let's look at the electronic diagram of this binary clock. Here we have our diagram that simulates the execution of our binary clock. Okay, let's see how this project is composed. First, we have our Arduino Uno, which we see represented here, and we can see that each of the pins is receiving a signal from each of the LEDs located at the top or on the proto board. Let's zoom in on this image to get a better look. Okay, and here we have, for example, our first LED. What we're basically doing here is connecting each of the LEDs to an output of the Arduino Uno. If you're wondering why we have 6 red LEDs, 6 green LEDs, and only 5 yellow LEDs, well, the answer is that we want to represent a numerical value. In this case, the value of seconds, minutes, and hours in a binary format. If we open the Windows calculator, here it is. Notice how we have a decimal representation of a number. For example, if we write the number 1, we see its equivalent in a different base. In hexadecimal, the number 1 is represented the same way as number 1. And down below, we have its representation in binary. In the case of the number 1, we have 3 zeros followed by a 1. Let's see what happens if we write the maximum number of seconds, which is 59. The binary equivalent is the number that appears here. If we count the number of digits that can be represented, we see 1, 2, 3, 4, 5, and 6. This means that it won't go beyond this number, as 1 minute has only 59 seconds, and similarly, 1 hour has only 59 minutes. Therefore, this is the maximum value we can have in a binary representation, which is the same as the value represented by each of these 10 that we have here. In the case of the diagram, the red LEDs represent seconds, the green LEDs represent minutes, and the yellow LEDs represent hours. Now, regarding hours, if we write the maximum number of hours in a day, which is 23 hours, note that the maximum number of binary digits we have here is 1, 2, 3, 4, and 5. Therefore, this is why we only have 5 LEDs on our proto board or in our project. That explains why we have 6 red LEDs, 6 green LEDs, and only 5 yellow LEDs. Now, pay attention to the fact that what we're doing with each LED is connecting the negative pole of the LED, which is also the cathode, to the negative line of the proto board. If you look closely, when we position ourselves above this line, we have a horizontal line that basically represents the negative pole. At the bottom, we have the line that represents the positive pole. In this case, we are not using the positive pole on the proto board, just the negative pole. So, all the cathodes or the short leg of each LED must close the circuit by connecting to the negative line. We must also do this through a resistor to avoid damaging the circuit and the LEDs. So we have a resistor connected to the negative side, which is 330 ohms in this case. And we are connecting this directly to the negative pole. Now, regarding the anode or the longer leg of an LED, we see that each anode of each LED is connected to a different pin on our Arduino, starting from pin number 2 for seconds up to pin number 7. From pin number 8 to pin number 13, we have the LEDs that represent the minutes. Note that all the anodes are connected to each of the pins on our Arduino, and also keep in mind that they are arranged according to the diagram. The LED on the far right is connected to pin number 2. The pin before the last is connected to pin 3, and so on until reaching pin number 13. If we look at the yellow LEDs, we see they also have their respective resistor connected to the negative pole. In the case of this set of LEDs, we see they do not connect to the pins at the top of the Arduino. Instead, they are connected directly to this section labeled Analog In. This allows us to instruct our Arduino that these inputs, although labeled as analog, behave in a digital manner. Therefore, we are connecting each of the LEDs to each of the pins from A0 to A4 on our Arduino. Notice that they also have a specific order. The LED on the far right connects to pin A0 and pin A4 connects to the one on the far left. It is very important to place the LEDs according to this diagram. Lastly, we have here a black wire that will connect our negative pole on the proto board to our ground pin or a negative pin on the Arduino. Here, we can connect it to the pin labeled ground, or we have 2 pins below that are also ground, so you could connect this wire to any of these pins labeled ground. This is the overall diagram of our binary clock project. Let's see how it looks when physically connected. We have already seen the connection diagram of our circuit. Now, let's see how to interpret the diagram to physically connect the components. If you remember, this is the connection diagram, which you can find in the lesson resources. To better understand it, we will isolate the LED connection located on the far right of our diagram to see step by step how to connect the different components. Okay, here we have our first LED and its isolated connections, specifically the one on the far right. What you need to notice is that you must close the circuit that connects to the LED. You need to do this with each of your LEDs. Let's see how to do this. The first thing we need to do is identify that each LED has 2 legs, one longer than the other. The longer leg, known as the anode, represents the positive pole, while the shorter leg, called the cathode, represents the negative pole. Now, to correctly place our LED, we will set up our proto board and position the first LED on the far right of the proto board, following the same pattern seen in the figure, meaning the longer leg on the right and the shorter leg on the left. We can see that the diagram image on the left follows this same pattern. Once we have placed the legs of the LED on the proto board, we see that we can no longer differentiate which pole is which. So you must be very careful when positioning the LED, ensuring that the poles correspond to those in the diagram. Perfect. Once we have placed the LED, we see that the connection diagram shows that the LED is connected to a resistor at its negative pole. Basically, this means we need to place the 330 ohm resistor in one of the holes either above or below the LED. If you're wondering what this purple line means, it's a connection between the upper segment and the lower segment of the proto board. Why are we doing this? Because remember that a proto board connects as shown in the image. Here we can see that in the center, which is this gap we see right in the middle, it interrupts the connection between the upper and lower parts. In other words, this line is not connected to the line below, so in our diagram, we're connecting both sections through this purple wire we see here. In the case of the black line we see at the bottom, we are connecting this resistor to the negative pole line of the proto board, which is this line we see here. We make these connections mainly due to the limitations of circuit design software, as they have component sizes that are not at all similar to the real world. Okay, now we know what these lines mean in the diagram. Now, in the physical project, we connect directly from the upper section of the protoboard to the blue line that represents the negative pole. We can see this since we have the resistor here, and notice how we make a jump from this hole to the hole with the negative pole on the protoboard. This is possible to do physically because our resistor is large enough to make this connection. It is equivalent to being able to extend this leg in our diagram to this circle or hole we see on the protoboard. If the real-world resistor were the size depicted in the diagram, we would likely have to use jumpers to make the connection. We already know how to connect the negative lead of the LED and where to connect it. Now, we need to make the connection for the positive lead of the LED. What we'll do is connect one end of the jumper to one of the holes above or below the positive pin of the LED. In my case, I have connected it to the hole beneath. We can see this both in the diagram and in the physical circuit. The other end of the jumper needs to be connected to one of the pins on the Arduino, according to the diagram we saw earlier or that you have at your disposal. For the first LED, or the one located on the far right, it connects to pin number 2, so we'll need to do the same in the physical circuit, as shown in this photograph. We can see how we bring the red wire, or the red jumper, to pin number 2 of our Arduino, just as it appears in our connection diagram. Returning to the topic of the protoboard, it is a fact that you will use more than half of the protoboard we have here to place your different LEDs. There's a very important point here, which is that in the diagram, we see that the positive and negative rails of the protoboard have continuity from start to end. However, in my protoboard, we can notice that the positive and negative lines, those we have here at the bottom and the top, are cut in half. This means, as you might imagine, that from one end to the other, there is no continuity. In other words, there is no continuity between this part on the left and this part on the right, due to this cut we have here. Some protoboards do have this continuous line, which means they provide continuity from start to end. But most protoboards have this cut in continuity precisely at the halfway point. We need to connect a jumper between both sections to work without issues. In our circuit, we have only placed the jumper on the negative pole, as it is the only connection line we'll use for this project. In the diagram, we also see a black line connecting the negative pole of the protoboard to one of the Arduino pins labeled GN, which stands for ground. Here we have this connection. The Arduino Uno has 3 of these pins, so it doesn't matter which one you connect to. Here you can see how I made this connection between the protoboard and the Arduino. Notice that I connected the cable at the bottom left of the protoboard. This is to avoid interference with the other connections of the other LEDs, and see how we're connecting directly to the pin labeled GND on the Arduino. Great. These are the basic connections you need to make physically. Now, you need to keep placing each of the LEDs with their respective resistors to the corresponding pins. Remember, there are 6 red LEDs connected to pins 2 to 7, 6 green LEDs connected to pins 8 to 13, and 5 pins connected to inputs A, O0, A5. Once you integrate all the LEDs, you'll have a protoboard like the one we see in the photograph. Now let's see how to program this wonder from the Arduino IDE. It's time to get down to the Arduino code to make our assembled circuit work. Here we have a completely clean file, along with the 2 common methods of a newly created file in Arduino IDE. Let's start by recalling a bit about our project. As we remember, we have 3 main sections: a set of LEDs representing seconds, a section of LEDs representing minutes, and a final section of LEDs representing hours. While we could define, for example, a variable called pin2 equal to pin2. To initialize this pin, remember that a pin must have either an input or output initialization. If we had to do this manually, it would take quite a bit of code. What we will do instead is represent this series of LEDs through an array, where each array will correspond to a specific part of time. That is, we will declare an initial array, which we will call setPins. To indicate that this is an array, we need to place these brackets. and we will denote that it is equal to a set of values within these curly braces. We will then place 2, 3, 4, 5, 6, and 7, which means we will have a set of integer numbers that will form part of this variable called set pins. We will do the same for the minute pins, naming it min pins, which will be equal to the following LEDs or pins: 8, 9, 10, 11, 12, and 13. Finally, we'll represent the hour pins by creating a new array, which we will call hour pins. And this will be equal to 14, 15, 16, 17, 18, and 19. Remember that this value represents which pin each LED is connected to. As you recall, the pins for the seconds are connected from pin 2 to pin 7. The LEDs representing the minutes are connected from pin 8 to pin 13. And as mentioned in a previous video, we can use the analog pins as digital pins. The digital pin numbers corresponding to these pins range from 14 to 19. The next step is to initialize the values of these pins to indicate whether they will be set as input or output. In this case, since these pins will be connected to some LEDs, we will specify that we want these pins to be outputs. Let's configure this method called setup, remove this comment, and to quickly iterate through this array, we will use a for loop. We will declare a variable int I equal to 0 as an array starts its indexing from 0. The index represents the position in the array, which goes 0, 1, 2, 3, 4, and 5. Here we are missing a comma, and this applies to each of the arrays. In the second array of min pins, the value 8 corresponds to index number 0, 9 to 1, and so forth in all arrays. That is why we declare a variable with a value of 0. Next, we need to specify the limit or when this for loop should stop executing. In our case, we will indicate until I is less than, and here we need to specify the size of the array we are interested in, which in this case, we'll start with this segment array. Unfortunately, in the Arduino IDE, we do not have a built-in functionality to get the count of elements in an array. However, we can do this in other ways. While we could manually write this value, meaning we could state that we have 6 objects or 6 elements in this array, we'll learn to do this so that it works with any array. We will temporarily comment out this for loop and initialize serial.begin with 9600 so we can examine some values during runtime. As part of the Arduino documentation, we learned about a method called sizeof. Reviewing the Arduino documentation, we see that this sizeof method returns the number of bytes for a variable type or the number of bytes occupied by an array. In our case, we have an array composed of integers, so we are interested in examining this data type, which is the integer type, and we see that it indicates that an integer occupies 2 bytes. Therefore, by calculating, we will multiply 6, the number of elements, by 2 bytes, which should theoretically give us a value of 12 bytes. Let's see if this is true, as we have a set of 6 elements in the array. So we will pass sec pins as a parameter to this method. We will temporarily store this value as temp, and it will be equal to sizeof. We will print this value we stored to see what gets printed. Okay, let's run this program to see what this serial.print returns. Let's indicate that we want to upload the sketch. Your Arduino must be connected beforehand. Okay, the sketch has been uploaded. Now, let's open the serial monitor. We see that indeed, the number of bytes stored in this variable is 12. Let's test the same, but now with this array called our pins, so we check the size of our pins to see what its value is. Okay, and we see that it returns a value of 12, which is correct, since we have 6 elements in this array. Let's remove one additional element here, re-upload this sketch, and check again. This time, we have only 10 bytes. With that in mind, we can perform a calculation to determine the number of bytes we have here, divided by the number of bytes of an individual element. If you recall, an individual element, which is of integer type, is equivalent to 2 bytes. Therefore, if we perform a calculation, for example, let's assign temp2 to sys, we will use secpins, which results in 12, and we can divide it by the number of bytes of a single byte. Next, We will print the value of temp2 and see what happens. Okay, and we see that we are successfully printing the number of elements in the array. So using this formula or operation here, we can obtain the number of elements in any array. Knowing this, we will define a set of new global variables. The first one will be called sec size, which will be equal to exactly this operation we have here. We will then copy this that we have here and paste it into this variable. Another thing we could do, if we wanted to make this a bit more universal, is to specify that we want to obtain size of sec pins at its value 0. What we're doing here is essentially reusing CISO to obtain the number of bytes of the first element. We're indicating that we wish to access the first element through these brackets and the index, meaning this would be equivalent to having a value 2 in the case of the first array, resulting in this value 2. We are doing this since we are obtaining the number of bytes of this element. In the end, this is equivalent to performing the division operation of CISO sec pines by 2. This is just slightly more universal since we are directly obtaining the data type we have in the first array. This operation could serve us with an array of another data type, for example, a floating point type, or a double type, etc. We'll leave this as it is, and we will declare another variable called minsize, which will be equal to exactly the same operation, changing only the name of the array. We will then paste min pins here and min pins here as well. Finally, we will declare a third variable called hour size, which will be equal to, we copy again the operation, and we will copy our pins to paste it into the size ava. With that, we can now obtain the number of elements in each of the arrays. Now that we have this ready, let's remove what we wrote earlier. Let's uncomment our for loop, and instead of writing less than 6, we will specify less than SECC 6. Remember that this will return, in the case of the first array, a value of 6. Later, we will complete this for loop declaration with a plus plus. We place the closing parenthesis in a couple of braces, where we will write some functionality that will be executed for each cycle. What we are really interested in executing during each iteration is setting an output value to each of the pins we have here. Therefore, we will write or invoke the pin mode functionality. Which pin will we initialize? Well, each of the elements of our array, in this case from value 2 to value 7. So we will write here pin mode SEC, pins of the current value of I, and we will indicate that we want these pins to have the functionality of output. With this, we will traverse each of the values in this sec pins array, and depending on the value of this variable I, we will assign an output value to it. We will repeat exactly the same operation for each of the other arrays. In the case of the second for loop, we will indicate that while I is less than min size, we specify that the array we will use is this min pins. We will copy our for loop one last time. And this time, we will set I to be less than our size. And we will use this, our pins array. With this, we have completed the declaration of our method called setup. In this method, we initialized each of the pins that make up our circuit with an output value. Now, let's move on to the second loop, which is the loop that will be running continuously. So, we will remove this comment. What we need in this loop is to have some type of container or variable that indicates the current second, minute, and hour. To do this, we will declare a series of variables that will be global variables. So before the setup method, we will declare these variables. Int seconds, which will represent the seconds. Int minutes, which will represent the minutes. And we will also declare the variable that will represent the current hour. We could initialize, if we wish, these three variables with a specific value. For example, we could set seconds to 30, minutes to 30, and hours to, for example, 5. This means it would be 5:30 in the morning with 30 seconds. What this loop needs to do is increment the value of the seconds variable, since, as we know, the seconds are what actually track the process when the minutes and hours change. After this seconds variable, we could place a delay to wait exactly 1 second before proceeding to the next count of these seconds. This means we will increment this variable's value by 1. Wait 1 second, and that is how this loop will execute. Thus, 1 second will be added to the seconds variable, or a value of 1 will be added to the seconds variable every second. After declaring this increment, we need to carry out certain validations. If seconds exceed 59, we need to change the minutes by adding 1 to this minutes variable. So we'll check if seconds is greater than 59. What do we do when seconds reach 59? First, we need to reset this variable to 0, and we need to increment minutes by 1. Next, we also have to validate if minutes is less than or greater than 59, because if we exceed 59, we need to change the hour. Therefore, we will indicate that if minutes is greater than 59, we will do exactly the same process. That is, set minutes to 0 and increment hours by 1. But we also need to check hours once again, because if hours exceed 23, we need to reset the counting cycle for minutes and seconds. So, if this hours variable is greater than 23, we will set hours to 0. It really is a fairly simple process. We just need to validate seconds, minutes, and hours. Once we have executed this check, that is, after this if statement, we can determine where this if ends by looking at the start of the brace. Notice how the Arduino IDE indicates where this set of braces ends. So, before the delay, we need to carry out the printing or displaying of information on our LEDs. How can we accomplish this if we only have the representation of the second, minute, and hour as integer values? Well, we can go back to our reference guide and see if we have any functionality to work with bytes. We can see that we indeed have a section here that says bits and bytes. We are interested in a functionality called bit read. Let's see what it's about. Okay, the description indicates that it reads a bit from a number. This is exactly what we're looking for, to read a bit from an integer. Notice that the syntax indicates it should be written like this, and that this x, or parameter x, refers to the integer from which we will read, while n represents which bit we will read from that integer. This is the most important part, starting with the value 0 for the bit on the far right, and it also indicates that it can return a value of either bit 0 or 1. What does this mean? Let's do an example. Suppose we have the value 1 in our variable called seconds. Then, if you recall, we would have 6 LEDs, and to represent the number 1 in binary format, this is the representation. If we wanted to represent the number 2, this is the representation. If we wanted the number 3, we would have this representation. You can do this on your Windows calculator as I showed you earlier. So what we would need to do is use this bit read function to read the bits, starting from the last bit, then the second to last bit, and so on for each bit. This value would be what we need to send to our circuit that we assembled earlier. So we could conclude that we need a loop to read each of the values that correspond to our seconds, minutes, and hours. To implement this functionality, we will declare a new method called displaySeconds. We haven't created this method yet. We will create it after the last brace we have here. So we'll specify void displaySeconds. We place a pair of parentheses and a pair of braces to declare the functionality of this method. Now, we will specify for int I equals what will be the initial value of I. Well, let's see what happens if we initialize this variable with a value of 0. We will add a semicolon. And we will state that while I is less than sec size, remember that this is the same as we did earlier. We will indicate that at the end, I++. What we will do inside this for loop is store each of the bits corresponding to a value from the LEDs. Now, we will declare a current second, and this will equal, we will invoke the bit read functionality, seconds. In other words, we want to read the variable seconds, which will have numbers from 1 to 59, and we want to read the bit according to the for loop. So we would read from right to left, from number 0 to number 5. If we return to our example, we would have 0, 1, 2, 3, 4, 5. The bit number would be value we would store in this variable called current. Next, we will specify that we want to send the signal we obtained, either a 1 or a 0, to the function digital, right? This function is used to send that signal. We will specify that we want to send it to the pin located at I, current. In other words, we will send to the pin, in this case on the first iteration, to pin number 0, the value of current second, which we have previously discussed as the bit position of this variable seconds. We can perform a type of debugging to see if the correct values are being sent in our functionality, or in this method, display the seconds. We can do this by declaring a serial.print inside this for loop, and we will send current. This is to see what values are being sent within this for loop. After the for loop, we will indicate serial.println to have a line break for the next execution of display seconds. Before running the program, we will go back to the variable seconds and set its value to 1. This is to observe the iteration starting from second 1. Now, let's run the program. We launch the serial monitor. Okay, and here we have the execution. Here, this execution starts from second number 2. Here, if you look, we have 2, we have the second 3, 4, etc. Here, if you noticed, we have a slight problem. And the issue is that the signal is being sent from left to right, but we need the signals to be sent from right to left, as that's how we've set up our sections. So this needs to be reversed. The 1s should be at the end, and the 0s at the beginning. Okay, let's fix this by going back to our loop 4, and we will execute the loop in the opposite direction. Instead of initializing this variable I with 0, we will initialize it with size -1, which means starting with the value of 5 in the first iteration. Next, rather than stating that I should be less than size, we will say that I should be greater than or equal to 0, and instead of using I++, we will use I. Okay, let's upload this sketch again, check the serial monitor, and see that we've flipped the functionality of printing our bits. With this change we've made, we can now copy this method, removing this serial.println. Let's paste it once, and instead of display seconds, we will rename this method to display minutes. We will make some changes. For example, instead of set size, min size, we will declare a variable that will change current second to current minute. We will perform a bit read of minutes. In digital write, we will indicate that we want to send the signal to one of the values in the array min pins of current minute. Let's print this serial.print. Once again, we will copy the method, but this time for the hours. We will call this method display hours, indicating that I will be equal to horse size -1. We will declare a variable named current hour. We will read the variable hours. In digital write, we will specify that we want to access an element of hour pins. Instead of current minute, use current hour. Okay, let's check that our program is running fine. Once it has been compiled successfully, we will quickly return to our loop method, which is the main method. We will indicate that after display seconds, we want to display minutes, meaning we want to show on our proto board or in our circuit which LEDs need to be lit for a minute. Lastly, display hours. With these changes we made, let's upload our program and you can see how our circuit is now functioning correctly. If you want to change the hours, minutes, and seconds from which the clock starts, you would need to modify the values of these variables we have here. With this, we conclude this module on how to build your first binary clock. Previously, we created an electronic piano using a set of buttons, and in a specific project, we had a special button to play a melody. In this case, we will see how we can replicate a melody but using arrays. When we talk about music, specifically about the scores that help us capture music, we have two very important elements. First, the musical note, which will represent the frequency for the tone method on our Arduino. We also have the duration of the note, which is basically the spacing or the delay between different notes. With this knowledge, we can go to this website on boylatestgear.com and explore some scores. This site basically contains a collection of scores that will serve our purpose. Let's search for a very well-known song, for example, Canon in D. We will use a filter on the left to indicate that we want only one instrument. I recommend looking for a song that has a single line. For instance, if you look at this song I just opened, it has two lines connected by a brace. We are not interested in this type of score. We want the ones that have a single line, like this one for Canon in D that says violin solo. In fact, let's open the score. On this website, you need to register to download a file called Music XML. Let's proceed to download this file. You might wonder, how can we transfer a musical score as we see it here to Arduino code? Well, we will see that in a moment. We can click on this play button for this score. You can hear how this song starts playing thanks to this score. This is due to the musical notes marked as part of the score and the duration between each of them. These are the two pieces of information that interest us for our project. Now, let's carry out the conversion of the musical notes to understandable code in Arduino. We have seen that we have described a file called Canon in D, violin solo, which I have here. We see that if we try to open this file with a text editor, it shows a text that is not recognizable to us. Let's close this file, and I will open this file with Notepad. As you can see, we also have unreadable text here, but what interests us are basically the pair of letters at the beginning that indicate this file is compressed. To open this file, we can rename it by adding a.zip extension, indicating that we want to change this extension, and now we have a zip file that we can decompress. Let's decompress this file, and notice that we already have a folder. We can open the folder, and now we have an XML file, which if we open again, shows us an XML file or a markup language. Note that there are tags as we specify an opening tag and a closing tag for each of these elements. Here we have this closing tag. Okay, let's continue discovering this file. Also, if we analyze the bottom of this file, we see that we arrive at a section where musical notes begin to appear. Here it specifies which musical note it is and in which octave this musical note is located. These octaves relate to the frequencies we discussed earlier. These have different scales for reproducing musical notes, some being deeper and others higher. This is defined by the octave in which this musical note is found. Notice that we also have the duration, which basically represents how long a musical note will play. However, extracting this information from this file to create our code in Arduino would take quite a bit of time. Therefore, as part of the resources attached to this chapter, I will provide you with an application. The application is the one you see here. What we need to do is open the .mxl file. I will go back to the Explorer and rename this file again with the .mxl extension. But first, I will rename this folder to avoid any conflicts. So I remove the extension from the folder and will rename this file from .zip to .mxl again. Okay. We return to the application and indicate that we want to open the .mxl file. Here we have this file ready, so I proceed to open it. Well, now we have a set of numbers, and basically it represents on the left the musical note according to the scale it belongs to, which means this is a frequency to be played as part of our tone method. On the right, we have the duration of each of these notes. These notes are synchronized. For the first note, we have 8 seconds of duration. For the second note, we also have 8 seconds, and so on. What we're going to do now is click where it says Play Preview. This will start the playback through a code, in this case, in C# language. Don't worry about this. Basically, what it allows us to do is play this song or simulate this song. Here we are listening to this song. In case you click on Play Preview and want to stop this application, you will click where it says in the Task Manager Music XML Parser, which says at that moment that it is not responding because it is executing a resource-intensive task. And we will click on End Task. Okay, I will launch this application again. I will reopen the file, and this time I will not press the Play Preview button, but I will click where it says Convert. This creates code in Arduino for us. What interests us at this moment are two arrays that have been created for us. The first array represents the melody or the musical notes of the song. I will proceed to copy this array up to the semicolon. And I will proceed to create a new circuit in Tinkercad. In this new circuit, I will drag an Arduino Uno. I come to the code section, specify that I want a text section, and before the setup method, I will proceed to paste this code that the application has generated for us, which is basically the melody of the song. I will proceed to remove this pre-created code. We return to the application, and we have a second array that represents the duration of each of the notes. I will proceed to copy this array and paste it after the first array. We now have two arrays. The first array represents the melody, and the second represents the duration of the notes. As I mentioned earlier, these two arrays are related, as the first musical note corresponds to the time specified in the second array, and so on for each of these values. Once we have copied these arrays, we will proceed to connect a speaker to our circuit to listen to the song. I will then connect a summing device, or a buzzer. I will connect the negative pin to the pin marked G and D. I will connect the positive pin to an Arduino pin, for example, pin number 11. Okay, this speaker is all we need for our project. Let's return to the code. Now, let's go to the setup section, as we will play the song at the start of executing our sketch. Within the setup method, we will first get the count of elements in our arrays, just as we did in the previous project. We specify a variable called count, which is equal to CCSUP. We specify that we want to obtain the amount in bytes of our array called melody between CSOF, and specify that we want to get the size of the first element of either of the two arrays. We will specify melody in the index 0 in brackets. Okay, with this we obtain the number of elements from one of the arrays, in this case the array called melody. Next, we'll create our for loop, specifying for int I equals 0, I is less than count, semicolon, plus plus. This is to iterate through each of these arrays. When we obtain one of the elements, we will indicate that we want to execute or call the tone method, passing our pin where the speaker is connected. We can create a variable for this purpose or specify it directly. We will proceed to create a constant to specify this pin, so const int buzzer will be equal to 11. Here I indicate or make the change for buzzer and specify that I want to execute the frequency located in melody and in brackets, the variable I. With this, we will execute each of the elements in this array. How do we specify the duration of each note? Well, we need to use the second array, and for that we will indicate that we want to use a delay with the time we will wait specified by note durations at index I. As I mentioned, these two arrays are connected. One represents the musical note, and the other indicates how long that musical note will play. Since these pairs of arrays are linked, we can use or reuse this variable. Once we execute this musical note, we indicate no tone to stop this execution precisely, and we pass the pin where our buzzer is connected. If we start the project simulation, we see that Tinkercad is currently having some issues. Therefore, we will proceed to see it physically. Here we have our project physically assembled. I have only connected the speaker to pin number 11. Let's upload the sketch and listen to the melody. With this, we have recreated a song using the tone method, but now we have greater control over the notes and their corresponding durations thanks to the arrays. If you are a musician, you could even make changes or improve this project. What? Earlier, we learned about one-dimensional arrays and worked with them in some projects. Well, there's a way to have not just one dimension, but two dimensions. Here's what a two-dimensional array looks like. Notice that we have already introduced multiple rows to our array. Following the same practice as with one-dimensional arrays, these types of two-dimensional arrays start at index 0. But this time we have both columns at index 0 and rows at index 0. Also, following the analogy of an Excel document, with this type of array, we would enable the editing of rows and columns, so you'll have a better idea of how these arrays work. Let's go to Tinkercad and see how to create and manage this type of array. We are now in Tinkercad. Let's proceed to see how to declare a multidimensional array and how to work with it by dragging an Arduino Uno board to our designer. Go to the Code section, indicate that we want a text section, remove the pre-created text that appears, and let's proceed to look at multidimensional arrays. First, we will see how to declare a multidimensional array. To declare this type of array, we will specify what type of data the arrays will hold. As you may recall, we need to specify a single data type. In my case, I will handle an array of integers and will give our array a name, for example, multi. In fact, its declaration is very similar to that of a one-dimensional array. We need to place a pair of brackets and specify within them the dimensions or the maximum size we want for each of the dimensions. We can specify, for example, that we want an array with 2 rows and 2 columns. This first section, or this first parameter that we specify here, indicates the number of rows, and this second value indicates the number of columns. So when you see 2 declarations within brackets, it means you are dealing with the two-dimensional or bidimensional array. The next step is to understand how we can assign values to our array. Here we have specified that we need an array of 2 rows and 2 columns. Therefore, we can fill that entire space, or this number of rows and columns, with integer values. To perform this action, we will invoke our array and place in brackets the row we wish to access. We will indicate that, for example, we wish to access row number 0, as it is within the range or is less than the specified amount. Subsequently, we will again declare a pair of brackets and specify which column we wish to access. With this, we will have access to row 0 and column 0. Here we can assign a value, for example, 32. Making an analogy with Microsoft Excel, we would indicate that we wish to access row number 0, which is equivalent to row 1 in Excel, and column 0, which corresponds to the letter A. We would be entering the number 32. We return to Tinkercad and will proceed to access a different cell. We will write again multi, and within brackets, we will indicate that we want to access row number 0 and column number 1 to assign a value, for example, 51. With this, we would be indicating in Excel that we wish to remain in row number 0, which would be equivalent to row number 1 in Excel. But this time we would access column number 1, which corresponds to column B in Excel. Here we would enter the number 51. As you can see, we already have behavior very similar to a two-dimensional array in a Microsoft Excel spreadsheet. Let's continue filling in this information. We will indicate that we want to access row number 1 and column number 0 to add a value of 200. In this case, we have already changed the row. So, as we have changed the row in Excel, following the same analogy, we would have changed to row number 2 to write a value of 200. Since we indicated that we want to access row number 1, but be in column number 0. Therefore, we would have a value of 200 in this position that we see here. We could fill in the last value through multi. We indicate position 1 of the rows and position 1 in the column section, fill it with a value, for example, 22. In Excel, we would have accessed row number 1, which is equivalent to row 2 in Excel, and column number 1 to assign a value of 22. This is how we can assign values to the different ranges within our two-dimensional array. Okay, we have seen how to assign values to the different cells of a two-dimensional array. Now let's see how to retrieve data from our cells. Let's proceed to declare, for example, an integer variable. Let's call it valor, which is equal to, and to access a specific cell, we will call our array, specifying the address or position we want to obtain. For example, let's indicate that we want to access our row number 1 and column number 0 to see what we have in the cell. We will perform a serial.begin 9600 to see this value in our serial monitor, and then we will do a serial.println of the value. Let's initiate the simulation to see what is displayed, and notice that we are successfully displaying the number 200, which is the value located at position 10, as we can see here. Another common way to declare different arrays is to declare a variable named rows, equal to the value of the rows we need, for instance, 2 in this case, and also a variable that references the number of columns in our code. We will proceed to change this value to rows and this value to columns. If we start the simulation, notice that we have once again a value of 200, which will help us later to perform some type of check. For example, how many rows we have available in our array and carry out different iterations or other operations. We have declared a two-dimensional array. Now, let's see how to iterate through each of these values using for loops. To visualize this more practically, let's return to the slides. Okay, we will learn how to traverse two-dimensional arrays. In this case, an array with 2 rows and 3 columns. I have placed some values to make the example a bit more realistic. The general idea for traversing a two-dimensional array is based on iterating through each row while evaluating that row and retrieving each of the columns that belong to it. In this case, the index would be 0, 0. After evaluating this column, we would evaluate the second column, which would be positioned at 0, 1. Next, we move to the third column, positioned at 0, 2. And once we finish with the columns, we would evaluate the next row. To retrieve the value, we would evaluate the first column of that row, positioned at 1, 0. Next, the second column of the same row at location 1, 1, and finally the third column at position 1, 2. So far, we have repeated a pattern. Let's revisit the traversal, paying attention to the progression of the indices. Let's start with the location 0, 0, then 0, 1, 0, 2, 1, 0, 1, 1, and finally 1, 2. This is the pattern we need to follow in programming to retrieve the values. Do you notice any specific pattern? We can see that we first traverse row number 0, and when we are in this row, we retrieve each of the columns. When we move to row number 1, we perform the same operation by iterating through the columns. With this in mind, let's consider how can we iterate through the rows. Well, previously, we saw that with the for loop, we could iterate through one-dimensional arrays. Let's do the same to iterate through each of the rows. But it doesn't end there, as we also need to iterate through the columns. To carry out this task, we will use a second for loop, which will handle iterating through the columns of each row. To clarify any doubts, let's do a virtual walkthrough of what would happen if we executed the program with this array. First, we initialize the variable I of the array with a value of 0. Check if I is less than 2, which is correct, and move to the second loop, where we create a variable for internal use in the for loop, called coda, with an initial value of 0. J, starting at 0, since it is less than 3, would execute the inner line, which returns the value of cell 0, 0. That is the value 50. Once we obtain the value, we would add 1 to j, resulting in a value of 1. We would compare if the value of j is less than 3, which is still correct. Therefore, we can now obtain the value of the cell located at 0, 1, which is a value of 65. We would add 1 to j, which would then have a value of 2. And since j is again less than 3, we would retrieve the value of cell 0, 2, which is 41. We add 1 to j, but this time, since j is no longer less than 3, we exit the loop. Since the second for loop is nested within the first, and the first loop is still running, we add 1 to the variable I, which now has a value of 1. Since I is less than 2, we re-enter the for loop, and as it's a new loop, the variable j is created again with a value of 0. The check against 3 is performed, and since it's true, we obtain the value from cell 10, which is 365. We add 1 to j, and since j is still less than 3, we get the value from cell 12, which is 54. We add 1 to j again, and again j is less than 3, so we proceed to get the value from cell 12, which is 3. Once more, we add 1 to j, but this time, since j is not less than 3, we exit the loop. As we remain inside the first for loop, we add 1 to the variable I. We check if it's less than 2, but since I is no longer less than 2, we do not exit this first loop. With this, we have finished executing the retrieval of all values from our two-dimensional array, and we could proceed to perform other operations. This is how to iterate through a two-dimensional array. Let's see it practically in Tinkercad. Okay, we're back in Tinkercad. What we're going to do now is iterate through each cell of our two-dimensional array to obtain the different values and perform operations, such as addition or subtraction, etc. Let's proceed by going below this serial.begin and start writing our pair of for loops to iterate over each cell of our two-dimensional array. Let's start by creating the first for loop, defining an internal variable I equal to 0, followed by a semicolon, specifying that I is less than rows, followed by another semicolon, and then incrementing I. This is because rows contains the number of rows and columns, but since numbering starts at 0, we need I to be less than rows. Once this is done, we create a second for loop. We'll call this internal variable j, starting at 0. We write the semicolon and indicate that while j is less than columns, we will increment j by 1. Let's comment out the serial.println we have at the end and replace it with this serial.println to display the value at the position of I and j in our array. So we write multi, then the first index, which is rows with the value I, and specify which column is represented by variable j. We close this println invocation, clear any content in our serial monitor, start the simulation, and here we have a problem as we've only placed one diagonal. Let's add the second diagonal, start the simulation, and if we look at the serial monitor, notice that we are successfully displaying all the values, starting with 32, then 51, 200, and 22. With this, we've satisfactorily covered our two-dimensional array. Let's stop the simulation, and I have a couple of additional comments to make. There are other ways to perform the initialization of a two-dimensional array. Let's see it practically. We'll create this variable and indicate that we want to assign it a value. Here, we will write a pair of braces, one opening and one closing, to represent the different elements that are part of our two-dimensional array. Inside this pair of braces, we will write another pair of braces that will represent the elements in the first row. We place a comma, write another pair of braces, and the second element, or the elements within this second pair of braces, will represent the elements in our row number 1, or in our row indexed at 0, or in our row number 2. So here, we begin to write the different elements, 32, 51, which are part of our row indexed as 0. We will place inside the second pair of braces the elements 200, 22. To make this representation more visual, we can press Enter to place this line on a new line. We will press Enter again, where the definition of the first content of the braces starts, and we will place this second content directly below it, and we will proceed to place the closing brace at this point. With this, it will be more visually clear what the content of the first row is, along with its respective columns, and what the content of the second row is, also with its respective columns. With this, we can comment on this line using a multi-line comment. We will close the comment, check that everything continues to function correctly, start the simulation, and notice that it shows us a problem. It indicates that the variable named multi may not be initialized. If you can see the code, we don't actually have any substantial changes that would lead us to believe there is a problem in this line marked in red. However, This issue is occurring because we are using the initialization of this multi-array with variables, as we see here. To correct this problem, we must assure the Arduino compiler that these variables will not change, as this is essentially why this issue is happening. Arduino understands that this pair of variables can change, since we have a set of variables that may change over the course of the application or the sketch. Therefore, what we need to do to resolve the issue is to specify or indicate that they are constants, which informs Arduino that these variables will not actually change. If we start the simulation again, notice that we are no longer encountering any issues, and we are once again displaying the correct values as part of the serial monitor. Okay, here we have them. Lastly, what would happen if we removed the declaration of rows and columns, just as we did with a one-dimensional array? As you may remember, in a one-dimensional array, we could remove the assignment of the number of elements and initialize this array satisfactorily. What if we tried to do this with a two-dimensional array, that is, removing this assignment? What will Arduino attempt to evaluate? The number of elements through the assignment as we have here. Well, we started the simulation to see what happens, and notice that we have a problem here. And the error indicates that this is a multi-dimensional array, and that it must have a limit for all dimensions except for the first one, which we have here. What this means is that in the case of two-dimensional arrays, we do need to specify the number of elements starting from our second element, or our second definition of the multi-dimensional array. If we leave the first assignment empty and only write the number of columns, notice that we start the simulation and this compiles satisfactorily. So we could leave this first element empty, but we must specify what the different values are that follow in this declaration. Although it is advisable to always specify the number of rows and columns in a multi-dimensional or two-dimensional array. In this section, we will create a project that will allow us to better understand the topic of two-dimensional arrays. This is a project involving a LED matrix. Once we are in Tinkercad, we will proceed to drag an Arduino Uno board onto our interface. We will also proceed to drag a small breadboard. We will position it over our Arduino board and proceed to create a LED matrix. To create this LED matrix, we will drag an LED component onto our breadboard surface. Next, we will drag another LED component which will be placed exactly to the right of our first LED, leaving a row space in between. We place the third LED on the surface, and now we have a diagonal row of 3 LEDs. We will proceed to copy these 3 LEDs by pressing Ctrl-C and Ctrl-V to have 3 new LEDs. We will then drag these LEDs, positioning them one line after the last LED as shown on the screen. We will copy and paste these 3 LEDs again and position them exactly in the next line from the last LED. In this way, even though we do not have a matrix that is exactly horizontal and vertical, we do have a simulation of a LED matrix. The idea is that we can manipulate these LEDs through a two-dimensional array. We will proceed to connect these LEDs. We will connect each of the cathodes to the negative rail of the breadboard. Let's color these wires black. We'll do this for each of the LEDs. Okay, we've connected the cathodes. Now let's proceed to connect each of the anodes of our LEDs. We'll start numbering from the first LED. This first LED must go to pin number 13. Let's connect this terminal of our LED to pin number 13. Let's connect the second light or the second LED to pin number 12. Let's connect the third LED to pin number 11. Let's place the fourth LED on pin number 10. Let's place the next LED on pin number 9. The next LED will be connected to pin number 8. The next LED will be connected to pin number 7. The next LED will be connected to pin number 6. The last LED will be connected to pin number 5. Okay, once we've improved the wiring, we now have our circuit ready to start coding this project. Let's go to the code section. We'll indicate that we wanted text, so let's remove the default text. The first thing we'll do is specify the number of rows and columns we need for our two-dimensional array. Here, as you can see, we have 3 elements for the columns and 3 elements for the rows. Therefore, we will create 2 integer constants. The first constant will be named rows, and it will be equal to 3. Since we want 3 elements for 3 rows, let's create a second constant called columns, which will also be equal to 3, as we want 3 columns in our project. Next, we will proceed to create a two-dimensional array. We will call it, for example, matrix. And this matrix will be composed of the number of rows defined in our rows constant, and also a number of columns defined in our columns constant. We can initialize our matrix right away, and that is what we will proceed to do. We initialize the matrix, and to control this matrix of LEDs we have here, we will start specifying the different elements that make up the matrix, beginning with the LED located on the far left, the one we have here. We will then number this LED, followed by this one, then this one, and so on. To carry out that task, I will proceed to create a set of curly braces, and remember that each of these sets or subsets of curly braces specifies each of the rows. Let's specify the first row, which consists of our first LED connected to pin number 13. Our second LED is connected to pin number 10, as we can see here. We are connected to pin number 10, and the third LED is connected to pin number 7. We then number it 7, close this bracket, place a comma, specify another pair of brackets, one opening and one closing bracket, and we'll specify the elements of our second row, starting with the one connected to pin number 12. The second LED, part of our second row, is connected to pin number 9. We then write 9, and our last LED is connected to pin number 6. We place a comma after this closing bracket, write another pair of brackets, and as you can see, we have the decreasing pin numbers. That is, we have 13 and 12, so the next number will be 11. Here we have 10 and 9, so the next number will be 8, and we have 7 and 6. Therefore, the last pin will be pin number 5. With this, we have defined our array of the different elements that will make up our LED matrix. Let's see if this works correctly. We will proceed to declare or initialize the serial class through serial.begin at 9600. We will write our for loops. As you might remember, we need a first loop that iterates through each of the rows. So for int I equals 0, I is less than rows, semicolon, I plus plus. We also need a second for loop that interacts with the different columns. So for an int variable called j equal to 0, j is less than columns, semicolon, j plus plus. Here, we can perform any kind of action. In this case, we will carry out the printing of which pin of our LED matrix we are currently on through serial.printi, and we will print matrix at index I and index j to ensure everything is working correctly. We start the simulation. Here, we have a problem. We forgot to define a semicolon after creating this matrix. We place the semicolon, start the simulation, and now we have on our serial monitor each of the pins according to our matrix. Notice that we are displaying the numbers 13, 10, and 7, which are part of our first row. Then we write 12, 9, and 6, which belong to the second row. And finally, 11, 8, and 5, which are part of the third row. This means that so far everything is working correctly. Let's proceed to perform some tests. Now that we have seen that everything works correctly, let's go to our function called loop. What we want in this loop function, first of all, is to turn on each of the LEDs that are part of the LED matrix. So within this loop method, we're going to recreate this pair of 4. The idea is for this to serve you, so you can practice creating these loops and memorize them to avoid problems in the future. So let's rewrite for int I equals 0, I is less than rows, semicolon, I plus plus. Remember that inside, we will write another for loop. Int j equals 0, semicolon j is less than columns, semicolon j plus plus. Inside this second for loop, we can now perform some action with our LEDs. For example, we'll turn on the LED we're at through digital write, and in parentheses, matrix of I and j. We are going to assign it a value of high. We will wait 250 milliseconds, and after this wait, we will turn off our LEDs through digital write of matrix I and j with a value of low. With this, we will turn on each of the LEDs, and after waiting this time, we will turn each of them off. Before initializing this simulation, we need to return to our setup method, as we need to specify the pin mode for each of these elements in our matrix. Now, after performing this serial.println, we will specify pin mode of matrix I and j, and we will indicate that we want these pins to have an output value. If we start the simulation, we can see that nothing happens with our LEDs. This is occurring because we need to connect the negative rail on our protoboard to the pin marked GND on our Arduino. Let's place a wire between this GN pin and our protoboard. Now, we'll start the simulation again. And notice that we are now correctly lighting up each of the LEDs in our LED matrix. Here, as you can see, we have this warning because we need to place a resistor. Let's quickly fix this issue by changing the pin for each of the LED wires and dragging a 220 ohm resistor so that we no longer have this problem. We'll copy this resistor, paste it again, and then correct the error on each of these outputs to our digital pins. Okay, let's start the simulation again, and we see that this problem is resolved. We are now satisfactorily lighting each of the LEDs in our matrix. Next, we will practice by creating some patterns with our LEDs. We previously saw that we can turn on each of the LEDs, but what would happen if we wanted to light up all the elements in each of the rows or columns from the code? We will carry out this task, and for that, we will first light up each of the columns in a sequence. Let's go back to the code. We will proceed to comment out these lines of the for loop that we have as part of our code. This is to make it easier to test our patterns. We will then write another for loop. For int I equals 0, I is less than rows, semicolon, I++. This is the classic loop we've done multiple times. For int j equals 0, j is less than columns, semicolon, j++. What we will do to achieve this purpose is that once we are evaluating each of the columns in our LED matrix, we will turn on the LED using digital write, matrix, and j, comma, I. However, this time, instead of waiting the 250 milliseconds we waited before, we will light up all the LEDs without leaving any delay. We will then apply this, and once all the LEDs in the column are turned on, that is, this LED first, this one, and this one, which corresponds to the first row, we will proceed to write a delay of 250 milliseconds. Notice that unlike the previous for loop, we are placing the delay once the first 3 LEDs are finished being lit. Once this time passes, we will execute a second for loop, with the purpose of turning off all the LEDs in the row. We can then copy this for loop, paste it, and this time, instead of performing a digital write of high, we will perform a digital write of low. With this change, if we start our simulation, notice that we are now successfully turning on each row of our LED matrix. Let's stop the simulation and suppose we want to light these LEDs in the opposite direction, that is, from bottom to top. To accomplish this task, I will copy this entire for loop, paste it once more, and this time we will set I equal to the number of rows. But this has to be equal to rows minus 1, as we remember that we start from index 0. The second condition will be that while I is greater than or equal to 0, since that is the index we will reach, then we'll decrease I by 1. Within these for loops we have here, which define the variable j, j will be equal to the number of columns negatable j. J must be greater than or equal to 0, and we will decrease this variable j by 1. We copy this line, and it's exactly what we need to do in this second for loop. Okay, let's see how this looks. Let's hide the code section, start the simulation, and notice that we are now effectively moving back and forth. Let's stop the simulation and proceed to uncomment this line we previously had where we declared our first section with the for loop. Let's hide the code and see all the patterns we have created together. We start the simulation. Notice that we already have a nice display of our LEDs. So far, we have created patterns that are heavily based on the idea that we can traverse each of the rows and columns of our circuit, or our LED matrix as we see here. But what if at some point we wanted to create slightly more complex patterns? For example, to indicate that this LED is on while this LED and this LED are off. Well, we can also achieve this thanks to two-dimensional arrays, but we are going to use them in a completely different way. This time, we will use two-dimensional arrays to define the different patterns that we will reproduce as part of our LED series. To carry out this task, we will go back to the top and proceed to create another two-dimensional array. So we will declare an array called pattern1, for example. In this case, since we want to have a larger set of row patterns, we will proceed to define another constant, which we can call, for example, row patterns. This will be equal to, for example, 6, as we will define 6 different patterns that will be part of our sequence. As part of pattern 1, or the variable pattern 1, we will indicate or we will define that we need as the number of rows the variable or constant called row patterns, which is equal to 6. As the second element, we will reuse this constant called columns. This will be equal to -. Here we'll proceed to define our different patterns that we will use as part of our sequence. Each of these rows that we define through this set of braces will define a sequence of LEDs. Within these braces, we will define which LEDs we want to turn on in each of the patterns that we will have as part of this matrix. For example, let's assume that first we want to turn on LEDs 13, 12, and 11, which are these 3 LEDs we have here, representing our first column. So we will indicate that we want to turn on LED 13, LED 12, and LED 11. We wait for a moment, and after that time, we will indicate that we want to turn on another sequence of LEDs. This could be, for instance, the LED connected to pin number 10, pin number 9, and pin number 8, meaning our second column of LEDs. Next, we will turn on the third column by declaring 7, 6, and 5. We write the comma, not only that, but we can also turn on other LEDs that are not part of any row or column. For example, we can indicate that we want to turn on LED 13, LED 10, and LED 7. The first LED we see here would also be the LED connected to pin number 10, meaning this LED we see here, this one we have here, and also the LED, the third LED, that is part of our first row. We could indicate a stranger sequence. For example, we could indicate that we want to turn on pin number 6, pin number 10, and pin number 8. We can create another sequence. Let's indicate that we want to turn on LED number 5, LED number 12, and LED number 9, for example. So far, we have 1, 2, 3, 4, 5, and 6 different sequences. Thus, these will be the sequences in our pattern that we are going to execute. As part of this code, we will proceed to our loop method and comment out what we had previously created. We'll also proceed to copy our penultimate for loop that we had created before. Let's copy it. Let's go to the bottom and paste this for loop. What we need to do is this check we had previously, which is that while I is less than rows, since the constant we are using is called Patronus Philos, we make the change. Once we have changed this constant, we also need to change this digital, right? Since we will not be accessing the array, instead we want to access this array called Patron1, which contains our different sequences. Let's paste this value into our digital, right? And once we've made these changes, let's proceed to test our circuit. We start the simulation and look. We have our patterns displayed through the LED array in a satisfactory manner. just as we defined them in this array called patron1. Now, we will use our LED matrix to display uppercase letters on this LED matrix that we see here. We can use these 6 LEDs to try to represent some letters that will be displayed simultaneously. Suppose we want to display the word hello. We would use these 3 LEDs to mark one of the lines, marking this middle line for the center of the H, and using this last column to complete our display of the letter H. If we wanted to display the letter O, for example, we would use the entire outline of our LEDs, leaving only this LED off, and so on. Let's carry out this task. Returning to our code, we will go to the top, and after defining this matrix called pattern1, we will proceed to define which LEDs are part of each letter. Let's define a new matrix called word H that consists of rows and columns. This will be equal to, and here we will specify which LEDs we want to turn on for each of the letters. In the first case, we'll use the LEDs located at pin number 13, pin number 12, pin number 11. And to indicate that these LEDs will be off, we will place a number 0. We will also use pin number 9, pin 7, pin 6, and pin 5. We will represent these LEDs through our array. We write an opening brace and a closing brace. Here, we include the pins that we are interested in, which are pin 13, pin 12, and pin 11. As a second definition, since we want to leave this first LED off, we will place a number 0. Next, we specify that we are interested in pin number 9. We leave a third number, 0, to indicate that this LED will be off. We create the third array, which is part of this 2-dimensional array, and we specify that we need pin 7, pin 6, and pin 5. With this, we have defined a word with its respective LEDs that will light up. We will proceed to copy this definition of this array to indicate that we want to create a second constant called palabra O. In this case, we want to light up pin 13, pin 12, pin 11, and we are interested in pin 10. However, since we do not want the middle LED, we will indicate that we want to place a 0. We are also interested in pin 8 and in pins 7, 6, and 5. We copy this constant, paste it, and indicate that we want to build the word L. For this, we are interested in pins 13, 12, 11, and pin 10. And pin 9 are not of interest, so we place a 0 and another 0. Pin number 8 is of interest since we want to mark the letter L. We are not interested in pin 7 or 6, but we are interested in pin 5. Finally, we will copy this constant one last time, and we will indicate that we want to build the word A. We specify that we do not want this first LED, so we place a 0. We are interested in pin 12, pin 11, and pin 10 as well. Therefore, we include it as part of our second array. We are also interested in pin number 9. We are not interested in pin number 8, so we place a 0. Pin 7 is also not of interest, so we leave this 0. Pin 6 and 5 are of interest, so we place a 6 and a 5. Let's return to our loop method. We're going to comment out the for loop that we had previously created. We'll go to the top where we had a for loop, which is structured as we see here. Let's go ahead and paste it once more with the purpose of reusing this for loop. What we will do with this for loop, we have pasted is remove this delay in the inner for loop in such a way that only this for loop and the other inner for loop remain. We will change the name of this array to palabra H, which is one of the constants we've defined for the LEDs that will light up when we invoke this array with its respective indices. Before executing the simulation, let's return to the top, as we need to add semicolons to each of these constants. Therefore, I will proceed to place a semicolon in each of these places. Once we have this ready, we will start the simulation and see that the corresponding LEDs for the letter H are now lit. Let's stop the simulation and remember that the goal is to display the word Ola on the LED matrix. Hence, we need to review our loop. What we should do for this task is add a delay of, for example, 500 milliseconds after executing the for loops again, but now invoking the palabra array. Since we already know how to create methods, Let's reuse this knowledge to avoid rewriting this code repeatedly. Therefore, I will proceed to go to the bottom and declare a method named scribbler that takes a two-dimensional array of integers as a parameter. I'll call this parameter a reglo, and I will define it to have 3 rows and 3 columns. If you're wondering why I don't pass the names of the constants, it's because Tinkercad does not allow me to do that once I have defined it. So after defining the name of my method, I will return to the top, cut all the code I wrote earlier, and paste it as part of the scribbler method. I will also proceed to change the invocation of the word h to array. The last thing we'll do as part of this write method is to turn off all the LEDs that are part of this array. Therefore, I'm going to copy this for loop again. And after this delay, I will proceed to invoke the array at index 1, index j, but now invoking the low value. Let's return to our loop method, and we will test this method we have created. So we invoke write, passing, for example, the word h. Let's start the simulation, and notice that we turn on the letter h. It may seem like it is not turning off, but it is actually turning off. Just remember that this write method is being executed multiple times, meaning indefinitely. Let's stop the simulation. Since we saw that our method works satisfactorily, I'm going to copy this line 3 times, and this time I will pass first the word O as an array, then the word L, and the word A. With the purpose of writing each of the letters in our array, let's see if this works correctly. We start the simulation, and notice that our code is functioning satisfactorily. I will add a bit more delay, for example, a second of delay, and start the simulation again. We are now displaying each of the letters that are part of our array satisfactorily. We have been consistently using certain data types in our sketches. Now let's talk about a data type that we haven't discussed much, but is very useful. This is the byte data type. For those who don't know, the lowest level language in any processor is binary language, which consists only of ones and zeros. Previously, we saw how to create a binary clock. This definition of a 0 or a 1 is called a bit. In the world of zeros and ones, a set of 8 bits represents 1 byte. Here we see a visual representation of this. We see that we have 8 bits represented by ones and zeros. In case we want to obtain the decimal representation of a binary number, we need to follow these steps. Specify base 2 with an exponent starting at 0, which will increase by 1 as we move to the next element on the left. This way, we will obtain a result by carrying out the operations at their corresponding positions. For example, 10 is the result of performing these operations in this example, as we will only carry out the operations where we find a 1. Here we have another example which results in 170. The largest number we can obtain with a set of 8 bits with a value of 1 is 255. Why am I telling you this? Well, because there is a table called the ASCII table, where we can see the representation of characters and numbers precisely in the result of these conversions. For example, we can see that the capital letter G is represented by the number 71, which in binary would be this representation. Well, we have previously been declaring variables with the integer data type, and as you will remember, the number of pins on the Arduino Uno is definitely less than 255. This means that since a byte data type can store up to the number 255, we could change the int data type to the byte data type without any issues. This would save us some memory space, allowing us to optimize code when we have more complex projects. I share this information with you because most of the examples of the component we will see in this section, which is the keyboard or keypad, come with byte definitions, which may confuse those who do not have this knowledge that I previously shared. Let's take a look at a demonstration of this by switching to Tinkercad to see it in a practical way. Okay, we are back in Tinkercad. We are going to do a couple of demonstrations so that you can understand the byte data type well. Let's start by dragging the Arduino Uno component to our interface. Let's go to the code section. We will indicate that we want to use text. Let's remove all the default code that gets created. We are ready to begin. The first example we will do is create an array of integers. We will name this array array, and we will indicate that it should be initialized with a set of 20,000 elements. We place a semicolon. In the setup section, we will perform a serial dot begin with 9600. And also at the bottom, we'll try to print the size of our array. If you remember, size_stop gives us the number of bytes being used in a variable, so theoretically this should give us the number of bytes being used in our array called array, which is of the integer type. Let's start the simulation to see what happens. And notice that we have an error here saying that the size of the array called array is too large. Basically, this error indicates that we are exceeding the memory capacity of our Arduino Uno. Notice what will happen if I change this integer data type to the byte data type. Let's start the simulation, and this time we have no issues. Let's check the serial monitor, and notice that we have a result of 20,000 here. As you can remember, this function returns the number of bytes a variable occupies. And since our array is of the byte data type, it yields a result of 20,000. As we can see, the byte data type is smaller than the integer data type, so we can significantly optimize our code. Let's stop the simulation, revert to the integer data type, and specify that we want a slightly smaller array, for example, with 2,000 elements. I'll clear the serial monitor, start the simulation, and notice that this time, if we specify an integer data type, we have a size of 4,000 bytes. If we stop the simulation and change the data type back to byte, then start the simulation, you'll see that the result is exactly halved. With this, we could perform optimizations in our code in case we encounter memory issues with our Arduino. I will now proceed to stop the simulation. Another interesting thing we can do with a byte data type is declare a byte data type variable. For example, we'll call it belt up. We can represent a byte through its bit representation. As you may recall from this slide example, we saw that the uppercase H was represented by the number 71, which is the result of this set of bits we see here. I'm going to note in the sketch, as a comment, the binary representation of this letter. This is the binary representation. So what we could do as part of our byte element is to declare the number 71 directly. But we can also carry out the representation of this byte in a binary format. This is done by specifying an uppercase B indicating what the different bits of the byte are. So we write 01000. Remember that it's important to include an uppercase B, otherwise it'll give you a compilation error. To see this graphically, I will comment out this serial.println, and we will include another serial.println to print the value of variable B. Let's see what it prints for us. Let's clear the serial monitor. Let's start the simulation once again. Notice that we are printing the value 71 on the serial monitor. We are not printing the set of bits that we have here. What this means is that we have an equivalence between this value we see here and the value being displayed on the serial monitor. If we want to see the representation of the character of this set of bits, we can do so with a new function called serial, right? So after placing the serial.println, we will add serial. And we have this method called write. We will pass this variable b to it. I will also comment out this array definition at the top. Let's start the simulation. Notice that we are successfully displaying the value 71. And along with it, we are displaying the value G uppercase. This means that this uppercase G is equivalent to this decimal number and to this binary representation we see here. To show you that they are equivalent, I will proceed to change this binary representation that we see here and replace it with the number 71. I clear the serial monitor, start the simulation, and notice that the value 71 and the uppercase G value are displayed again. This is very useful to know, as in some examples, you'll see these different ways of representing a byte. So if you see any of these examples with this nomenclature, you will understand why this is happening. To continue with our section, let's talk about a new component, the keyboard or keypad. There are different models of this component, although the simplest ones are like the one we can see in this image. Typically, we can find those with 4 rows and 4 columns, but there are also ones with 3 columns and 4 rows. Each of the rows and columns is enabled by an output pin. The first output pins represent the rows and the last ones represent the columns. These connections are interconnected. If we didn't have these interconnections, we would need to use one pin for each button we required, which would increase our pin count. For example, if we wanted to connect 9 buttons, we would need to use 9 pins on the Arduino. However, by having them in a matrix and interconnected in rows and columns, we can save 2 pins, as we would only need 6 pins, 3 for the rows and 3 for the columns. How do we detect when a key has been pressed? Well, let's imagine we have a keypad with 4 rows and 3 columns, totaling 12 keys. We need to apply a technique called keypad scanning, or scanning keypad. It is called scanning because we will check each key to see if any are pressed. Notice how the pins for the rows are connected as output pins, while the pins for the columns are connected as input with pull-up resistors, which gives them a high output value if the key is not pressed. Let's start the scanning process. First, we will iterate through the first row. This row will change its value to low. Then we will proceed to read the status of each column. If the status is high, the key is not pressed, which is the case we see here. We will do the same for each of the columns. No key presses were detected from the first row. Let's move on to the second. The status of the first row changes to high, while the status of the second row changes to low. Again, we check each of the columns. Let's proceed to the third row. Now, let's examine the last row. Look at what has happened at this point. Someone has pressed the key with the number 8. As we were checking row 3, we performed the necessary checks for each column. No key presses have been detected yet. Let's continue going through the rows. Pay attention here as we reach the row where the key is pressed. As you can see, with the key pressed, the circuit closes. Let's start by validating the row with the first column. When we reach the second column, we detect a low value, meaning the key is pressed. After this step, we will continue to check the columns as before. Once the key is released, the execution of the algorithm will continue as we have seen so far. This is how we detect when a key is pressed. Fortunately for us, there is a library that will help us avoid manually monitoring this algorithm. Let's see what it entails in Tinkercad. We are back in Tinkercad. Let's proceed to search for a component called keypad. Now, let's browse through our list of items, and as you can see, we do not have it in this section of basic components. Let's list all the components, and then we will proceed to look for our keyboard. Here it is. We can see that it is a keyboard with 4 rows and 4 columns. We will drag it to our designer, and notice that this keyboard has 8 pins. The first 4 pins represent each of the rows, and the next 4 represent each of the columns. We will learn to integrate it with Arduino. Let's proceed to drag in Arduino Uno. We will list the basic components, and here it is. We will drag our Arduino. To make our keyboard work with our Arduino board, we need to connect each of these rows and each of these columns to a different pin on our Arduino. Let's then proceed to connect the first pin to our first Arduino pin, which in this case will be pin number 12. I won't connect it to 13 as this causes some issues in Tinkercad. Let's connect the pin to number 12. We'll connect the second row to pin number 11, the third row to pin number 10, and the fourth row to pin number 9. Column 1 will connect to pin number 8 of the Arduino, column 2 to pin number 7, column 3 to pin number 6, and column 4 to pin number 6, and column 4 to pin number 5 of our Arduino. It's that simple to connect a keyboard to our Arduino board. Now let's go to the code section. We will indicate that we want to use the text, remove this predefined text, and make use of a library. A library is essentially a collection of code files that allows us to utilize that library to perform certain actions without having to code them ourselves. Therefore, there is no need to reinvent the wheel if something already exists. This library is the most commonly used for working with this component, the keypad. In Tinkercad, we can find it by clicking on this icon here that looks like a filing cabinet, and we have different libraries that we can integrate into our project. The library we are interested in is called Keypad, which allows us to read button presses on the keyboard. So let's click where it says Include, and this line we see here has been added, allowing us to use this library. In the case of the Arduino IDE, to install this library, we need to do it as follows. We go to the Tools section, click on the Manage Libraries option, and we will search for this library called Kpad. Okay, the results are filtered, and we will search for the library called Kpad. Here it is. It was created by Mark Stanley and Alexander Brabink. We need to click on the button that says Install. I don't see this button because I already have this library installed, but once you install it, this line will appear for you. Once we have integrated this library into our sketch, we will define how many rows and columns our keypad has. Let's declare a couple of constants of type byte. The first will be called rows, and this value will be set to 4. Next, we will declare another constant to represent the columns, which will equal 4, since our keypad has 4 columns and 4 rows, as we see here. The next step we need to take is to create a two-dimensional array to represent the mapping of the keys that are part of our keypad. We will visualize it. We'll proceed to create a two-dimensional array of type char, since the elements stored in this array will be characters. Let's name it, for example, keymap. We specify that it should have a set of elements representing the rows defined by the constant named rows and a set of columns defined by the constant columns. With this, we are representing a two-dimensional array. We will indicate that we want to create the elements at the time of creating our array. Remember that each element we place in this way will represent a row in our array. Here, basically, we will place each of the characters that are part of our matrix. That is, we will define the first row with character 1, character 2, character 3, a comma, and uppercase character A. We will copy this row and indicate that our second row is represented by the values 4, 5, 6, and uppercase value B. We copy this line again and specify that the third row is represented by the values 7, 8, 9, and uppercase C. Another row is represented by the values asterisk, a 0, a hashtag, and finally, an uppercase letter. This is very important, as it will allow us to obtain these characters according to the position we are pressing. This may be the case if you have a keyboard that does not exactly have these characters that we see here. For example, it might have the hashtag symbol inverted in this position and the asterisk symbol in this position. In this case, you would need to change your key map to define where each character is located on your keyboard. The next step is to define an array, indicating where each of the rows and columns is connected on our Arduino board. We will proceed to create a couple of one-dimensional arrays of type byte, and we will indicate that our first array is named pin rows, with a number of elements defined by the constant rows. We will set this equal to, and we will specify which pins represent the different rows of our keyboard. In this case, these are pins 12, 11, 10, and 9. So we will place these values, 12, 11, 10, and 9. Next, we will create a second array to represent the column pins, and its size will be specified by the constant columns. This will be equal to, and we will specify which pins correspond to the columns. In this case, these are pins 8, 7, 6, and 5. Once we have created all these constants, variables, and arrays, the next step is to create an instance of a special class. This concept of instances relates to the topic of classes we discussed in a previous section. Essentially, it is a special data type that we will encounter, which is part of the library we have installed. It's similar to declaring an integer data type. For example, in the case of an integer variable, we declare it as int, such as let pin equal 13. I will comment on this line. Well, a class is declared in the same way. We need to specify the data type, which is a special data type called keyAdd. We must write the name of the variable. Let's call it, for example, myKeyPath. This will be equal to, as we see above, we need to specify something. We cannot specify an integer since keyPath is not an integer data type. The data type we can assign is a keypad data type. To initialize this data type with certain values, we place parentheses and a semicolon, and essentially we must pass a set of values to carry out the initialization of this class and to use it easily. The values are, first of all, the keypad that we have declared above. To correctly pass this first parameter, we need to use a subfunction of this class called makeKeyMap. In parentheses, we need to pass the keymap, which is called keymap. Okay, after this closing parenthesis, we will place a comma, because next we need to specify the pins for the rows. We already have this variable created here, so let's pass pin rows. We also need to pass the pins for the columns, so we pass col rows. Lastly, we must pass a couple more variables, the number of rows and the number of columns that make up our keypad. We also have these variables declared in the constants, rows, and columns. With this, we have completed the initialization of our keypad class, and we will now be able to use the myKeyPad variable in our sketch. Let's start the simulation to ensure everything works and compiles correctly. Here I have an error. I passed an incorrect name. The name is pin columnus, not colfilas. We restart the simulation, and now our sketch compiles successfully. Next, we will initialize serial in the setup method using the begin method with 9600. We go to our loop section. Here we want to recognize or print which key we pressed. To carry out this action, we will declare a char data type which stores only one character. We will call it pressed key, and it will be equal to, and we will reuse the class defined above. We will then indicate myKeyPad. And as part of this class, we have a set of methods that will allow us to work with the different values from our keypad. It's similar to the serial.begin method. In this case, these methods will help us perform operations with the keyboard, one of which is called getKey. This method will allow us to get one of the keys when we press it. After acquiring the key, we can check if pressed key is not equal to. And since we are using the keypad.h library, we have a special definition called noKey. This special keyword allows us to know whether we have pressed a key on our keyboard. Therefore, we can ask if pressed key is not equal to noKey. If a key is pressed, certain code will execute here, and if not, we will skip this if statement. Since we want to print a character when a key press is detected, we will code within this if statement to use serial.println, passing the pressed key as a parameter. As you may recall, this is of the character type, which is why we can display it on our serial monitor. Okay, it's time to test the sketch. Let's start the simulation. We will open the serial monitor, show our keyboard, and press a key. For example, the number 8 key. Notice that it is successfully displayed on our serial monitor. Let's press a few more keys, and notice that each time we press a key, it is shown on our serial monitor. This undoubtedly opens up a wide range of possibilities for creating numerous projects based on Arduino. Let's see how to integrate our keypad into a real project. What we will proceed to do is add a series of LEDs, 4 relays and 1 green. The idea is to have an initial password or PIN, allowing us to enter 4 characters on the numeric keypad. If the 4 characters are valid, the green LED will light up. Otherwise, it will not. The idea is also that while we press the keys on our keypad, the red LEDs will light up to provide feedback on how many keys we have pressed. Let's see how this algorithm will function to validate whether the PIN is valid or not. First, we need to define an array that will contain the characters for our PIN that we will validate. For example, 5, 8, 1, and 4. You'll also need to declare a second character array, where we will store the keys we press. which will later compare to see if it matches the initial pin. Suppose we press the key 5 on the keypad. This value will be stored at index 0 of our second array. We press another key, and this value will be stored at index 1 of the second array. Then we will press a third key and a fourth key. With this, our array will be filled from indices 0 to 3. By adding 1 to the index, we can check if we have filled the array. In this case, the condition is true, so we will proceed validate both arrays. In this specific example, since the values of the two arrays are not equal, the access LED will not light up. We must have exactly the same values in both arrays for the validation LED to light up. Let's go to Tinkercad to implement this logic. We are back in Tinkercad. Let's proceed to hide the code, and we will also add a small test board. Let's add 4 LEDs that will represent the keys pressed by the user. We will add a 5th LED on the right side. This LED will indicate that the pin we entered is valid. Now, let's place these LEDs in red, with the last LED being green. Let's connect the cathodes of our LEDs to the negative rail of our proto board. Let's color these wires black. We will also connect the cathode of this last LED to our negative rail. Once this is done, we will proceed to connect our LEDs to the pins of our Arduino. To maintain separation, we will connect these LEDs from pin A0 to pin A5 on our Arduino board. Let's now connect this first LED to pin A0. We will connect the second LED. To pin A1, the third LED will be connected to pin A2, the fourth LED will be connected to pin A3, and finally, we will connect this green LED to pin A4. Let's color this wire a different color, for example, yellow, so that we can differentiate them. We will also color these wires purple, for example. Finally, let's add a resistor to our LEDs to prevent any issues. We will rewire these connections. Let's use a value of 220 ohms. We copy and paste this resistor for each of the LEDs. We do the same for this green LED. All right, we have our connections ready. Lastly, we will connect the negative rail of our breadboard to our Arduino. So let's connect the negative wire to one of the GND pins on the Arduino. We color the black wire, and now we have all the connections ready. Good. Let's move on to the code. The first thing we will do is declare a new constant, which will allow us to represent the pins for our red LEDs that we see here. We will declare a byte-type constant named LEDPins. We will specify that we want to use 4 elements, which will correspond to the pins for our red LEDs. As you can see, we are using pins A0, A1, A2, and A3, which are actually pins 14, 15, 16, and 17. As you may remember, the pins we have here at the top end at pin number 13. Therefore, the first analog pin, if we want to use it as a digital pin, will start with the number 14. Next, we will declare another constant of type byte, which will represent the pin for our green LED. In this case, this LED is connected to pin A4, which is actually pin number 18. Let's call it valid LED and assign it a value of 18. After declaring the pins to which our LEDs are connected, the next step will be to define our pair of arrays. One will store a key or an initial pin that is the valid pin, and the other array will store the characters we input as part of our keyboard, which we will validate at the end to see if they match or not. We will proceed to declare a character array with a size of 4 elements. We will also declare a second array called password, which can be any name you prefer, indicating that it will also contain 4 elements, and we will initialize this array with the valid pin. We will set the password to be 2, 5, 4, and 3. The user will need to enter exactly these characters to turn on the green LED. Once we have done this, we'll go to our setup method and initialize the pin mode for these LEDs. We will then indicate for int I equals 0 is less than 4, an increment. We invoke pin mode and indicate that we want to assign the LED pins at the index with the value output. Lastly, we will also set a pin mode for the green LED, which we recall is named LED. We then assign the value output. Let's check that everything is functioning correctly. Once we have done this, the first thing we will do is store a different value in our array called attempt. This is to store the different values we are entering from our keyboard. To carry out this action, I will proceed to declare a variable called index that is equal to 0. The purpose of this variable is to know exactly what position in the array we are in. So let's go to our loop method. And once we have detected that a key has been pressed, remember this is with the if statement, we will remove the serial.println and instead indicate that we want to store in a tip index the pressed key. Since this variable's initial value is 0, we will store the key we pressed in the first element of our array. We will perform a serial.println so that we can see what the value of attempt is at index. Once we have entered the first value in our array, we will also turn on our first LED, which is this one here. Since this LED is in position 0 of our set of LED pins, we can indicate that at position 0, which is the pin connected to pin number 14, it can be turned on. To do this, we will indicate digital right on the LED pins at the index value, which should have a height value to turn on this LED only. Once we turn on this LED, the next step is to increase the value of our index variable by 1, so that the next time we read a character, we store it in our attempt array, but now at index number 1. Let's see if this works correctly. We will clear everything from the serial monitor, and we will start the simulation. We have a problem here. I mistakenly put key preset, but the correct value is key pressed. We will start the simulation. Okay, everything seems correct. Let's proceed to check our circuit. Let's press a key, for example, the number 9. Notice that two things have happened. We printed the value 9 successfully, which means it is being stored correctly in attempt at index number 0. And this LED has also turned on, indicating that we now have a character stored in our array. Let's press another key, for example, the number 1. And notice that we printed the value 1 and turned on our second LED. Now, let's press the number 7 key, for instance. The same thing happened. We received another value, the number 0. And now we have all 4 LEDs on and have successfully printed each character we pressed. However, if we continue pressing different characters, we are starting to encounter some issues, as we have exceeded the number of elements that are part of our array. Let's correct this. I stopped the simulation, and what we need to do is, once we have read the last key that is part of our array, to check if the index is equal to 4. With this, we can easily check if we have finished storing each of the elements in the attempt array. So if the index is equal to 4, we can perform the check to see if these two arrays match or not, or if they are equal or not. We will proceed to declare a variable called isValid, which will be equal to a method that we will invoke named validate. We have not yet created this method. Let's proceed to create it. We will position ourselves outside of our loop at the bottom of our sketch, and we will proceed to declare this method. Since we want this method to tell us if the set of characters is equal or not, we will indicate that this method will return a Boolean value, specifying whether the check is valid or not. We will call this method validate, place the respective parentheses and curly braces, and here we will specify for int I equals 0. I is less than 4, I++. We have seen this before. And basically, we will iterate over each of the arrays and ask if password, which is our first array seen here at this position, is not equal to attempt at its position I. In other words, if any of the characters is not valid in the same position, then we will return false. This line of code will allow us to terminate the execution of this for loop, exit the validate method, and return a false value, which will indicate that this comparison we have made is not correct. We can execute a couple of additional lines, for example, serial.print, to visually see that the value is incorrect. In case each of the checks is correct, and we exit the execution of this for loop, we will return the value true, which indicates that the comparison was successful. With this simple algorithm we have created, we will see if our arrays are equal or not. Now, we will return to our loop method, and after determining whether the arrays are equal, we can check if it's valid. That is, if the check was successful, we will print serial.println. It's correct. Here we will invoke a method called creating a method, since you might have a set of different components that you may want to modify to carry out a series of actions once a pin is entered correctly. I will then proceed to create a second method. This method will be called access, and it will not return anything, hence the void modifier. Once we access, in our case, we want to turn on the green LED, so I will proceed to indicate digital write valid_LED with a high value. What I want to do is wait for 5 seconds through a delay. This is to ensure that after these 5 seconds, we can turn off this LED. However, we don't want to perform just this task. After the LED is on for 5 seconds, we also want to reset our entire sketch, which means turning off these LEDs and resetting a variable called index. To make this simpler, we will proceed to create a method called reset. The purpose of this method is to allow us to reinitialize each of the variables. And if we want to reinitialize any component, we can do that as well. To carry out the reset of our components, we'll turn off each of the red LEDs. We'll create a for loop for int I equals 0, I is less than 4, I++. And we will perform a digital write on pins with the index I with the value of low. This will ensure that we turn off each of the red pins, and we will also reinitialize this variable called index with a value of 0. We'll invoke this reset method from our access method. That is, once the LED has been turned on for 5 seconds and then turned off, we will reset our entire circuit. However, we will not only use it here, but also in our main method. If we detect that we have entered an invalid pin through this if comparison, we will also carry out the reset of the LEDs, since we do not want these LEDs to remain on. We will then declare an else that is part of this first if. This will be executed only if our pin input is incorrect. We will perform an action such as a serial.println for being incorrect. We will invoke the reset method here to reset our components. With what we have done, we will start the simulation to ensure everything is correct. Here we have a problem in this section of the code. Okay, it's that our array is not named pins, but rather let pins. We restart the simulation, we now have a successful build, but let's see how our circuit behaves. I will hide this section of code and enter an invalid pin, for example, 9999. Notice that once the LEDs light up, they turn off again, as we can re-enter a pin. Let's enter the valid pin, which is 2, 5, 4, and 3. Notice that our green LED lights up satisfactorily. After 5 seconds, everything resets. We can re-enter our valid pin, and now our circuit is working satisfactorily. Let's see how to assemble it physically, and we will also test our circuit in a real situation. Let's assemble the project. I will start by connecting a series of jumpers to the output pins of the keyboard. These connections appear as shown in the image. On the other side, we have the different jumpers arranged so that we can integrate them quickly and easily into the Arduino board. We will connect from pin number 5 to pin number 12. We will add a set of LEDs that will represent the number of buttons pressed by the user. We will also add a green LED that will indicate whether the entered pin is correct or not. Once this is done, we will connect the cathodes of the LEDs to the negative rail of the protoboard. Next, we will connect a 220 ohm resistor to the outputs of each of the LED's anodes. Let's do this with the second LED, the third LED, and the fourth LED. Also for the green LED. Subsequently, we will connect the first LED to the pin marked A0 on our Arduino. The second LED will be connected to the pin marked A1 on the Arduino. The third LED will be connected to pin A2, and the last LED will be connected to pin A3 on the Arduino board. Finally, we will connect the green LED to pin A4 of the Arduino. Lastly, we will connect the negative rail of the proto board to one of the pins marked as G and D on the Arduino. Once assembled and the sketch uploaded to the board, we have the project functioning. We see that the LEDs light up as we enter the digits of a pin. While the password is invalid, the green LED does not light up. Let's enter a valid password. Great. The green LED has turned on because this is the correct password. Let's see it once more. We are going to create our second project for beginners, which is a motion detector. Yes, just like the ones you've seen in the movies. This video shows the final result of the project. Notice that the interesting part is that when the sensor detects motion, an alarm sound and an LED are activated to alert of a possible intrusion. Doesn't it seem like a project to stop the infamous James Bond? To carry out this project, these are the components needed. A proto board, an LED of your favorite color, a 330 ohm resistor, a buzzer, a PIR motion sensor, HCSR 501, 3 female-to-male jumpers, 3 male-to-male jumpers, and of course the Arduino Uno. With these components, let's take a look at the connection diagram of the project. Here we have the circuit diagram that we'll be working with, and basically, we see that there are 4 fundamental sections that will serve for our project. The first part relates to our motion sensor, which is the PIR sensor. Here it is represented in this way in our diagram. We will see in a later video how to carry out the identification and placement of the different jumpers to our PIR sensor. Now, if you are interested in learning a bit more about this sensor, I will leave a PDF document in the resources section of this lesson, which contains all the information about the sensor. Here you will discover what the PIR sensor is used for, how it works, and the purpose of this Fresnel lens that we see here. We see a set of data that will help us understand more about the operation of this sensor. We also see a description of the different components of this sensor, including information about the purpose of the orange potentiometers we have. So I repeat, I will leave this in the resources section if you want to delve deeper into the topic of this PIR sensor. The second section of interest is this LED located here, which is directly connected to pin number 3 of our Arduino. Basically, this LED will react when motion is detected by the PIR sensor we have here. Likewise, when this LED lights up, this buzzer or speaker placed here will also sound, which is connected directly to pin number 4 of our Arduino. So basically, this is how it works. The sensor detects motion, and both the LED and the speaker turn on. Let's start a quick simulation to see how this works. Okay, we activate the sensor and position ourselves where movement is detected. Okay, notice how the LED turns on immediately and the alarm starts emitting a sound. So, if I am within this zone, the alarm is triggered. But if I leave the detection zone, we see that both the LED and the speaker turn off. Basically, this is the operating and connection diagram that I will provide as part of the resources to help you learn how to set up this project, which can also be useful for more complex projects and integrate it with larger projects. Now, let's proceed to see how to interpret this diagram to carry out the physical connections of our components. Once we have reviewed the project diagram, we will learn how to connect the components. Here we have the connection diagram. Let's break it down component by component so you can assemble your circuit without issues. The first thing we need to do is identify the ground pin of our PIR sensor. In my case, it is the pin that appears on the far right, as it is marked with the letters G and D, which means ground. In my case, I had to remove the dome to visualize the data on the board. We need to connect the first male to female pin, which in my case is black. Next, we need to identify the second pin, which is the power pin. In my component, it is marked as VCC. I have connected the white wire to this pin. Finally, we need to identify the signal pin, which in my component is marked as out, meaning output. I have connected a green male to female wire to this pin. Once we have identified the three signals, we are ready to integrate our module into our proto board. In the diagram, we can see that the positive and negative signals are connected to the proto board at their respective poles. Therefore, we do the same physically as shown in the image on the right. We connect the black wire to the negative pole of the proto board and the white wire to the positive pole of the proto board. We will connect the signal wire to pin number 2 of the Arduino to read the sensor data. This is how it should look physically after connecting the signal jumper to the Arduino. Next, we will integrate an LED that will light up when motion is detected. The most important thing is to note which side is the anode and which side is the cathode of the LED. In the diagram and in reality, the shorter leg is the cathode and the longer leg is the anode. So what we'll do is identify the length of the legs, and based on this, we will connect our LED on the proto board, placing the longer leg on the right side and the shorter leg on the left side. Once our LED is positioned, it should look like this. In the diagram, we connect the cathode of the LED through a resistor to the negative rail of the proto board. In our assembly, we will do exactly the same using a 330 ohm resistor for this connection. Make sure to connect it in the same section where your LED is, which is the upper part of the proto board. The other leg should go directly to the negative rail of the proto board. On the other hand, the longer leg connects directly to one of the Arduino pins. In this case, we will connect it to pin number 3, as shown in the image. With this, we have completed the connections for the LED. Finally, let's see how to integrate the buzzer. We see it has two terminals, one positive and one negative. So we need to identify which is the positive terminal and which is the negative. In the case of my buzzer, it's quite simple, as it has a black wire that represents the negative side and a red wire that represents the positive side. Once we have identified this, we will connect the negative side either to the negative rail of the proto board or directly to one of the pins marked with the letters G and D on the Arduino. On the other hand, we will connect the positive terminal of the buzzer to pin number 4, allowing us to control the buzzing at will. Last but not least, we need to power the proto board by connecting the respective outputs of the Arduino to the positive and negative lines of the proto board. In the diagram, we see that we connect a pair of jumpers to the 5-volt pin and the GIMP pin, and on the other side, we connect them to the proto board. Physically, this is what we are doing in this image, although in this case, the cable connected to the pin marked with 5 volts is white. On the other side, we connect the same cables to the section of the proto board where the components are located, specifically to the right side of the proto board. If we connect them after the opening marked in yellow, our circuit likely will not work unless we connect a pair of jumpers between both sections. With this, we have completed assembling our motion sensor circuit. Now, let's move on to see how to code it to detect intruders. Now, let's see how to code this sketch so that our project functions successfully. In fact, the code for this project is simpler than the previous one. We will start by declaring some global variables that will represent the pins of the different components we have connected in our circuit. So we declare these pins with an integer variable. The first variable will be called a peer pin, which, if you remember, connects our peer module to our Arduino on pin number 2. Therefore, we indicate that this pin is equal to 2. We will declare a couple of additional variables, lead pin, which will be equal to 3, and a third variable called buzzer pin, which will be equal to 4. By doing this, we are declaring these variables so we don't have to remember which pin we connected our components to on the Arduino. If we want to make any changes later, we can modify this section at the top without having to change the pin number throughout our code. This is definitely a practice that will make your life much easier in case you need to make changes later. Okay, let's proceed to code our method called setup. If you remember, This method allows you to carry out the initialization of the different components, specifying how they will behave and if you have any additional rules or initializations for any component. In our case, we will specify the role that these different components will play. That is, whether they will be components that accept information for us to process, or if these components will perform some action based on the information we provide. So what we will proceed to do is call a method called pin mode. And in parentheses, we will indicate that we want to initialize or configure a peer pin as input. This pin mode method is used to configure the different pins. We have some possible values, although the most commonly used are input and output. That is, input is when you need one of the pins to receive information for you to work with that information and subsequently send some kind of message or indication through an LED, etc., via another pin. However, in this case, since we will be reading information from a pin, specifically from a peer sensor, we indicate that this pin will act as an input for receiving information. On the other hand, we will also configure our pin associated with the LED, and as you can imagine, the configuration for this pin is output. This is because this pin will perform an action outward or externally, which in this case will be to turn the light on or off. Next, we will also configure the pin related to the buzzer. As you might guess, the mode for this pin is also output. This is because we will be producing sound externally. That's why this configuration is output. We will also carry out the initialization of the serial communication between the Arduino and the PC using serial.begin 9600. We sometimes use this for some type of monitoring through the serial monitor. Okay, with this, we have finished the initialization of our program. Let's move on to the loop method, which will be cycling through the execution of our sketch. Remember that this setup method is executed only once throughout the life cycle of the sketch, while the loop method executes continuously as long as your Arduino has power. So we said that this method will be executed repeatedly. What we want to validate or find out is whether our peer has detected an intruder signal or not. To do this, we will use an if statement and we will check through a digital read of the peer pin if this equals high. Here, we missed an L. If it doesn't show up in orange, like we see here, it means you have a spelling error. In this case, I already added the L and see how the color of digital read changed. Basically, we are asking the peer or the peer sensor if it has detected any kind of signal. We are doing this thanks to using digital read. If this equals high, then it means an intrusion has been detected. Therefore, what we'll do is turn on, first of all, the LED using digital write, lead pin high. Notice how, in this case, we've used digital write as opposed to what we used here with digital read. In this case, we are reading or trying to read a signal from an external component, while in this case, we are executing a type of digital right through one of the pins. Similarly, we will indicate that our buzzer should be turned on. We will do this through digital.write, but this time using buzzer imran. That is to say, we are indicating through this high that we need to turn on the LED and the buzzer. In case we want to monitor something on our PC, we can use serial.println to write a message to the console. For example, the word intruders. With this, we have coded it to detect if there has been any intrusion. If we have not detected any intrusion, we need to turn off our different alarms. We will do this by executing the opposite of what we have above. Additionally, we can copy these 3 lines if you don't want to write everything again. What we'll do here is instead of turning on the LED, we will turn it off, turn off our buzzer as well, and finally, in that serial.println, we will put something like standby mode. Okay. We will perform a check to ensure that this sketch is 100% correct. So we click this button or click on this button. Okay. We see that the sketch was compiled successfully. Once we have compiled this sketch, we need to make sure that our Arduino is connected. In this case, it is connected. Now, we'll proceed to upload our sketch to the Arduino. Okay, Great. We have already uploaded our sketch. Let's test it. Let's move our hand over the sensor and notice how it lights up satisfactorily when detecting the movement of our hand. Remember that the peer sensor will operate differently depending on its configuration. That is why it is very important to read the document I provided in one of the previous lessons to understand how the component works and to see how you can calibrate this sensor to meet your needs. How cool! We are now in the section for the fourth beginner project with Arduino. The project we will see next is a weather station made entirely with Arduino. This is a very interesting project as we can measure almost in real time the temperature, humidity, and heat index. We will divide this project into two parts. The first part will consist of displaying the values detected by the sensor on the serial monitor. In the video, we can see this in action. We see how the values gradually appear on our serial monitor. In the second part, we will add an Arduino shield to display the values we previously printed on the serial monitor on an LCD screen. This part is an improvement to the weather station, so you don't have to depend on the serial monitor to see the values. Now, this part is completely optional, as it involves a bit more expense regarding the acquisition of the shield, although believe me, it is a worthwhile investment. To carry out the first part of the project, these are the components you will need. A breadboard, a DHT11 sensor with PCB, 3 male-to-male jumpers, and an Arduino Uno. With these components, we will look at the connection diagram for the project. The connection diagram is the one we see here. We can see that the diagram is quite simple, as we only have our HT11 sensor, and we need to identify the outputs of this sensor to connect it to the Arduino. It is a direct connection to the Arduino, including its ground and 5-volt pins. And finally, a signal, which in this case goes to pin number 2. So it is a really simple connection, and we'll see how to connect this physically in the next video. Now that we've seen the project diagram, let's learn how to connect it physically. This is the project diagram. We see that the connection is really simple. The only thing we need to worry about is the outputs of our DHT11 sensor. Some sensors have a configuration like the one in the image, meaning that the middle output pin is the one we need to connect to our Arduino pin. Note that in this case, each pin is clearly labeled. However, there are other sensors that do not have such clear labeling, as is the case with the one I will be using. Here, it simply indicates that the leftmost pin is the signal pin, which we will need to connect to the Arduino. On the other hand, the rightmost pin is the negative charge, while the middle pin is the positive charge. Once we've identified the pins, we will connect the sensor on a breadboard as shown in the image. Next, we will connect a jumper, which in my case is black, to the negative charge pin. We will connect a red jumper to the middle pin, which will provide the positive charge. Finally, we will connect a yellow jumper to the leftmost pin, or the signal pin. Once this step is finished, we will connect the black jumper to one of the pins marked with G and D on our Arduino. The red cable will be connected to the pin marked with 5 volts on the Arduino. Finally, the yellow jumper, or the signal pin, will be connected to pin number 2 of our Arduino. With this step completed, we are ready to create our sketch and upload it to the Arduino. Let's do it. We will see how to create the sketch for our weather station project. For this, we first need to take a preliminary step, which is to install some additional libraries that are part of our Arduino IDE. This is basically to allow us to use code that has been previously written, so we don't have as much complexity when creating our sketch to obtain information from the DHT11 sensor. To carry out this task, we will open a new Arduino sketch. We will go to the Tools menu, and here we have an option that says Manage Libraries. We click on this option, and we see that we have a filter to carry out the search for some libraries. In our case, we are interested in a library that we can find by searching for DHT. We press enter and we see that we have different libraries available. In our case, we are interested in installing the one called DHT Sensor Library by Adafruit. In my case, it is already installed. But if you don't have it installed, which is likely the case, you will need to click on the button that says Install. In my case, this button doesn't appear since it is installed, but you will indeed need to click on this button that says Install. Once you have installed this library, we will look for another library, which we will find by entering Ada, fruit, space, unified, space, sensor. We press enter and see that we have different options. The option that interests us is the one that matches exactly with what we wrote here. That is, in my case, it appears at the end as Adafruit Unified Sensor. So we will have to click on the button that says Install, and you should see the message indicating that it is installed. Once we have done this, we will be able to use these libraries to manage our DHT11 sensor. So we click on this button that says Close, and preferably, I recommend restarting your Arduino IDE. Once you have restarted it, we can use this HT library. First, what we need to do is type a hash symbol, the word include, a space, in between a less than and a greater than. We will write HT in uppercase followed by a dot and an H at the end. So it should look like this. You need to write it exactly as it appears here so that you don't have any issues. What we're doing with this line is including external code that is part of our Arduino sketch. This is to use what I mentioned, the Adafruit library called DHT. Subsequently, what we will do is declare the pin to which our sensor is connected, as we have done before. So we declare an integer variable and name this variable HTPin, which we will set to 2. Next, we will declare a new data type that will be of a type HT. You might have a question about what I just did. Basically, this data type is like declaring an integer data type. The difference is that in this case, DHT has different characteristics that will allow us to control our sensor or obtain information from the sensor with little complexity. So all this code, or this complexity of code, is encapsulated within this declaration we have here. This is code written by someone else, so we can use it in our sketch. And to use it, we need to declare it as follows. You will need to set a name for your variable. In our case, we will call it DHT. This is equivalent to having a declaration of an integer type, except DHT will be a data type of HT, which is the data type we have here. Next, we need to directly initialize this HT variable. If we want to learn more about this library, we can visit the official repository of this library. Here we have a file, or we are in a file called BHT. This is basically all the source code of this library, which you don't have to write, but can use. If we look at the bottom, we have a constructor here. I know this is a bit more advanced code, but just in case you want to learn a bit more, I'll quickly explain this. Basically, the constructor, or how to create a new HT data type, will first define the pin, and second, a type. And here we have a default data type, which is 6. Therefore, the required data are the pin, or the pin number, and what type of DHT sensor it is. There are several types of DHT sensors. Here we have a list of different types of sensors. We have DHT11, DHT12, DHT22, etc. In our case, we are interested in using a DHT11 sensor. Therefore, we can pass the type, this number 11 directly, or we can pass this type of HT11, which is actually the representation of the number 11. So returning to our sketch, first we said we need to pass the pin number, which is defined in the variable DHT pin. Secondly, we can pass the type, which if you remember, can be DHT11, representing the number 11. We can validate this sketch by clicking Verify to ensure everything is correct. Notice that we have a program compiled successfully. To simplify things a bit, what we have here would be equivalent to having a value of 2 as the HT pin, and here a value of 11, which specifies that we will work with a DHT11 type sensor. To use the variables, let's return this code to its original state. And with this, we have initialized this HT variable. Next, we will work with the setup method. This code is used to initialize some variables or pins we desire. In our case, it will help us initialize serial, which is the serial monitor. We will indicate begin 9600. And similarly, we will initialize this DHT variable using dht.begin. As you can see, we are using this method to carry out the initialization of this DHT class instance. Don't worry too much about the term I used, class instance. Just keep in mind that this begin method will serve to initialize this variable, allowing us to use it, as failing to initialize it could lead to problems. Finally, in the setup, we will specify that we want a delay of 5 seconds before starting the reading from our sensor. Once we finish the setup method, we will move on to the loop method, which is the code that will run repeatedly. Here, the first thing we will do is indicate that we want a delay each time we pass through this method. That is to say, we will wait 5 seconds before the next reading of the sensor data. This is mainly because there are some restrictions with the HT11 sensor, which specifies that we must have a certain amount of time before carrying out the next reading. Subsequently, after completing this task, we will declare a floating variable called humidity, which will be equal to DHT dot, and as part of our DHT variable, we have a method called read humidity. If you have noticed, the color of read humidity has changed to orange, which means you have written everything correctly. If you see that the entire phrase or method appears in black, it means you have a typographical error. In my case, it now appears in red and is valid. This method, read humidity, which belongs to DHT, will allow us to read the humidity data from the sensor. As you can see, you don't have to do anything else. You don't need to obtain additional information. With just this method, we get the information and store it in this variable. This is the real advantage of using these libraries that we have installed previously. We do not have to deal with lower level issues. Instead, we can read the data in an extremely simple way. Let me show you another example. For instance, we can read the temperature. We will declare a floating variable called temperature, which will be equal to DHT dot read temperature. With this, we will read the temperature data in degrees Celsius. But we also have another function that will allow us to read the temperature in Fahrenheit. So, we will declare another variable, temperature, and we will add an F at the end indicating that this is equal to that read temperature. It seems we are doing the same thing as above, except here the difference is that we will pass the value true within the parentheses, which indicates that we want to read the information in Fahrenheit. Once we have read these 3 values, we will perform a check to ensure that we have information in all 3 variables, meaning we have successfully read from our sensor. We will do this with an if statement. So I will ask, if is none humidity, or is none temperature, or is none temperature. Notice that I placed 2 parentheses at the end. The first parenthesis corresponds to is none, and the second parenthesis corresponds to the closure of the if statement. We will place an opening brace and a closing brace. Basically, we are asking if this is none function if these variables contain a value. If they are empty or do not have a value, then there has been some issue, and we can print, for example, for serial.println error in reading from the sensor. Let's correct that here to reading. Later, it is important to place the word return so that the code below no longer executes. Essentially, what we will do with this return is exit this function so that, as I mentioned, the code following this if statement does not execute. Once we have ensured that we have information sent by the sensors, we will declare a new variable, which will also be a float, named HIC, which essentially means heat index. In English, it would be heat index in Celsius. This will be equal to DHT. And as part of this DHT variable, we also have a method called compute heat index. As parameters, this method receives a temperature, receives a humidity, and finally, whether the temperature we are passing is in Fahrenheit format. In this case, the temperature, if you remember, is in degrees Celsius. Therefore, we will pass the value false. We will declare a second variable called HIF, which is heat index in Fahrenheit. This means heat index in degrees Fahrenheit, and this will be equal to DHT dot, and again, compute heat index. Notice how these methods allow us to carry out this operation very simply. We will pass temperature as a parameter, but this time the temperature is in Fahrenheit format, so we place the F at the end, and finally humidity. In this case, there is no need to pass a true value, since automatically this function has a default true value at the end of the method declaration. Here, we will store the heat index information in degrees Celsius and give this second variable the heat index in degrees Fahrenheit. Lastly, what we need to do is basically print the information to our console or serial monitor. We will proceed to print this information using serial.print. Notice that we're using print because it allows us to write many statements in a single line. If we were to use println, it would print the following text on a new line. That is the difference between println and print. Let's write within this first serial.print, humidity, space. Notice that this is in quotes, and then we would use print with humidity in parentheses. Notice that in this print, we haven't used quotes because we want to print the actual value of humidity, which is a variable that holds the humidity value. This is why we are not printing a pair of quotes as in the previous case. Next, we will do a serial.print, and again in quotes, we will print percent temperature, space. On the next line, we will do serial.print with temperature in parentheses. Then, in the next line, we will write degrees, Celsius, space. We close this line, followed by print with temperature in parentheses, closing the parentheses with a semicolon. Then, we will print quote degrees Fahrenheit, and then heat index, space, closing quotes, closing parentheses, and semicolon. Following this, we will print the variable H and C, semicolon. Next, we will print with degrees Celsius in parentheses, semicolon. Here, I need to add some quotes, and we will also introduce a space. Then we will print the variable H and F, or the H and F variable, and finally, we will do println with degrees Fahrenheit in parentheses. All of this in quotes and without spaces. If you notice, println has been used here. This is because after printing this last text, I want a line break so that all the information is printed again, but on a new line. Let's check if we have any errors. Let's validate this sketch. Okay, and we see that the sketch has been compiled. What remains is to upload this sketch to our Arduino. To do this, we will ensure that we have the correct board selected and that we are on a valid port. Once we have this, we will upload the sketch. And once the sketch has been uploaded, we will click on this button that says Serial Monitor to start the monitor. We wait 10 seconds before information starts printing, okay? And notice that we are successfully printing the data we specified. The humidity, which is at 56%. The current temperature, which is 33.10 degrees Celsius, 91.58 degrees Fahrenheit, and the heat index, which is at 38.37 degrees Celsius, equivalent to 101 degrees Fahrenheit. We see different values as we proceed, and surely, if we leave it for longer, we will see how the information varies, both in temperature, humidity, and the heat index. This is how we successfully printed information obtained from our HT11 sensor. In the next video, or in the upcoming videos, we will see how we can integrate an LCD screen so that we don't depend on this window we have here, which is the serial monitor. Let's get to it. To carry out the second part of this section, these are the components needed. A proto board, an HT11 sensor with PCB, 3 copper wires, an LC keypad shield, and an Arduino Uno. These components do not differ much from the original project. so we'll move directly to see how they are physically connected. If we want to add the LCD shield, we need to change the jumpers we connected earlier. Later, we will see why. Instead, we will replace them with 3 copper wires, which in my case, I have obtained from a UTP cable. In the image, we can see that the negative wire is connected to a green wire, the positive wire to a blue wire, and the signal to a white wire with blue. We will connect these wires exactly as we did with the jumpers. That is, the green wire, which is the negative, will connect to the pin marked with God, and the blue wire will connect to the pin marked with 5 volts. On the other hand, the white wire with blue should be connected to pin number 2 of the Arduino. Once we have swapped the jumpers for the copper wires, we need to insert our LCD shield. To insert it into the Arduino, we should ensure that the analog pins marked with an A at the beginning match both on the shield and on the Arduino board. In this order, we must carefully insert the shield onto the Arduino board. We have replaced the jumpers with copper wires so that we can insert the shield and it fits as we see in the photograph. This is a little trick to avoid having to solder wires to the LCD shield. On the other side, we see that the copper wires have also stayed in place without interfering with the LCD shield. This is how your LCD shield should look on your Arduino board once we have placed it. Now, let's see how to implement the coding to display messages directly on it. Here we have the sketch we used earlier to obtain information from the sensor and send it to our serial monitor. Now, let's code what is necessary to display information on our LCD shield. For this, the first thing we will do is include an additional library apart from DHT. To do this, place the hash symbol, the word include, and between a less than and greater than symbol, the word liquidcrystal.h. If it appears in red, it means you have written it correctly. If not, check for case sensitivity to ensure it matches what I have written. After declaring the data type for HT, we will leave a blank space and declare a data type, liquid crystal, space LCD, and within parentheses, we must initialize LCD. In the specific case of the shield we have here, we need to use the following values: 8, 9, 4, 5, 6, and 7. So, if you're using the same shield, you must use the values I've indicated here. Subsequently, we will initialize this variable LCD after DHT.begin through LCD. We use the begin method, and in parentheses, we specify the dimensions of our LCD. In this case, 16 spaces horizontally and 2 vertically. Then, we will indicate LCD.setCursor. This is to send the cursor to a certain position on our LCD. In this case, we will indicate that we want to go to position 0, 0, which is the beginning of the LCD. We can print a message, for example, lcd.print, and we will print weather station. With this, we have completed the configuration part of the LCD in our sketch. Now let's move on to the loop section, or the loop method. To code this method and reflect changes on the LCD, we will go to the end of the serial.print, specifically after this serial.print element, and we will start working with the LCD. To fit all the information on our LCD, we will need to print only certain information, as we will not be able to display each data point as we did with the serial monitor. We will indicate lcd.setCursor to send the cursor to the start of our LCD screen. Then we will do lcd.print to print H. This H will refer to humidity. Later, we will do an lcd.print, and to remove the decimal values, we will convert it to an integer data type, which will truncate our data to display it only in integer format. Then we print humidity, followed by an lcd.print with parentheses, quotes, a percentage sign, a space, an uppercase T, a colon, another space, and we close the quotes in parentheses. Here we will then print the temperature. So we do an lcd.print, convert the temperature data to an integer data type once again, which is to ensure we only print the integer values of our data and save some space. Next, lcd.print in parentheses quotes. In this case, I need to print this value that I have here. This is equivalent to printing a degree symbol that we had in serial dot print. The only difference is that for it to display correctly on my specific shield, I need to print this character instead of directly printing the symbol. Because if I print the symbol, some strange symbols appear on my LCD. So with this, I add a space. After printing the degree symbol, add a C, a space, and close this string. But that is, I have two strings that are part of my print method. Next, I will do a set cursor to position myself on the second line. I do this by going to coordinates 0, 1, and I will continue printing information. In this case, HI, which stands for heat index. I close this string, do another LCD dot print, print the variable HIC, which contains the heat index in degrees Celsius, and finally, LCD dot print. Again, I will print this symbol, the degree symbol, space, C, space. And now I have this string. Let's test our program to see if everything is correct. Once we have seen that the program has compiled successfully, we will proceed to test it on our LCD screen. So, let's upload the sketch to our Arduino board. Once it is uploaded successfully, let's see it in action. Okay, I will play this video faster so that the changes are more visible. Great! With this, we've built our weather station, which allows you to see the changes in different temperatures and humidity levels in your city almost in real time. And you could do much more complex things with this information. For now, let's stop here and move on to see the last beginner project for Arduino. Hello, how are you? I'm Hector Torres from Interesting Projects. In this video, we will learn how to create a distance meter using the ultrasonic sensor HCSR04. The video will be divided into two parts. The first part will focus on connecting the sensor to our Arduino and getting it to work. In the second part, we will connect a 16:2 LCD display to show the measurement information. Here we have the result of this project. We can see how as we move the box closer to or farther from the sensor, the distance displayed reflects the calculated distance. Isn't that great? To carry out this project, these are the components you will need. I will leave a link in the description to the interestingprojects.com website, where I'll provide the diagrams, component list, and source code. The components are a proto board, a 16:2 LCD screen. We will connect the display via an I2C to LCD adapter for easier connection. We will also need the HCSR04 sensor, an Arduino Uno, and in my case, 8 jumpers. Now that we have seen the components we will use, let's proceed to assemble our project step by step. Let's start with the first part of the project, connecting the sensor to the Arduino. Here we see the connection diagram. We will look at how to connect each component step by step. Let's begin with the sensor. We will place it facing outward from the proto board. The diagram looks a bit odd, but it had to be drawn this way to match how we're positioning the sensor. This sensor has 4 pins, which we will fit into the proto board. The next step is to connect the pins marked with VCC to the positive rail of the proto board, and likewise, the pin marked with G and D to the negative rail of the proto board. On the right side, we see how to make this connection physically. Next, we need to connect the eco and trig pins of the sensor to the Arduino in order to program the sensor. Let's start with the pin called eco. We will connect a jumper, in my case brown, from the output rail of the eco connector to pin number 10 on the Arduino. Now let's proceed to connect the pin called trig. We will connect a jumper, in my case yellow, at the output of the connector on the proto board. We will carry this wire to pin number 9 of our Arduino. Finally, to complete this assembly section, we will connect the Arduino pin labeled 5V to the positive rail of the proto board and one of the pins marked with G and D to the negative rail. This is how the physical connection looks with both wires and the connections on the Arduino. Pretty simple, right? With this, we are ready to create our sketch and test our brand new ultrasonic sensor. Let's do it. Okay, here we have our Arduino IDE. We have a newly created sketch. The first thing we're going to do is declare a couple of constants to represent the pins of our HCSR04 sensor. Let's declare the first constant as an integer, naming it TRIG pin. If you remember, this trig pin was connected on our Arduino to pin number 9. Next, we will declare a second constant, which will also be an integer, and we will call it echo pin, which will be equal to 10. Okay, these two constants are the only ones we will use for now. As a second step, we will initialize these pins within the setup method. So we will do this inside the setup method, indicating pin mode, specifying that we wish to set trig pin as an output, and also setting echo pin as an input. Here, it's a semicolon instead of a comma. If you're wondering why we're specifying the value output for the trig pin and the value input for the echo pin, it's because our sensor has two components. Firstly, we have a transmitter, and we also have a receiver. In this case, the transmitter will be responsible for emitting an ultrasonic wave, which will bounce back upon hitting an object and be received by our receiver. In this context, the transmitter is designated as TRIG and the receiver is labeled as echo. So, if we emit a signal from the transmitter, it means we need to set this pin as output, since we will be sending some kind of wave outward. Since we are going to receive the wave we emitted at the receiver, we must specify that this echo pin is set as input because we are receiving information from the outside. Finally, we will initialize our serial monitor through serial.begin 9600. Okay, we have our setup method ready for this part of the project. Now, what is the next step? The next step is to measure the distance between our sensor and the object we are detecting. If you look here, we have a distance that we need to obtain in order to know how far an object is. Now, we must understand that the sensor we have here does not actually measure a distance as such. Instead, the way we will receive the information is by measuring the time it takes for this wave to travel through space. That is, how long it takes to complete this journey we see here. To measure this information, as part of the Arduino documentation, we have a method called pulseIn, which we have here. Let's quickly read the description. It states that it reads a pulse, whether its value is high or low, on a pin. For example, if a value is specified with a high value, this pulseIn method waits for the pin to go from low to high, starts a timer, and then wait for the pin to return to its original low state, stopping this timer. Finally, it returns the length or duration of the pulse in microseconds, which is the value we will receive. Another important point is that it works with pulses ranging from 10 microseconds to 3 minutes in duration. So this method will be one of the key components in our project, as it will allow us to measure precisely how long it takes for this pulse to go out and back. Now let's return to our Arduino sketch and proceed to declare a new variable. It will be of type long and will be called duration. Let's go to our function called loop and begin working with our sensor. The first thing we'll do is turn off our sensor if it is on. To carry out this task, we will perform a digital write, indicating the pin number, and we will assign it a low value. To ensure we give it enough time to turn off this signal, we will use a function called delay microseconds. It is very similar to the delay function, but it works with microseconds. We will tell it that we want to turn off this sensor for 2 microseconds. The next step is to turn on our sensor again so that it sends an ultrasonic wave. We will do this using digital write, and we will set trig pin to a high value. This is to ensure we send a sound wave. Subsequently, we will specify that we want to send this wave for 10 microseconds. This is to ensure that our pulseIn function works correctly. As you remember, the minimum value for it to work correctly is 10 microseconds. Therefore, I will specify delay of microseconds and pass the value of 10, which is 10 microseconds. After that, I will indicate that I want to turn off the sensor using digital write. Trick pin, and I will send the low value. Now that I have specified the sending of the wave, we need to set up the part where we receive this wave back. To do this, we will set duration equal to, and we will use this function we saw in the Arduino reference guide, which is pulsi. We will pass as the first parameter which pin we want to handle. In this case, we will not use trick pin, as trick pin is responsible for sending the wave. Instead, we will work with echo pin, which is responsible for receiving this ultrasonic wave. We will measure how long it takes to send and receive this wave. Therefore, we will set the high value. With this, we can start testing our sensor. We can write serial.println to display the duration. If you currently have your Arduino connected with the components setup we saw earlier, you can first validate your sketch. Since it has been compiled, you can upload the sketch to your Arduino. Now let's see what we get in the serial monitor. Okay, and notice that we get a series of values here. This actually represents the duration of a wave in microseconds. If I start moving the sensor, notice how we have a change in the distances, or more specifically, the duration in detecting the ultrasonic wave. I will close my serial monitor, and let's return to the slides. Okay. We now know the duration it takes for a wave to travel to our sensor and back. The next step is to determine the distance based on the time we have received. If you remember from your physics classes, we know that there are three formulas to work with speed, distance, and time, which are these here. In our case, we have this variable called time. You may not know, but we also have this variable called speed. How do we know this? Well, because we know that the speed of sound travels at 340 meters per second by default. Our wave is an ultrasonic wave, so it will adhere to the speed of sound. However, since we are not working with meters per second, but with microseconds, we will use this value, 0.034 centimeters per microsecond. With this, we have both the speed and the time, allowing us to determine the distance. We will then know that the distance will be equal to 0.034 times the duration we receive from the pulse-in function. However, this duration is the time it takes for the wave to travel there and back. What we're really interested in is knowing the distance that exists only between the sensor and the object. Therefore, we will need to divide this result by 2. As we do not wish to know the distance from the sensor to the object and vice versa. With this in mind, we will proceed to create a new variable. This variable will be of integer type and will be named distance. We will go to our loop method, and once we have attained the duration of the wave traveling to and from, we will set distance equal to, and in parentheses, we will place duration times 0.034. Which, if you remember, is the formula we covered divided by 2. Let's see what happens when we display this information on our serial monitor. We upload the sketch to our Arduino, check the serial monitor, okay? And as you can see, we now have smaller values, which represent the centimeters or the distance to an object. If we proceed to move the sensor, notice how the value increases the farther away an object is. With this, we have concluded the first part of our project. Now, let's see how we can integrate an LCD display into our project to show this information. In this second part, we will integrate an LCD screen into our project to display the information without needing to have the serial monitor open. For this purpose, we will use an I2C to LCD adapter to minimize the complexity of the connections. Both the display and the I2C adapter usually come unsoldered, so you will need to solder the adapter into the slots of the LCD screen, resulting in the assembly shown in the image. You might already have an assembled piece, or you may need to solder them. If you want to avoid this, or if you are just starting in the world of electronics and do not have a soldering iron, I will leave a link in the description to a very complete kit that includes the pre-soldered screen with pins, allowing you to easily insert it into a protoboard. Additionally, this kit includes an HCSR04 sensor, so you only need to acquire the I2C connector separately. Since I have this LCD screen, I'll proceed to insert it into a mini protoboard. As I mentioned, this step is completely optional, as you might have your screen soldered directly to the adapter. This is how the screen looks mounted on the protoboard. Next, we will insert the I2C adapter, which usually comes with the pins already soldered, ensuring they match the display pins with respect to the adapter pins. Once we've connected the adapter to the screen, the next step will be to connect the adapter pins. Let's start with the pin marked G and D. We will connect this to the negative rail of our protoboard. Make sure to connect it in a place where you have continuity. As we can see, in the protoboard I have, the continuity is interrupted in the center, as represented by the line shown in the image. Now let's connect the pin marked VCC. Let's connect a jumper, in this case red, to the positive rail of the protoboard. Great. Now let's move on to the pin marked SDA. I'll connect a gray jumper to this and take it to the pin labeled A4 on my Arduino. Finally, let's connect the pin marked with SCL from the adapter. I will connect a white jumper to my Arduino at the pin marked as A5. Great. With this, we are ready to code the display of the results on our LCD screen for the project. Let's move on to the Arduino IDE. Okay, let's integrate the LCD screen into our project. The first thing we need to do is find the physical address of our LCD screen to use it as part of our project. Fortunately, we have a website within the Arduino playground called I2C Scanner, which will allow us to detect the physical connection of our display. Here we have the source code of the sketch. Let's copy it. We return to our Arduino IDE. Let's create a new temporary sketch and paste the code we copied from the Arduino page. We will proceed to upload the sketch to our Arduino. Okay, it's uploaded. Let's open the serial monitor. Notice that it indicates we have found an I2C device at address 0x27. Let's save this data. Close the serial monitor. The next step is to install a library that will allow us to work with this I2C adapter. So let's go to Tools, Manage Libraries, and here in the search filter, we will type Liquid Crystal I2C. Okay, let's proceed to search for a library among these, called Liquid Crystal I2C, authored by Frank D. Brabander. In my case, since I have already installed the library, it shows up here as installed. However, in your case, you will need to click on the button that says Install if you have not installed this library. Once we've done this, we are ready to proceed. What we will proceed to do is import a couple of libraries into our Arduino sketch. So, let's go to the top of the sketch to write. Include. Between the less than and greater than symbols, we will write wire.h, and we will also include the library liquid i2c.h. Be careful to write this library correctly, as if you do not, it will be as if you never imported this library, resulting in many errors. The next step is to create an object of type liquid crystal from this library. We will discuss what objects are in another video. For now, after declaring this variable called distance, we will write liquid crystal I2C space, and we will call this object LCD. This name can be whatever you want. In parentheses, we will write the physical address we found from the previous sketch. In my case, it was 0x27. We place a comma and indicate the number of rows and columns of our display. In my case, it is a 16x2 display, so I enter these values. Now that we have created this object, we need to initialize it. In the setup section, after initializing serial, we will write lcd.init to initialize our object. We will also specify lcd.backlight to turn on our display. Now that we have initialized our object, let's return to the loop method and scroll down after performing the print on the serial monitor. we will write lcd.setCursor, which will help us position where we will start writing the information. We will indicate that we want to write at the first available character, or the first available space on our display, using setCursor00. We will likely print a string using print, and we will write distance, followed by a space. This message will then appear by default in all messages. Or we will write a specific string as part of the message. Subsequently, we will write lcd.print, and we will print the variable called distance again. As you can see, we're using print here, so this distance and value will be written on the same line. Finally, lcd.print, and we'll write a space followed by cm and the closing quotes. Lastly, to make this look good, we will apply a delay so that it doesn't look bad when the new information is printed. Let's upload the sketch to our Arduino board. Here we have our sketch running on the board. Notice that we have a problem. The issue is that when we print the information, sometimes some characters remain as part of our implementation or as part of our LCD. This is an error that we need to solve. To fix this problem, we will go back to the Arduino sketch and declare a new variable, which will be of integer type and called last distance. Let's assign a default value of 0. The purpose of this variable is to allow us to compare this value with the previous distance. If a new value is found, we will clear the information from the screen. If no new value is found, simply nothing will be done. Now, let's return to the section where we handle the printing to the LCD or the screen, and let's check if the distance is not equal to the last distance. We will cut and paste the content that we had previously created. Notice that the delay is outside of this if. So if a new value is found, we will indicate that we want to clear the screen using lcd.clear. Finally, after this last print, we will indicate that the last distance is equal to the distance, so that this variable is updated and the next check is made against the last measurement. Okay, let's verify our program to ensure that everything compiles correctly. Once the project is compiled, we will upload this code to the Arduino board. Here we have the operation of our project. Notice that every time we move an object further away or bring it closer, the values on the display change, and those characters from a previous print no longer appear. Therefore, we already have our complete project.